Okay, thank you all for joining us. We had to reset the stream, so welcome back if you're rejoining us on this new link. And okay, so we're in the hour 15 of the weather and climate live stream, and we've got only a little bit less than about 35 hours to go. So hope you've been enjoying these talks so far. My name is Vanessa Sun. I'm a PhD student in atmospheric sciences, and I research improving air quality. And we're gonna start the next session with reminding you why we're here doing this stream and also being on your screens. The United States has been a world leader in weather and climate prediction. We developed the first computerized weather forecasts, the first computer models of the climate impacts of carbon pollution. Alongside these computational tools, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle. This miracle was made possible by decades of US taxpayer funding and by a merit-based system in which scientists have judged the best projects to receive funding. But now all of this is at risk. The administration is threatening to cut the National Science Foundation and NASA's Earth Science budgets in half. They're looking to eliminate the National Oceanographic and Atmospheric Administration's research arm and slash programs for training the next generation of young scientists. I've personally participated in NSF federally funded research programs in the past and organized conferences to bring young researchers in such crucial research fields together. And to think that such programs are at risk is quite devastating on a personal and professional level. But past this, these cuts also hurt everyday Americans. Weather stations are so short-staffed that we are losing our observational coverage, worsening our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk down in size. But it doesn't have to be this way. If you like what you see here, then we ask you to please use the link below to contact your representatives and tell them to defend weather and climate science, to fully fund NOAA, NASA, the National Science Foundation, and other agencies that make this work possible, and to protect NCAR. The House and Senate are making these decisions right now, so now is the right time to make your voice heard. So with that, our next speaker will be Marc Alessi, speaking about working with data and AI. As a reminder, all of our speakers' views are their own, and they are not representing their employers or any other institution. And I want to remind you all to put the questions that you have in the chat as the stream goes on, and we'll take 1 or 2 questions at the end. All right, take it away, Marc.
Thanks, Vanessa. Also, love your pens.
Thank you. It's Happy Pride Month.
Yeah, this is so funny because this is my first time presenting on the live stream, but I'm one of the organizers, and it's been exciting to see from both sides, and I'm so excited to be presenting this year. So I'm going to talk a little bit about my work. So I'm a climate scientist, and I actually work outside of academia. So this, if people are interested in maybe not becoming a professor or staying as a researcher in academia, I can give you some ideas about what I do outside, which honestly is basically very similar research. But the work that I do at the Union of Concerned Scientists, you can see on the bottom here, is kind of work that follows our campaign goals in certain ways, but it's still using kind of the physical climate science background that I am trained in from my PhD, master's, and bachelor's. So I'm gonna just briefly, I'm gonna run through some of these slides a little bit quickly, but one of the projects I've been working on is filling in historical temperature data sets with AI, particularly in global south regions. So we have historical temperature data sets, right? Because stations record temperatures around the world. However, a lot of locations are missing temperature data. And so something that I've been working on is using AI to kind of fill in these temperature gaps, and I'll kind of explain how the AI does that. And the reason I'm doing this is because I want more climate attribution studies to be carried out. A climate attribution study is a study that asks the question, what percent of this extreme event was influenced or caused by fossil fuel caused climate change? Okay, so let's say, well, let me give an example. Hurricane Helene, a couple of years ago in 2024, made landfall in Florida, brought devastating rains to Appalachia, Georgia, South Carolina, North Carolina, parts of Tennessee. And there were studies that came out that said this storm was 50% more intense. These areas received 50% more rain because of fossil fuel caused climate change. So that's a climate attribution study. Now, in order for a climate attribution study to be carried out, we actually need long and reliable records of observations to test model skill. And I won't really go into this, but just know that in order to do these studies, we need to know what happened in the past because we need to make sure our climate models are accurately replicating those extreme weather or climate events. Now, there are significant gaps in the observational record for climate extremes, especially in global south regions, sub-Saharan Africa, northern parts of South America, parts of Central America, Caribbean, Middle East. These locations don't have as many temperature observations as global north, and this is a significant problem because it makes it hard to do attribution studies in these regions, which are the same regions that are particularly the most vulnerable from anthropogenic climate change. So a recent paper was released in 2024, basically summarizing the most important issues with climate attribution. And one of them was a lack of observational data identified as one of 6 key limitations for EEA, stands for Extreme Event Attribution. So my goal in this is to create a gridded historical data set of climate extremes by filling in missing data in global south regions using machine learning. And the machine learning, or ML, is a type of artificial intelligence, or AI. This work follows the success of another paper in 2024, which used machine learning to reconstruct observations of European climate extremes. So they literally looked at a European historical temperature data set, and then they basically trained a machine learning model on weather patterns and then gave it the observations, and it could fill in kind of the missing temperature data. Just really quickly, the color bar here is representing the percentage of days when daily max temperature is greater than the 90th percentile for a given month. So for example, you can see that parts of the Iberian Peninsula were experiencing a heat wave during this particular month, which I think was in the 1940s. And there it is, November 1947. So how does climate reconstruction AI work? I give it basically a data set with missing data. I give a machine learning model, in this case, a convolutional neural network, a data set. I give it climate model data, but then I apply kind of a random mask to it. So I say, you can't see this value or this value or this value. And then I ask the CNN to predict what the values are in those missing areas. And that's kind of how, it fills in the missing data in these observational temperature records. I use a bunch of different temperature data sets, which I don't need to go into at this point. How well does, and when it says CRAI here, this is Climate Reconstruction AI. This is kind of the acronym that they call it in the 2024 paper. So how well does this machine learning approach perform during the 1947 heat event that I just showed? Here is a data set called HADX3. That's one of our climate extremes data sets that already fills in observational data gaps, but it uses a different statistical approach called angular distance weighting. And the takeaway here is that our current approaches to filling in historical data smooth out extremes too much. So for example, this is ERA 5. This is not ground truth, but it's another way of looking at historical data. But it basically is an approximation through a model when we feed it observations. And you can see that ERA kind of identifies this heat wave in the Iberian Peninsula, and it kind of shows it a little bit better than this HADX3 data set. So these are both kind of observations. This one is more observation with infill data gaps. This one is observations plugged into a model, which gives us a reanalysis data set. This is the original ground truth. And this is the machine learning approach. So you can see that the machine learning approach nicely identifies the Iberian heat wave. It preserves kind of those extremes. It doesn't smooth out the data like the HADX3 data set. So there's actually a lot of promise with this data set that we could use, of course, for climate attribution studies. And as I said, yes, the HADX3 data set shows over smoothing. That's this one up here due to the angular distance weighting method. So instead of ADW, which is a statistical method, we're going to use AI to fill in data gaps. And I just mentioned here that, CRA does good with the heat wave. So statistical approaches like ADW are limited, whereas CRAI, this machine learning approach, trains on physically realistic climate weather patterns over a continent to make a prediction. And what exactly do I mean by that? Well, let me just give a brief example. Let's say I'm looking at a weather map of the United States, and this green line here is the jet stream. Now, the jet stream is a river of air that weather systems travel along, and typically north of the jet stream, you have a cooler air mass, and south of the jet stream, you have a warmer air mass. So at this time, the eastern United States is cold, and the western United States is hot. This is a pattern that actually dominated a lot of this winter. So for example, here's the temperature departure for this past December. The west was smoking hot, and the east was a little bit cooler than average, but a lot of people thought it was very cold because the last 10 winters have been so warm, which was very interesting in climate communication. Another topic. Okay, let's say we had very limited temperature observations. We don't actually here in the United States, but let's say we did. Let's say we only had temperature observations from these dots. And you can see that in the west, we have a few observations. I'm denoting dark red as very warm, orange as not about normal, and blue as below normal. You can see in the west, we have some above average, and then in the east, we have one station below normal. However, the machine learning model literally trains on basically patterns of climate data. So it can easily identify patterns of weather or climate in our climate system, in our weather system. So it's when the climate model sees that it's warmer than average, when the machine learning approach sees that it's warmer than average in the west and might be cooler than average in the east, it's going to make a guess that the east is cooler than normal, the west is warmer than normal, because it kind of imagines the jet stream to be in this position. So machine learning is cool because it can identify patterns in weather or climate and then apply that to data. So again, our goal was to create this historical data set. We leveraged multiple data sets beyond the data sets in the original 2024 study. And just to give an example, this is the West African heat wave event in March 1998. This is the ground truth. So we have SST data or sea surface temperature data. And then this data, this is inland data. You can see Nigeria here. You can see Niger, Togo, Benin, Ivory Coast here. And you can see that we're missing a lot of temperature data, especially in Nigeria, Cameroon. However, when we apply our machine learning approach, it nicely infills the data and even identifies and fills in the rest of this heat wave event that was particularly striking in March of 1998. This is kind of just comparing observations to our machine learning model to ERA 5 data, which is kind of our ground truth, despite the fact that it's not ground truth. And the only reason I'm showing this is really because I forgot to take the slide out, but it does compare these three together, which is very important to make sure that our machine learning model is doing okay. And it actually does better than ERA data compared to observations, which is very important. And also just pointing out that we get more observations in the 1970s for the Global South, which significantly helps the machine learning model. Okay, that is all I have for now. I'm willing to take questions or talk about anything that did not make sense.
Okay, great. Great talk. Really enjoyed it, Mark. We do have one question in the chat. I'm hoping you're able to answer it. So in a previous talk, they mentioned ways of collecting historical temperature, such as corals. Are there other biological / other ways that this data can be collected, and how accurate is it? I know it's a little different from the climate models that you were mostly talking about, But hopefully, if you know any, if you have more of a oceanography background or know more on that, yes.
So my background is not in oceanography, but I can say that there are a lot of ways to collect historical data. I mean, ice cores, tree rings. A lot of trees are, actually very old when you find them, not fossilized, but just out in nature, I guess.
Yeah.
You can look at like the oxygen isotopes, which gives you a good idea of how much rain fell at a certain time thousands of years ago. So there are other ways besides corals, for example. In my talk, we're not adding any of these methods because it's so recent we don't need to go back into. I actually don't know the time range for corals, but I know we don't need to go back to oxygen isotopes to figure out temperatures back then. And I cannot comment on accuracy. I know there are large ranges of uncertainty, but climate scientists always take that into account. They tend to be very conservative in their estimates.
I've held an ice core before, and I don't know if I would have like thought of it as like the first thing, but yeah, that makes a lot of sense. I think we have enough time for like one more question. What is the limit where the machine, in terms of like machine learning, cannot correctly fill in the incomplete data, i.e., lots of gaps?
That is a really good question. What is my life 6927? If you saw actually my last slide with the crazy line graph, I put like a line and I said in the mid 1970s we got a little bit more observations in the global south, and that actually improved the machine learning method significantly. So when you don't have any inland observations, which is very common in the global south before like 1950, your machine learning method cannot do anything because you can't even get one temperature observation in like northern Niger to say, hey, there's actually a heat wave in this location, so the rest of the sub-Saharan West Africa should be doing this with their temperature. Since we don't even have that, you can't make a prediction. Even the machine learning method can't, because we don't know what's going on in the interior parts of the global south. So there are definitely limits, and you kind of identify where that happens just by comparing to the data we have, basically. Great question.
That was a really great question for from the audience, and really enjoyed your talk, Marc. And yeah, thank you so much for telling us about your work.
Thanks, Vanessa. Good luck with the rest of the hosting.
Thank you. All right. Thank you all for. So moving on, thank you all for joining us in hour 15 of the Weather and Climate live stream. Only a little less than 34.5 hours to go. Hope you've been enjoying these talks. So before we hear from our next speaker, I want to remind you why we're here on your screens and doing this stream. The United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecasts, the first computer models of the climate impacts of carbon pollution. Alongside these computational tools, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle. This miracle was made possible by decades of US taxpayer funding and by a merit-based system in which scientists have judged the best projects to receive funding. But now all of this is at risk. The administration is threatening to cut the National Science Foundation and NASA's Earth Science budgets in half. They're looking to eliminate the National Oceanographic and Atmospheric Administration, or NOAA's research arm and / programs for training the next generation of scientists. I'm personally working with some data collected by NOAA scientists in my current air quality work and have several collaborators from NOAA laboratories. And they're all doing such great pioneering research, yet the proposed budget cuts and dismantling of these laboratories are going to hurt our research endeavors, and these cuts are going to hurt Americans as well. Weather stations are so short-staffed that we are losing our observational coverage, worsening our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk. But it doesn't have to be this way. If you like what you see here, then we ask you to please use the link below to contact your representatives and tell them to defend weather and climate science, to fully fund NOAA, NASA, and the NSF, and other agencies that make this work possible, and to protect NCAR, the National Center for Atmospheric Research. The House and Senate are making these decisions right now, so now is the time to make your voice heard. Our next speaker will be Dr. Michela Biasutti, speaking about storms. As a reminder, all of our speakers' views are their own, and they are not representing their employers or any other institution. And make sure that you put your questions in the chat as the stream goes on, and we'll take 1 or 2 questions at the end. So with that, thank you so much for our speaker, and let's hear it for our speaker.
Good morning, everybody. This is my first sentence of the day. I hope my voice is okay. My name is Michela Biasutti. I work at Columbia University, and today I'm going to talk about traveling storms, in particular those storms that bring extreme rainfall to Africa. But I'm also going to try to explain why they matter for us here as well. And before we get into the science, I want to tell you a little bit about who I am. And I started out studying physics. In fact, I graduated from the University of Trieste in Italy in the mid-90s. And basically, Italy had given me 20 years of excellent public education, but then there was nothing for me there in terms of a good research environment. And the United States was really the place to go. So I was recruited to the University of Washington for a Ph.D. in atmospheric sciences, and I got my degree in the early 2000s. And then I moved to New York to the Lamont Doherty Earth Observatory, where I've been ever since. I also now teach at the Columbia Climate School. So it's been a wonderful career, and most of it has been thinking and writing and doing math about rain. The rain in particular that falls on monsoon regions, like here, a photograph of India, but especially, when rains are trouble. So when there's not enough of it and you have a drought, as it happened in the Sahel in the 1970s and 1980s, or where you get too much of it in a short time, like it happened in Pakistan more recently, or when the summers get so hot that fires break out, like here in Europe recent time. And so let's start from the beginning. What is the recipe for rainfall? If you need a cloud, it's pretty easy. I don't know if any of you have been following Sil in his walk to New York and from New York to DC, and he showed how you can make a tiny cloud in a bottle. In the atmosphere, the easiest way to do it is to take some water vapor in a parcel of air and bring it up where it's cold. So water vapor and upward motion gives you a cloud, but usually it gives you just something cute and like these fair weather cumulus. But if you want rain, you need to get something a little bit bigger, taller, larger, and long-lived, so that you can form the drop from droplets to big raindrops. And so we need something more to do something like this. One possibility that happens a lot in the tropics is that you get these mesoscale storms, this large storm, when there's some wind shear in the background. And what wind shear is just the change in the background wind with high. And what this does is basically keeps the upward motion in the cloud and the downward motion that happens, especially when there's rainfall, separate from each other, so that you can get a continuous flow of moisture unimpeded, and things get organized neatly, and the storm can grow larger and can grow for a longer time, so that we get a lot more rainfall. So how do these storms look like? Here are satellite images. What we're looking at is brightness temperature. So it's the temperature at which the satellite sees the emissions from above, and the lighter the color, farther up in the atmosphere these clouds reach. And so those are the big angry clouds that make a lot of rainfall. And so what you see here is this blob of convection that travel through Africa. If you can see the contour of the continent here. And so we go from having very small kind of thunderstorm rainfall to something that is organized in this much larger scale. So something like this is the size of New York State. Okay. So here is another beautiful image of one of these storms taken from the International Space Station. And so you can divide them in a broad region, that's the anvil region. And then there's places where the convection is really, really intense and some often overshoots even this anvil region. And these are the places where rainfall is the most intense. But here, the entire system gives you a sense of the entire system and where we have rainfall in general associated with this storm. And so when you look at this picture and you think about, okay, what's the large system and what's the small little embedded convection, the large system in places like the Sahel give you more than 70% of the total rainfall, and the smaller embedded cloud towers give you 70% of the extreme rainfall. So we can follow these guys from above, and we can figure out what's happening with rainfall in this region. And we've been doing this for 40 years. So, as I said, the fraction of rainfall that comes in these large storms, mesoscale convective systems, is more than 70% in the Sahel, this region of Africa, and the extreme precipitation is more than 80% coming from just these really strong towers. Over the course of the decades, this rainfall in this part of the world, in the Sahel, has changed quite a lot. And so it went from a pluvial in the 1950s to some really, really severe droughts in the 1970s and 1980s. And then it's been leveling off towards average in the last few decades. But the recovery from drought over the last 40 years has really coincided with the increasing extremes. And so we have these beautiful satellite data. We can figure out what has happened exactly in these last 40 years. And so we can look at the amount of rainfall that fall as extremes. And this is work done with a student and collaborators in Austria. And so we went from about 60 millimeters for the season to 120. And so that's a doubling of extreme rainfall. And so a third of all rainfall is now falling as extreme events in this region of the world. So again, we have this data set. We can ask a little bit more questions. So, what happened to these storms? Were there more of these? Were they larger? Were they rainier? How did they change? And so here is a somewhat busy figure, but we'll go through it. And what I'm showing here is the count of when we saw here in black these large storms, so all the mesoscale convective systems. And in the bluish here color, we see the just the count of these towers that bring most of the intense rainfall. These red dots here are a way of telling when the time series seems to be changing behavior. And what they, so statistically, what these dots tell us is we don't know exactly when, but sometime around the 2000s, something has happened so that before this count was going up straight, as increasing, and then it kind of leveled off. And the same thing happened for the most extreme rainfall and convection. It went up for a while, and then it seems to have leveled off. And we have two different data sets, and they agree. So the storm counts has stopped increasing in the early 2000s, and that followed from trends in the regional wind shear. So that mechanism of organization of convection has changed. First, it was getting stronger and stronger and organizing the system more and more, and then it stopped increasing, and so the storms don't get as organized anymore. But at the same time, when we look at how much rainfall has been falling per unit of cloudiness, what we see is that it was steady for a while, but then it's been increasing. So for the same amount of upward motion, now we're getting more rainfall. And how is that? Well, we had these two ingredients, right? The lift and the moisture. And so what's happening is that the lift is not growing anymore because there's no shear to organize it as much. But the rainfall is growing more and more intense because we have more and more water vapor from warming. So why does this research matter for the US? Well, for one thing, what starts in the tropics does not stay in the tropics. And in particular, these storms often behave as seeds for tropical cyclones. So we study what's going on in Africa, but that tells us whether we're going to get a tropical cyclone hitting Florida a few days later. Also, we learn a lot from looking at these places because we can understand a whole monsoon system. Well, we have our own monsoon system in North America. We can translate this understanding. Same for organized convection. We have severe storms in the US, of course. We can understand things more. And also, the changes in rainfall that we saw in the Sahel are some of the largest in the record. And so this is a good benchmark for understanding if our climate models are getting things right, and if they can then give us reliable projection for the future. And so here's my final thought here. Research like this on rainfall and what has happened to rainfall and what will happen to rainfall has been the joy and privilege of my professional life. All of it has been funded by the federal government, NSF, NOAA, NASA, as well as a lot of community resources provided by NCAR. I haven't shown any modeling work here, but I do a lot of that. And my students and my postdocs have been using the NCAR model for decades. And so, I came here because of the research environment in the US and how bright it's shown back in the 90s. And I don't want to see it going away. So continued support for science, scientific independence of NASA, NSF, and a healthy NCAR are an absolute necessity for the weather and climate enterprise and the well-being of all of us in the US. So thanks for your attention.
Thank you so much for such a great talk. Earlier in your talk, somebody mentioned a beautiful visual that you had in your talk. I'm not sure which one they were referring to.
Oh, I'm sure I know which one. It's this one.
Yeah, I don't know.
I would imagine. This is such a beautiful image of these storms.
Yeah. So they said thank you, by the way, for showing the figure, the image that you have there. So what Dog 75 wants to know, how did we figure out that the big clouds have a small cold cloud within them?
Oh, because of radar. So we can see the structure of these storms with great details because of we've been looking at them with radars for a long time, starting out in the U.S., in particular in the Great Plains, where severe storms are obviously they're very important and they do a lot of damage, and so we can see the size of the hydrometer, so the water, the ice, and distinguish the structure of these storms from the different reflectivity in the radar data. And so we know you can see convective cores popping in and out and then decaying, and the water and ice that is brought up by these towers then expands in this anvil structure, and it keeps precipitating, but with less intensity. So you get a whole lot of rain from this anvil region, but it's a milder rain that the really intense shower that you get within the convective core. But if these things organize, they can the individual element is born, grows, and dies, but the system persists for a while.
Mm-hmm. I think for me, as somebody who works mostly with atmospheric models, it's always important to kind of take things to remember, like where we're getting this information from and all the data from. So I thought that was a really good question and really kind of connects the physical instrumentation and those processes that tell us more about how the atmosphere looks like. So.
Yeah. And I should say, we started out with the ground radar, but now we have radars in space, which is kind of amazing. So for most of the satellite data that we have is passive. So we just look, the Earth is giving us radiation, and we look at it and we try to interpret it, but we don't send anything down. Radars are different. And so it's only been since 1998 that we have radars in space. So first it was TRIM, now is GPM, and so we can now look at these systems even in places where we don't have the ground observation. So and so we can look over the ocean, we can look over underserved places. It's not obviously there continuously, it just goes by every so often, but we've learned a whole lot about this system since we had TRIM in space. And of course, that was also with the support of the federal government.
Right. Okay. With that, thank you so much for this great talk, and I hope you all enjoyed learning about storms and this great presentation. Yeah. Thank you so much. Okay, so we've reached hour 16 of the Weather and Climate live stream. Where I am in Salt Lake City, it is still dark outside. We have only 34 more hours to go. My name is Vanessa Sun. I'm a PhD student in atmospheric sciences, and I research improving air quality. I'm so excited to be here with you all, learning about the work of some great weather and climate scientists. This hour of weather and climate science is going to be pretty fantastic. We have really great speakers, and I'm really excited to see all the different talks that they're going to give. But first, we want to remind you why we're here on your screens. So the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecasts, the first computer models of the climate impacts of carbon pollution. Alongside these computational tools, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. And you've seen some talks where people have data from all these different sources. The resulting forecasting and observation system is a true scientific miracle. This miracle was made possible by decades of US taxpayer funding and by a merit-based system in which scientists have judged the best projects to receive funding. But now all of this is at risk. The administration is changing the rules so that political appointees, not peer review, determines who gets funding. Political interests are already being used to justify the planned dismantling of the National Center for Atmospheric Research, or NCAR, in Boulder, Colorado. And the administration's proposed budget for the fiscal year 27, now being considered by Congress, would gut weather and climate research across the federal government and end foundational programs for young scientists. I've personally used some NCAR climate model data in my master's thesis, and I had the opportunity to visit NCAR before I moved across the country to my new PhD program. And there I met quite a few scientists that were really encouraging of my research career, and it really set me up to feel confident going into my PhD. At the time, they told me about some programs that I could participate in as a graduate student, and NCAR is still attempting to run some of these formative programs for scientists like me and others that you are seeing across this stream. NCAR is a world-renowned laboratory which engages in weather and climate science research in this country and their work is known around the world, and it heavily depends on crucial federal funding. But because NCAR's climate research does not align with the administration's political priorities, it is at risk for being defunded. But it doesn't have to be this way. If you like what you see here, then we ask you to please use the link below to contact your representatives and tell them to defend weather and climate science, to fully fund NOAA, NASA, and the NSF, and other agencies to make this work possible, and to protect NCAR. The House and Senate are making these decisions right now. Now is the time to make your voice heard. So with that, our next speaker will be Paul Summers, who is speaking about ice and glaciers, which is quite a bit different from our previous weather-focused talk. As a reminder, all of our speakers' views are their own, and they are not representing their employers or any other institution. Make sure to leave any questions that you have during the talk in the chat, and we'll get to one or two in the end. And with that, okay, tell us about your work, Paul, and we're all excited to hear about it.
Thanks so much, Vanessa. The sun's just coming up here on the East Coast, so I hope it gets to you soon. But thank you, everyone, for having me here today. I'm excited to share some of my research with you, which will focus on the importance of ice melange in glacier fjord systems. And all of this work has been funded through support by the NSF, and all of the data products that I work with similarly come from federal programs like NASA and NCAR. So it's important to keep all of this going. And so to give some motivation for why you should care about the cold parts of the world, we'll bring you up to Greenland, where we find most of ice melange today. And importantly, global mean sea level is on the rise. And if we look at projections moving forwards to the end of the century, this is a plot from the Intergovernmental Panel on Climate Change. Sea levels are projected to rise up to a full meter by the end of the century. And of course, there's some spread depending on our emissions pathway and some model uncertainty there. But the overall sort of direction is clear that sea levels are rising, and they are rising rapidly. And importantly, 20% of rise in sea level today is coming from melting of the Greenland ice sheet. And about half of this loss from Greenland comes from surface melt that turns into water and then runs off the edge of the ice sheet. But the other half of this mass loss is actually solid ice being discharged from the coastal margin of Greenland. And so to visualize how this ice makes its way to the coast, on the left here, I've plotted a plot of surface velocity of the ice across the entire ice sheet, where the cooler colors are slow-flowing ice. We see this largely in the interior, where ice is flowing anywhere from 1 to tens of meters per year, sort of the glacial pace that you might have in mind. But as we move towards the coast, we see these warmer colors, which correspond to much faster flow, flowing kilometers per year. And these are termed outlet glaciers, and are these narrow jet-like features that dominate the total mass flux of solid ice to the ocean around the coastal margin. And my work focuses in these regions, particularly in Greenland. Many of these outlet glaciers terminate in what's called a glacial fjord, which is a very narrow, deep, and long valley in the bedrock that's filled with the ocean. This is an image of a fjord on the right here, where the glacier is in the back. The open ocean, or the ocean, is filling the fjord. And we see trapped within this fjord, there's lots of icebergs that form when they break off of the glacier, and they can become jammed and packed with sea ice that forms when the ocean freezes, when the surface temperatures are well below freezing. And this large jam of pack ice and icebergs can create a very dense, jammed particle flow, which you can think of, which is called ice melange. And you can think of this a lot like a huge pile of Legos that's jammed in a hallway of your house. It's really easy to throw a Lego down the hall, but you can't really push the whole pile because they jam and bind up against each other. And it's this immense resistive stress of melange, which is why it is so important for understanding glacier dynamics. And so to get a sense of scale for how large these melange flows can actually be, we're now going to go to Western Greenland. We're looking at Jakobshavn, the world's fastest flowing glacier. And we can see the ice sheet is on the right, sort of the brightest white blown out colors in this image. And the open ocean is on the far left. It's the darkest blacks we can see on the left. And there's a bunch of exposed land as the dark browns, but this sort of lightest, almost blue, is the Mélange itself. You can see some of the largest icebergs you can actually see individually in this satellite image. But the Mélange is very extensive and runs the entire length of the fjord, well over 100 kilometers long. And to get a sense of scale for the calving process and how it interacts with the Mélange itself, we'll zoom into a time-lapse image right here on the calving front of the glacier itself. And so now we're inside that red box looking at the calving front. The ice sheet and the glacier is on the right. It's this slightly higher region that we can see. And the Mélange is over here on the left. All of this ice is actually floating, and this ice is sitting on the bedrock beneath the ocean. And so this will be a time lapse where 1 second is a minute of real time. And we'll see a calving event, but I'll just let it play. You can sort of see the regions as they interact with each other. Cool. So to get a sense of scale for just how large these processes are, because there's not a lot to give you a sense of scale in this image, but those largest icebergs that broke off are well over 1 kilometer long, almost a mile in size. And that's just individual particles within this large flow. And these cliffs over here on the right are well over 100 meters tall. So it's really an immense scale of both the glaciers, but also the Mélange itself. And it's the great size and extent of this Mélange, which is why we study it. It's one of the only natural phenomena that we see that has a large enough resistive stress to actually push back on the glacier itself and influence the calving rates. And so calving rates of glaciers is a complex problem that we as scientists are still trying to figure out exactly how fast ice will calve off. But ice Mélange has been demonstrated to directly control these calving rates. And that analysis, one of the papers that sort of helped move this forward was by Olivia Mang in 2025. And this used remote satellite data to make observations at many locations across the entirety of Greenland and found a strong correlation between Mélange elevation or Mélange thickness, which is shown in blue here, with major calving events, which are the highlighted red lines here. And so the main takeaway from this image is that whenever the Mélange gets thinner, we see a reduction in the elevation of the Mélange that tends to correlate with large calving events, which lead to the sort of terminus of the glacier front migrating backwards. So as we see thinner Mélanges, we see more calving, more glacial retreat, and more mass loss. And so this is the strong coupling between why the dynamics of Mélange and what's setting Mélange thickness is very important to understanding the future dynamics of calving and rates of mass loss across Greenland. But of course, the Mélange is also floating in the ocean. And so it's this strong coupling mechanism between ocean conditions and the glacier itself. And so as the ice Mélange floats in the ocean, it's susceptible to warm, deep water from the open ocean coming up the fjord, driving more melting of those icebergs within the Mélange. And as those icebergs melt, they produce large amounts of fresh water. This fresh water is buoyant and drives more circulation within the fjord. And modeling studies that have been done comparing both fjord systems with and without icebergs show that as we include icebergs and ice Mélange, this extra freshwater buoyancy and extra meltwater actually drives an increase in overall circulation within the fjord. And this means that more warm water moves up the fjord, bringing more heat to the glacier face, which can lead to more mass loss and more melting from the glacier itself. And so the overall story that I hope to clarify to all of you here today is that the net impact of Mélange on glacial fjords is still not entirely clear. There's a variety of feedback mechanisms, and it's not clear in which regimes which one will dominate. So there's some processes that can lead to more stability and a reduction of mass loss. So as we build up larger Mélanges, there's more back stress on the glacier, and this reduces calving and stabilizes the glacier in its location. In contrast to that, as we build up more Mélange, we also see more meltwater from the Mélange. That leads to increased circulation throughout the fjord and brings more heat up the fjord to the glacier front, which can lead to more submarine melting, which can ultimately destabilize the glacier and lead to more glacial retreat. So these feedbacks are exactly what my research and my project has been focused on, and building a coupled model that directly couples an ice sheet model, an ocean model, and a melange model. But I guess, or further importantly, as much uncertainty as we have in the current moment, as insofar as how much melange is influencing ocean and glacier dynamics, it's an even more open question of what will happen in the future as we continue to see changing ocean conditions and changing conditions on the Greenland ice sheet itself, where we expect there to be more surface melt, more subglacial discharge, and potentially warmer waters in the open ocean. And so our work continues. This is some of the modeling work that I have done, where we have this ocean model, again, coupled with our melange model running up here. So this work continues. It's funded by the NSF, and we continue to need detailed observations from both from fieldwork and satellite missions through NASA. And so it's important to have continued funding through NSF to support all of the great work that's done throughout the cryosphere to better understand the future of sea level in both the United States, but also across the entire world. And with that, I'd be happy to take any questions.
Thank you so much for such a great talk. While you were doing your presentation, there was a lot of comments that were coming in, and I think everyone's really excited to have a glacier-oriented talk. I just wanted to let you know. Some people were mentioning that it looked like some pieces are flipping over, and we're marveling at how big I suppose the glaciers were. All right, so in terms of questions, let's see. I'm trying to see which one I think is maybe the best question for you. Okay, I guess, does the subglacial discharge also increase the glacier breakoff since it's making holes in the ice?
Yeah, so it does in an indirect way. So the subglacial discharge, it puts fresh water, comes in at the bottom of the glacier, where it mixes with the sort of warmest and saltiest ocean water. And so that drives this intense upwelling of warm water. And as this graphic shows, that leads to a lot of melting at the base of the glacier. And that can lead to what's called undercutting, where the bottom is more melted in than the top. And this can become unstable and can create some of that sort of like calving mechanism, whereas the front gets too buoyant, it'll break off. And so there are many pathways where subglacial discharge and this undercutting can directly lead to an increase in calving and increased mass loss, both directly through melting, but most of the mass is lost through calving and breaking off, because ice can break off a lot faster than it can melt. Although the melting is quite extreme at some of these locations. We can see melt rates of up to meters per day in some of these locations. That's a massive amount of ice that's melting directly at the glacier face.
So I want to know if you know it's called calving.
Sorry, can you say that one more time?
Yeah, so speaking of calving, someone wants to know if you know why we call it calving, like the terminology.
It's a really good question. I am not sure why we call it calving.
Okay.
We certainly don't call the icebergs calves. But yeah, I don't know. I should look that up. I've never thought about it too much.
It might be some kind of process, like some agricultural or like specific process that we just don't know about the verb.
Yeah, I don't know. I'm curious what other languages use for it, but I've only ever heard it discussed in English. And yeah, calving seems to be our favorite.
Someone else wants to know if current climate models include icebergs or if they're missing.
Yeah, this is a great question. So most large-scale ocean models do not include icebergs, and it's actually a big issue that they're trying to figure out. And so the large-scale Southern Ocean models tend to run a little warm compared to observations, and a lot of this mismatch is thought to be because of iceberg melt, because you can move a lot of icebergs out into the open ocean. They both release a lot of fresh water, but they also consume a lot of heat. But it's difficult to include the effects of these. They look quite large in these images. They're up to a mile big, but a lot of our large-scale climate models have resolutions that are like tens of miles across, even bigger than that. And it's hard to account for these very small subgrid features. So some work has been done recently, which they call freshwater hosing, where we just add freshwater to the surface layer. And that has shown that it does influence the results in some way and can close the gap to observations a little bit. But of course, icebergs have a finite depth. They're not just at the surface. And so it's important to include those. And there's lots of work in the community to try and better include the effects of these icebergs as they drift in the open ocean. So not yet, but progress is being made towards it, and it's believed to be an important part of capturing the overall dynamics of the ocean and the larger climate system.
That's a really great explanation. I think that was really, I don't know, it was insightful to kind of have that information for those who want to know more about how to bridge the like climate modeling with the physical observations and having that be accurate for the kind of work that you're interested in.
Mm-hmm.
So on the calving process, they want to start a petition to call ice sheets cows.
That could be fun. We'll see.
Yeah, they're really engaging in the conversation. Okay, so I think we can do one more. Does the ice from the Mélange come from pieces that break off the glacier or the frozen sea surface, or both?
Mm-hmm. Both. Yeah, so it's a mixture of both of them. And depending on the time of year, the main source can switch. So in the summer, when we see more calving coming from, I guess, the Cow Glacier, as we're now calling it, that's the dominant mass source. In the winter, we see less calving, but we see more sea ice formation as surface temperatures are well below freezing. As you saw in the video, the actual dynamics within the Mélange are very chaotic. There's a lot of overturning and fracturing and mixing. So I think so it's really hard to make observations within the Mélange. So there's not a lot of sort of taking a big bucket of Mélange and surveying what it's all made out of. But from the sort of mass source analysis, it's coming from both. It's mostly new ice is mostly coming from sea ice in the winter, and new ice is mostly coming from calving in the summer. But and I guess in Greenlandic, I don't know how to pronounce the word, but the word they have for Mélange is more of this hybrid that can mean both sea ice or icebergs trapped in sea ice, sort of a spectrum between the two. And so it is better to sort of think of them as one continuous spectrum from pure sea ice to pure icebergs. And Mélange is somewhere in the middle.
That someone pointed out that whales also have calves. So they could be whales as well. I just thought that was fun, and lots of people chimed in to say that they liked that terminology as well. And whales can also be cows in their hearts. So I thought that was just very fun moment on the stream. Well, I can see that it's getting lighter on my in the sky right next to me. So thank you so much for your talk, Paul. I think I enjoyed it, and so did the audience. Thank you so much for telling us about your work.
Thank you.
Thank you. All right. Thank you all for joining us in hour 16 of the Weather and Climate live stream. We've got only a bit more than 33 and a half hours to go. Hope you've been enjoying these talks so far. My name is Vanessa Sun. I'm a PhD student in atmospheric sciences, and I research improving air quality. So let's start the next session with reminding you why we're here doing this stream and being on your screens. The United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecasts, the first computer models of the climate impacts of carbon pollution. Alongside these computational tools, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle. This miracle was made possible by decades of US taxpayer funding and by a merit-based system in which scientists have judged the best projects to receive funding. But now all of this is at risk. The administration is changing the rules so that political appointees, not peer review, determine who gets funding. Political interests are already being used to justify the planned dismantling of the National Center for Atmospheric Research, or NCAR, in Boulder, Colorado, and the administration's proposed budget for the 2027 fiscal year, now being considered by Congress, would gut weather and climate research across the federal government and end foundational programs for young scientists. I've personally used some NCAR climate model data in my master's thesis, and I had the opportunity to visit NCAR before I moved across the country to my current PhD program. And there I met some scientists that were really encouraging of my research career, and it really set me up to feel confident going into my PhD. They told me about numerous programs that I could participate in as a graduate student, and NCAR is still attempting to run some of these formative programs for scientists like me and others that you're seeing on this stream. But it doesn't have to be this way. If you like what you see here throughout the stream, then we ask you to please use the link to contact your representatives and tell them to defend weather and climate science, to fully fund NOAA, NASA, the NSF, and the other agencies that make this work possible, and to protect the National Center for Atmospheric Research. The House and Senate are making these decisions right now. Now is the time to make your voice heard. Our next speaker will be Christina McCluskey with another ice-focused talk, and particularly special because they're also from NCAR. And as a reminder, all of the speakers' views are their own, and they are not representing their employers or any other institutions. Make sure to leave any questions that you have in the chat throughout the talk. And with that, we're eager to hear about your work, Christina, so tell us about it.
Wonderful. Can you hear me okay?
Yes.
Great. Thank you so much. And I just want to say thank you to all the organizers. It's been so well organized. I'm so impressed. And thank you for doing this. And thank you to everybody who's chiming in and listening along. So today's talk, the title is Ice, Ice, Maybe. And I'll be talking a little bit about leveraging the Southern Ocean and the clouds over that region as a natural laboratory. My main work is looking at cloud physics, and in particular, how particles in the atmosphere affect clouds. And so we'll dive into a little bit of that. And then I have a few results I'm looking to share that have already been published. This is a picture I took on the Southern Ocean while I was on the RV Investigator. So this was during my PhD studies. And we were located just south of Australia. I mean, I saw multiple albatross in the wild, which was a pretty spectacular experience. The title of his talk, Ice, Ice, Maybe, is inspired by Vanilla Ice. The first lyric of the song is, "All right, stop, collaborate, and listen." And I just think this is such a perfect example or way of thinking about the science that we're doing, which is extremely collaborative. I work a lot on thinking about how to take observations and make use of those to inform our physical understanding, and then also improve that representation in our models. And so there's a lot of collaboration between observationalists and people who are focused more on theory, people who are focused more on laboratory studies, and of course, people in modeling across different scales. And so I just want to highlight that the work that we do is so, so important, but it's also so reliant on each other. And that's one of the reasons why I'm here today to talk about how we can hopefully avoid catastrophic cuts to our funding. Okay, so really quick about funding, or sorry, not about funding, about clouds. I have some time lapse here and a couple videos showing different types of clouds. So on the left, we have just right down the road from my house, this multi-layered cloud system, absolutely beautiful. This was taken in January. I was driving down the river road in Moab, and we witnessed these clouds forming right on the edge of this river valley. And then I got to participate in another field campaign. This is flying in the Canadian Convair 580 aircraft, looking at convective storms in Houston. And the point of this is really to show, one, that clouds are amazing and they're beautiful, but two, that clouds really are formed in different ways. They're very diverse depending on where you are, when you are, and what all is going on in this sort of broader field. So, for example, in Houston, Texas here, there's clearly a whole lot of convection. This was during summertime, so a lot of heating at the surface driving this convection. And so I particularly look at how particles in the atmosphere will influence clouds. And so what I mean by that is particles serve as seeds for clouds. In liquid clouds, where we only have liquid cloud droplets, particles serve as cloud condensation nuclei, where basically water isn't very good at getting together into a pure liquid cloud droplet. We need very high relative humidities to form a pure liquid cloud droplet. But since we have materials in the atmosphere, that those materials have what's called water affinity, and water can collect onto the surfaces and form these liquid cloud droplets. So these are liquid phase clouds. So these are typically warmer than 0 degrees Celsius. But we know that there's much more cooler temperatures in the atmosphere. And so we have ice clouds, particularly at very high levels of the atmosphere. And this is formed using homogeneous freezing, which forms these ice crystals. But then in the space in between, at that negative 40 degrees Celsius, that's that homogeneous freezing. But in the space in between, we have mixed phase clouds. And this is where particles can still serve as cloud condensation nuclei and form these supercooled liquid cloud droplets. But there are also these ice nucleating particles, which have unique features on its surface that mimic the shape of ice that then allow ice to form in these mixed phase temperatures. And so we have multiple modes of ice formation in the atmosphere that we study. In particular, I'll be talking about this immersion freezing of ice where we have an ice nucleating particle that forms a cloud droplet. And then within that cloud droplet, once that cloud droplet reaches a certain temperature, it forms ice. And just to show super cool liquid, you could do this with many different examples, but here's an example of a water bottle I left in my car overnight in February here in Colorado. It's just to show that water has this ability to be super cooled. You may have witnessed something similar if you put a water bottle or a soda can in the freezer. And so you can see this is liquid, but it's super cooled. As soon as I shake it and irritate it and help, again, mimic that formation of ice, you can see the whole bottle glaciate. So this is ice nucleation. This is what we're trying to study. The reason why this is important is because different materials have different ice nucleation abilities. So here, this is a really nice map from NASA that highlights the different types of particles around the world. It's a little simplified in that it has, let's see, there we go. It has 4 categories of aerosol particles. There are more than 4 categories, but it's a nice way of demonstrating these different types of aerosol sources. So we, of course, see dust from our deserts. We see pollution coming from our main, especially the northern hemisphere. We see smoke particles coming from the regions where we expect to see a lot of biomass burning. And then, of course, sea spray is coming from the ocean. And one of the reasons why we really like studying in the Southern Ocean is because we have a pretty simplified aerosol field compared to, let's say, the Arctic. And so what's just simply shown in this picture here is that most of the particles that are present over the Southern Ocean are these sea spray particles. We do, as you can see, have occasionally what's called long-range transport, where emissions, let's see over here over South America, could end up in the Southern Ocean region. And so that's actually a really nice way of looking at what we call perturbation experiments, where we can say, okay, we have some influence from a unique source and what's going different in our clouds. The other thing that's really valuable about the Southern Ocean is we have a lot of cloud there. This is a video from a field campaign called Socrates we completed on the NSF G5 aircraft, which is a facility maintained at NCAR. And you can see here that there's a massive cloud layer. And in fact, this is known in New Zealand as the long cloud. And in this cloud layer, we can see this can stick around for many, many days. And what's really spectacular about these clouds is they are optically thick. And what that means is our satellites are actually really limited in our ability to penetrate all the way through this cloud layer. And so we really need our aircraft and ship-based measurements to make total observations of these clouds. Otherwise, we only get a view of the top. And so this field campaign went out to the Southern Ocean to measure the different properties of clouds. And so over the Southern Ocean, we have 80% cloud cover on average throughout the year. And also these clouds are what's called supercooled liquid. And so we expect to have a lot of the processes we're interested in ice nucleation active in this region. And so that's another argument for studying the Southern Ocean. I wanted to give an example of a type of instrument we use to measure ice nucleating particles because it's super cool. And this is the CSU Continuous Flow Diffusion Chamber. This is an instrument I used during my PhD work. And this is just a schematic showing the setup of this instrument, which has 2 cylindrical columns. Those 2 cylindrical columns are ice covered and also temperature controlled using refrigeration. And so these particles will pull in using an inlet, or you can think of it as a straw to suck in particles from the atmosphere. And those particles enter the chamber. And since these are ice coated and at very cold temperatures, we can form a mixed phase cloud. So this is something we deploy on aircraft, on ships. And so we're literally making a cloud in these platforms. It's very, very cool. Okay, so and the mixed phase cloud then forms these super cool liquid cloud droplets using as those particles are exposed to that supersaturation. And then if there's an ice nucleating particle present, then it will form these ice crystals. Those ice crystals tend to be very big. And we also, in this last third part of the chamber, will take the two temperatures of the walls and set them at the same temperature so that the particles are then exposed to water subsaturation. So the droplets will evaporate. But the ice crystals, the saturation with respect to ice remains greater than 1 or 1. And so then the ice crystals can carry on through the chamber. Ultimately, we have what's called an optical particle counter at the end of the instrument at the very bottom. And here you can see an example of the output of that data where you have increasing size and counts here. And so we can detect those ice crystals using that optical particle counter. And so I wanted to show an example of some of the data we observed. This is a data set I'm particularly proud of. It's the first Southern Ocean INP measurements collected during my PhD work a few years ago now. But you can see that IMP number concentrations over the Southern Ocean range. You can see this is a log scale. So they range, let's say, at -25 between 10 and 100 per cubic meter. And we compare this then to other ice nucleation particle sources using this metric called the ice nucleation site density, or NS, which is where we just take that number concentration and we normalize it by the total aerosol surface area. And this allows us to have this NS parameter, which then allows us to form what we call parameterizations. And so this was then this really helped identify that over the Southern Ocean, we have a very distinct population of ice nucleating particles. So here is showing that ice nucleation site density for some other marine IMP measurements. And this is in comparison to a dust type. So you can see that in general, the mineral or the marine IMPs of the Southern Ocean are much less ice nucleation active compared to dust particles. And so this is an important feature that we are now we are currently putting into our models to try to improve those. And one of the things that we've done, and I please stop me when I've exceeded time. So one of the things that we are doing is now thinking about how can we represent these in our climate models. And so on the left is an example of where we take our model and we run the model using different aerosol types in the model and look at, as a function of height, what types of particles are contributing to the IMP number concentration. And so on this example here, this is over the Southern Ocean. We see that over the lower parts of the atmosphere, so below 2 kilometers, we mostly see marine IMPs, whereas at aloft and at these higher altitudes, we see these dust IMP. And this is what motivated, this was a simulation. So this motivated us to go back to the Southern Ocean, following on that 2018 study, to go down for that Socrates campaign. And during that, we were able to collect samples of these ice nucleating particles and investigate their composition. And what we found was that, in fact, when we are flying above the boundary layer, above these clouds, we do see dust particles present in our IMP population. So this tells us that we really have to consider both of these particle types. Okay. And then I want to also highlight one of the things that we are able to do with these observational campaigns is what we call observational closure studies. And so this is where we take, in this case, a parameterization for predicting IMP associated with these marine aerosol. And we have observations of surface area, which feeds into this parameterization. And we have observations of these ice nucleating particles. And so now we can test that parameterization on an independent data set to see if that parameterization is valid. And so what's shown here are different ways of estimating those IMP number concentrations with different types of surface area measurements. This is all in interest of trying to decide what is the best parameterization for predicting these ice nucleating particles. And so right now what we are doing is we're continuing to develop the model and think about exactly how well we have to predict these particles, because the clouds have varying levels of sensitivity to these. And so from here, we're still very active in this work, thinking about not only additional observations, but then how we are linking this to the cloud physics. And that's my current work. And this is a picture of me in 2016 on the RV Investigator. And so I'm happy to take any questions at all. This was a very, very, very brief look into some of the work we've done over the Southern Ocean. Thank you so much.
All right, great talk. I hope you all enjoyed it. We have a couple questions in chat. I think we can run maybe the two of them that were asked. So Fish's Failure Sun 5114 wanted to know more about the materials that the rain droplets are gathering around. I know you mentioned a couple different parts throughout your presentation, but if you want to emphasize like what might be the most important or the most relevant, I guess, for what you're studying, yeah.
Yeah, okay, so for cloud condensation nuclei, that's the ones that form the cloud droplets. Those particles are present from various sources, and the way we describe those particles is using a term called hygroscopicity, and that hygroscopicity is dependent on what materials are within that droplet, so are within that particle. And so, for example, if you have a biomass burning particle that's like a sort of organic glob versus a sea salt particle, the sea salt particle will be much more hydrophilic, and so it will be more likely to form that cloud droplet if they are both exposed to the same environment. And so that's one question or one answer. In terms of the ice nucleating particles, these particles have varying properties. So actually, the person who's doing the walk is his name's Sil. They actually mentioned Pseudomonas syringae, which is a bacteria that can be released into the atmosphere and serve as an ice nucleating particle. So that's a biological source. We also know that soils and organic soils can serve as ice nucleating particles. In the ocean, and this was the big part of my PhD work, in the ocean, we've often observed diatoms and bacteria being emitted as part of the sea spray, and those are ice nucleation active. But then we also have this other molecular type, which is like fatty acids, carbohydrates, those sorts of things that are byproducts of biological activity in the ocean. And when those particles are emitted into the atmosphere, that's what we find as the main INP active site. And so hopefully that's a good overview of our thoughts there.
Mm-hmm. Okay, one other question from WhatDog75. Is this ice nucleation detection done high in the sky, like on planes? And they might have missed that part.
That's okay. So the instrument we had, we would definitely take it on aircraft, pretty much anything that would take us. So the ship here, that was the first time we put it on a ship, but it has since been on more ships. And then we also take it on the various research aircraft we have. And it's something that it's one of many methods for measuring ice nucleating particles. We also have another method that's a little more straightforward, or I guess it's just a little simpler. It has you get different types of data out of it, but it's a filter-based measurement where we can collect particles onto a filter, bring them back into the lab and analyze those. And those are really nice for, when you're really remote or, people are trying to look at putting those on balloons and tethered balloons and things like that. So it's very much an evolving area.
Mm-hmm. Just a comment that somebody mentioned that I believe I'm falling in love with the Southern Ocean through these talks. So you're talking balloons.
Yeah.
Thank you so much for such a great talk, Christina.
Thank you so much for all you're doing. Yeah, thank you.
Thank you. All right, so it's really starting to lighten up on my sky. Thank you all for joining us in hour 16 of the Weather and Climate live stream. We've got around 33 and a half more hours to go. Hope you've been enjoying these talks thus far. My name is Vanessa Sun. I'm a PhD student in atmospheric sciences, and I research improving air quality. This is going to be the last talk that I'm hosting for before I go take a nap and do my own PhD research meeting that I have later today. So let's start the next session with reminding you why you're here, looking at the stream, and why we're here on your screens as well. The United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecasts, the first computer models of the climate impacts of carbon pollution. Alongside these computational tools, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific miracle. This miracle was made possible by decades of U.S. taxpayer funding and by a merit-based system in which scientists have judged the best projects to receive funding. The administration is threatening to cut the National Science Foundation and NASA's Earth Science budgets in half. They're looking to eliminate the National Oceanographic and Atmospheric Administration's research arm and slash programs for training the next generation of young scientists. I've personally participated in NSF federally funded research programs in the past and organized conferences to bring young researchers in such crucial research fields together. To think that such programs are at risk is quite devastating on a personal and professional level. Past the impacts for me, these cuts hurt all Americans. Weather stations are so short-staffed that we are losing our observational coverage, worsening our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk. It doesn't have to be this way. If you like what you see here throughout this live stream, then we ask you to please use the link below to contact your representatives and tell them to defend weather and climate science, to fully fund NOAA, NASA, the NSF, and the other agencies that make this work possible, and to protect NCAR. The House and Senate are making these decisions right now. Now is the time to make your voice heard. Our next speaker will be taking us back in an atmospheric science direction. As a reminder, all of our speakers' views are their own and they are not representing their employers or any other institution. And make sure to leave any questions that you have in the chat while the talk is going on. And we'll have time for 1 or 2 questions at the end. So let's welcome Brian Mapes. I'm not sure, he might be having a momentary technical issue. Oh, I think it's working. Let's see. This label says some dude. It's very funny. I don't hear Brian on my end, so my assumption is the rest of you are not hearing him either. Oh, I see him now. Okay. Yeah. I'm starting to hear him. Okay, great. Hi, Brian. I think it's going through.
Okay, good.
Yeah.
All right, ready to roll. Good. Thank you all for running this and for, it's a nice opportunity to stash a talk on the web for later, as well as, talk the early birds through a thing. This will be a brain puzzle for you, I think, in the early morning. But these are the things I'm thinking about. I'm trying to inject a sort of an evolutionary sensibility into the problem of cloud patterns, which otherwise is just descriptive statistics that are too big. And so that's my project, I guess. The reason this connects to predictability and, save our forecasts and stuff is that down here in the Amazon, for instance, reality is that a day's worth of rain is lumpy on the 1,000-kilometer scale. But when you just try to run a model that has a high resolution, you don't get those 1,000-kilometer lumps. So something's going on that, makes for, bad forecasts for almost everybody living there. Because I don't know, some lump formation processes aren't there. Here's an example, I guess, of one day. In the morning it starts out all sort of random, and then these lumps kind of gather into a big rain area. But meanwhile, that's competing against all the other individual lumps trying to pop up everywhere. So the whole thing it's really an ecological problem, I guess, in a sense. So the way I'm trying to view it that way, probability of patterns is essentially infinite, but we can work with that with our infinite improbability drive. So one thing I like to start people with is check your brain. What's your Drake equation prior? In other words, what do you think is the probability that other radio-inventing life forms will be heard or detected by humans on Earth? Some people are easily dazzled by the largeness of the universe. Oh my gosh, there's 10 to the 10th stars, 10 to the 10th galaxies. That's just, 10 to the many, many stars. Surely somebody else has come up with possibly even me, or at least intelligent life. what vast numbers those are. But the inverse of that is how unlikely we are or life is. And that is, for instance, the genetic code is a 10 to the minus 84 chance that the one and only genetic code would be what it is. So, you know, it's an interesting puzzle, I guess. You know, and what this shows you is that the combinatorics of things is much vaster than, you know, how big is the universe. So we just have to play in these vast spaces. And when we play chess, we're playing in a game of 10 to the 123rd possible games. Go games, 10 to the 360th. We have no words for these size numbers. And, you know, random monkeys, no, we'll never type Hamlet. Don't wait up. Don't hold your breath. So therefore, says, well, you know, maybe in a quick thought, oh, therefore God exists and everything's made just so. But, you know, scientists, I guess maybe we doubt that. Might combinatorics hold the key to its own lock? It's a lock, but also a key. And that is through iterated selection. If you always take the better of the better of the better, far from invoking anything called an optimum, which is a chimera, you know, a falsity, you know, nature finds a way. So let's play with paradigms for pumping our intuitions about this. And let's start with a countable problem where we can really almost, you know, grasp our way through it. So let's say we have a set of clouds here on a 4x4 periodic lattice. I've just repeated it, you know, tiled it 4 times over. So the yellow things are updrafts and the purples are the downdrafts or subsidence for mass continuity. And the little arrows are how the wind connects the circulation. They flow into the updrafts. So for instance, there's 4 configurations of a 4x4 tile. How many are there? There are 43,680 just for 4x4 tiles of zeros and ones. So anyway, you know, combinatorics, boom. So maybe we don't care, you know, which way they're rotated. So maybe they, you know, we could beat it down a little bit, and we could beat it down especially well. Suppose we only care to distinguish these patterns by their domain averaged wind speed, you know, kinetic energy maybe. Turns out, you crank this out, there's 31 unique patterns in terms of their domain average wind speed. The multiplicity of each pattern, the number of distinct patterns that have the same mean wind, varies from 1 to 71 in these. And the largest wind speed, for instance, is configuration number 31 here. And that's 9 per 1,000 if you just randomly drop cells in a 4x4. So 9 per 1,000 are the maximum wind speed there. So there's a little space we can count, and you can tell, you know, this case is the most wind because all the updrafts are together and all the winds align into roaring into that updraft. Okay, so let's see about finding pathways in this kind of playground wilderness, you know, countable wilderness, through a kind of a non-random walk but with iterated probability. So let's make a probability for the updraft at time t+1. Here as a function of the state at time t. So we got 4 coefficients here. W is just persistence of W. If there's an updraft now, you'll have an updraft. R is a random noise, you know, just some random numbers added to the probability. E expresses this protection from entrainment by 4 neighbors. So clouds are better when they have neighbors because they don't get dried out as much. And F expresses the wind speed dependent surface flow. You get a windy place, the heat comes off the ocean, and maybe the next updraft will happen there. So we have a little toy model here with 4 terms. And let's walk through that just one by one for clarification here. So if we just have persistence, then wherever there's a cloud now, there's a cloud forever. Boom, right? And we can build a thing called a transition probability matrix, which is the configuration at time t, versus configuration at time t+1. And so obviously this is just ones up the diagonal. Whatever configuration you get, it just lasts forever. So that's a trivial case. Here's the noise case. You know, no history at all, just random noise every time. So no matter what the configuration was at time t t+1, it's just a random selection from all the possibilities. And there's this kind of barcode pattern, which is just the multiplicity of each value of the wind. Remember, there was 9 per 1,000 of configuration 31. It was a block. But there's 20, there's 71 sometimes patterns that are equivalent, that are more, we wouldn't have words for them. Okay, so that's getting in, but what really gets interesting for pattern evolution, patterns can change with time, is these terms E and F. So in this case, let's initialize with 4 random cells, iterate for n time steps, like 10's enough, and do that 1,000 times, and then just look at the statistics of it. So let's take just our entrainment protection from the neighbors, right? So probability of new cells at each time is places that had a lot of neighbors the previous time. And here's what happens with time, 10 time steps. Here's 100 ensemble members just trying to different random initial conditions. You can see they often end up in this light blue color here, which is number 13. And if you looked at that in transition matrix space, you'd find a big dot here at number 13. Once it hits number 13, it sticks at number 13, part of that diagonal matrix of thing just in itself. And then you see some other ones here. There's a few other attractors along the diagonal there. And maybe you can tell, I don't know about screen quality, there's something else. But number 13 here actually turns out to be an alternating pattern between two equivalent things, where in this one, the purple sites are all encircled by yellow. So the purple sites become yellow. And the yellow sites here are all encircled by purple, so they go back to purple. So this pattern just toggles back and forth like that, and that's state 13. So that's the neighbor. That's what the neighboring gets you. Now the interesting one maybe is this wind speed, because the wind speed is non-local. If you have a set of updrafts, the wind speed is a field that's connected, that connects them all. And so here's an interesting case. And what happens is you get all these multi-step pathways. A lot of them end up at state 31, don't they? They all end up at that block state 31, which we saw. So you can see state 31 here has this big thing on the diagonal. And there's a few other, there's another diagonal piece here that maybe gets, sometimes lasts a long time. And then there's off diagonal, pathways to 31 that end up kind of stuck at 31. And this was an interesting case because there's an attractor that's stable, but it's not very stable. It's brittle, because if you had 0.1% random noise to it, state 31 is no longer, it doesn't just go to yellow all the time now. Now it's going all kinds of colors and rarely settles down. Maybe sometimes it sticks in, turns out, number 30. You can see number 30 and still somewhat 31. They're still weak attractors. But look how many states lead to other states that aren't along the diagonal. So it's probably taken, paths. I don't know if they're periodic paths or they're chaotic paths. I mean, who knows, right? It's just already super complicated, and interestingly so. And what ChatGPT tells me is I need to think about this as a network. Instead of just T and T plus 1, you need to think about multiple time step paths. And so I got to study network analysis now. But anyway, that's more than I've done. But that's our little playground. But I want to just make it a little bigger, because the world is bigger. So let's talk about something that's bigger than we could possibly count. And this is inspired by that Amazon basin problem. Suppose we have 100 by 100 mesh of 10 kilometer points. That's like the size of the Amazon basin. And at each point, we have a cell or not every hour, right? So hourly, 10 kilometer, 100 by 100. We have about 10,000 to the 200th or 10 to the 203rd randomly possible configurations. This is like Go games, I guess. So, and almost all of those are just, we would just call them random because we don't have words for it. But they're distinct, but they're very high multiplicity of very random things. And how is a system going to find organization, lost in the flat plains of randomness that are, vaster than we can imagine? Maybe only if successive selection or pathways or trails, lead to the mountains of betterment. So there's just an example of how I measured from data. I just used satellite data here over the Amazon and just measured cells as cold spots in the infrared. And from a data set like that of cells related to other cells, you can build and you can compare this to other. Models don't necessarily do this right, so that's an interesting way to look at models. But you can just take all those cells and build this conditional frequency or conditional probability of a cell at a given point in this 1,000 kilometer square every 3 hours, given a cell at the origin. So you just take all those data, shift them to have a cell at the origin, and just count the frequency of cells around that. And what you see is that when you have a cell at the origin, you get a ring of enhanced probability of other cells, and inside that, a blue circle of reduced probability. You know, that early cell maybe made some shadows so the ground's not getting sunshine, or they made a cold pool, so the air's cold and not going to rise up. Anyway, who knows what the mechanism is, but it's frequency and probability. It stands alone. So we can lift that out and make a little kind of mathematical model of that, which is, an expanding ring of probability here. And I biased it toward the west just to give it some interest. So expanding ring of positive enhanced probability, biased to the west, and an expanding circle in the middle of reduced probability, and just for 5 hours. We only keep track of this for 5 hours, and then back to random beyond that in space and time. And here's what happens. First thing in the morning, it picks one out of the 10 to the 203rd states, but very, very quickly it discovers that conditional probability. Wherever you have a winner, it creates a beam of positive probability to the west, and those beams of positive probability can help create new cells, and then that beam aligns with the previous beam, and they align. The whole thing knows how to build highly organized systems really quite quickly. I made this a 24-hour kind of diurnal cycle, and so just within every day, things build up to these big lumps like that just from conditional probability. So that is that's kind of my bigger version of this game. And the improbability is infinite. I hope 10 to the 203rd counts as infinite for you. And back to our little intuition quiz. The universe is vast, but improbability is even more vast. But on the other hand, even with vast improbability, survivors surviving, conditional survival, iterated again and again, not that much, can just race to find amazing forms of organizations. For me, just learning all this stuff kind of pushes my prior, closer to 1. I used to be close to 0 because I thought I'm smart. I understand combinatorics, and any yokel can be dazzled by how large the universe is, like that Monty Python sketch. We have your liver then. But now I'm starting to think, things find a way. So anyway, that's just where I'm at mentally these days. A lot of this comes. I took my title, I suppose, from this lovely book by a famous chaos scientist who's in economics now, "The Wilderness of Bounded Rationality," which has a zero intelligence gate. Oh, let's assume the world is random because it's complicated, and a rationality gate. Oh, let's assume the world is perfect because things that will happen must have already happened. And somewhere in between is this wilderness of conditional bounded rationality with trails through it that lead to not to one optimum, but it's a wilderness. It's wonderful. Let's explore it. So here's our vision of convection: random plumes. No, totally infinitely efficient neutralizer of instability. Nope. What it really is cloud field developments, pond developments. So anyway, that's my new view of how convection works and why predictability is hard. And I'll just pitch my little art movie here about it, and anybody can scrape that link off the screen. So that is my talk. Thank you for your attention.
Okay, thank you so much. It was a really interesting talk and very different from a lot of the other talks. I hope that everybody enjoyed that part of the stream. Okay, so actually we have time for maybe one question. What is my life 6927 wants to know, what do we consider random noise?
To me, it means unconditional on the past. Random is something that doesn't come from the past. Doesn't come from patterns in the past. Yeah. Innovation, I guess, but dumb innovation. Cosmic rays striking your microchips.
Yeah, thank you so much, Brian, for your talk. And to point out that Andrew mentioned that Syl walked 50 miles last night, so that's a great update on how the walk portion of the live stream is going. And so with that, that concludes our previous session and group of talks. I'm off to take a nap, so taking over the hosting for the next time block is Haley Krim. I hope that you've all been enjoying the last couple hours of the stream and enjoy the talks. I'm definitely going to have to tune into a few after my nap, so thank you all for having me. I had a blast, and take it away, Haley.
All right, get some good rest. Hello, everyone. Good morning. It is 8:03 a.m. where I am in Cambridge, Massachusetts, and I'm super excited to be here and see you all. And I recognize good night, Fish. I recognize a lot of the names in the chat from yesterday. I was behind the scenes, kind of running this stream. So great to see you all again this morning. Before we get started with our next presentation, I just want to welcome you all to hour 17 of the live stream and say that, or just say a quick message about why we're here right now. So as we all know, as we've been hearing for the past 17 hours, the US has long been a world leader in climate and weather prediction, from developing the first computerized weather forecasts, the first models of climate impacts of carbon pollution, and alongside these computational tools, of course, we have an unparalleled network of observations from weather stations to satellites to planes to balloons, boats, and floats. Argo floats were going crazy in the chat yesterday. So all kinds of things monitoring weather and climate all around the world. And unfortunately, now all of this is at risk. So the administration currently is changing the rules so that political appointees, rather than peer review, determine who and what gets funded. Political interests are being used to justify the dismantling of NCAR, the National Center for Atmospheric Research in Boulder, Colorado, which powers much of the weather and climate science in this country and around the world. So we've already begun to see how these cuts hurt Americans and people all over the planet. Weather stations are so short-staffed right now that we're losing our observational coverage and it's worsening our forecasts. Laboratories are dedicated to understanding our climate's future are being closed or shrunk. I actually experienced this myself. I used to be a contractor in the NOAA Climate Program Office and am no longer there. So you will hear a little bit more about that later today and also tomorrow. We have a panel of fired NOAA scientists, so come back for that later this afternoon. But the real reason why we're here is that it doesn't have to be this way. So if you're liking what you're seeing on the stream, please use this link that's scrolling across the bottom of the screen to contact your representatives and tell them to defend weather and climate science by fully funding NOAA, NASA, NSF, and the other agencies that make this work possible, protect NCAR as well. So these decisions are being made right now and they need to hear from you. So make your voice heard to your representatives. With that, I want to bring up our next speaker, Hikaru, who is the Executive Director of Climate Cardinals. So welcome to the stream and take it away.
Yeah, thank you so much, Haley. And yeah, good morning, everyone. I'm joining you all from New York City. And thank you so much for joining in and all the incredible work that all the scientists and practitioners who've been presenting do. And also, it's very roundabout for Haley to be hosting this for me because when she was at NOAA, we had also been speaking for a long time about collaborating. But as Haley said, my name is Hikaru Hayakawa. I am the Executive Director of Climate Cardinals. We are a global organization focused on the language barrier in climate science. And so I'll share more about what that means. But basically, we were started by teenagers 6 years ago because we realized the climate movement was leaving people behind. And so we started translating climate information, and through that, we also did a lot of policy work. We also spoke a lot with different US agencies around protecting people's lives from climate disasters. So essentially, billions of people are excluded from taking action on disasters and on how climate change is affecting their communities because information isn't available in their language. So up to 98% of climate science research is only published in English, but only 18% of the world speaks the language. And there are actually only 400 million native English speakers. And within the US, there is a very significant population of households that do not speak English at all at home. And so the issue is that a lot of communities that are being affected by climate disasters that don't have adequate infrastructure to respond are not receiving adequate information through their education systems, or they don't, for example, have access to emergency alerts that are translated into languages that they understand. So part of the issue is that for policymaking processes, like within the US and globally, there's an issue where like these communities are not being included. Another part of the issue is, as I shared before, there are significant issues with emergency alerts, and actually there was government funding dedicated to climate scientists researching risk communications. And risk communications matters greatly, as we saw with what happened in Texas, as we see what's going on within the country, every month. And there have been many cases, for example, during the LA wildfires last year, where communities have failed to evacuate because they weren't able to receive information they can understand. And there's also a need not just to translate the information, but also to do research on what information actually gets people to act. So for example, like within Arabic, the word for tornado and for hurricane are the same. And so if you were to translate tornado or hurricane into Arabic, there would need to be more context, or else communities wouldn't know what to do in order to prepare. And so actually, there has been legislation around this, and there is supposed to be emergency alerts in up to 14 languages, but because of current funding cuts like that, there hasn't been that much information on this. Another manifestation is that essentially a large proportion of the global population and the US population cannot also share their information and what they're seeing on the ground, and how that can inform broader climate science and broader efforts to protect communities. And even though there have been significant advancements in technologies, the role that the US government was playing was very important, because globally and also within a lot of states and municipalities, there wasn't as much support for dealing with this language barrier. And the US federal government was really pioneering the way, and also creating models that could work, that also include humans in the loop, because with emergency communications in particular, translations can matter a lot. So it's incredibly important that there is standardized language and that communities are aware, and that it also meets their cultural context so they know what to do in times of disaster. And so essentially, this language barrier can delay local adaptation. It can prevent people from evacuating, responding to disasters. It also, will undermine that there are solutions within communities, and also concentrates decision-making, within communities that are well-resourced, that are able, that don't deal with the same language barrier. And so basically, a lot of the solutions that we had originally provided to a global community, the US was already working on, and under the current way in which things are functioning, these are still very much possible, but there's a need to really invest in the research that's going behind all of this, so that communities can receive information that is accessible to them, and that meets their needs. And so essentially all of this information is on Climate Cardinals website. This is our broader research. Beyond that, we do implement programs. So if you're interested in learning more, please feel free to reach out. If you're all also interested in being directly connected to research or scientists who are working on this issue, let me know too, and we'd be happy to connect you. But with that, I will conclude this presentation, and I'm happy to answer any questions, but I'll stop sharing my screen for now.
Hello, thank you for that great presentation. We have a question from the chat, which is how many languages do you have in the Climate Cardinals database at the moment?
Yeah, that is a great question. We cover 150 languages within Climate Cardinals.
And just to add my own question on that, how do you determine what languages? How does that work? Could you speak a little bit more about the translation process and everything like that? Because I think it's super interesting.
Yeah, of course. So we have a global volunteer community, although a significant portion of our volunteers are also in the US. And essentially through them, we're able to offer translations. But the way that the translation process looks like for us is that we have our own dashboard, and the dashboard has like access to specific machine translation tools, which produce the base translations. And attached the machine translations is also glossaries that we've created with linguists and scientists to ensure that we're translating terms correctly. But basically, since the information that we are translating is very critical, like we always involve humans throughout the process. So basically, the translation gets broken up among multiple people, and there's always a single person who proofreads the entire document. And then most of the translations we're receiving are coming from partners. So, for example, we'll get requests from governments, from various UN agencies focused on disaster communications and children. And in fact, we have done informal translations in the past for different government agencies, as well as official ones for municipalities and state governments.
That is amazing. And just to ask a question that I saw coming up a lot yesterday, how did you personally end up in this space? How did you end up, working on climate and also on the language translation space?
Yeah, no, that's a great question. So in terms of how I ended up working in climate, I mean, I lived through Hurricane Sandy when I was very, very young. And I think just seeing how Hurricane Sandy had affected communities and how, some communities were more prepared for others because of, access to emergency alerts, as well as like access to clear information, what to do, and prior education. That really inspired me to really focus on this issue or on this intersection of climate and like communities. And then in terms of how I ended up doing this work, so basically when I was, a few days, well, actually when I was 18, so a few days before my 19th birthday, Climate Cardinals started as a high school project and basically students were translating climate information for their families and communities because they saw this language barrier. And then basically, it went viral on the internet. Thousands of people signed up. UN agencies and the U.S. government also reached out to us. And so, throughout the next few years, we spent a lot of time collaborating with agencies, providing them insights based on the work that we were seeing. We also have a global chapters network. So we have over 136 school-based chapters. We grant out to them. We also survey them so that we can understand like what they're seeing on the ground, so that we can also provide that information to others. And so, yeah, it's been an incredible and meaningful journey that, of course, relates to so much of what everyone here is doing.
Absolutely. We have another question from WhatDog75, which is, has Climate Cardinals been involved in policy-related work in other countries? I could imagine this being really valuable context for framing policy change.
Yes, definitely. We're involved in policy-related work in other countries, and then we also contribute to different UN processes, both through our own research, but also because we have a global network, we do our best to connect them with different UN agencies and constituencies so that they can represent their communities there. And then, yeah, I mean, most recently, actually, we shared some of our research, or actually the same exact white paper with the Norwegian Parliament.
And everyone should go check out that white paper on the Climate Cardinals website because it is amazing. Great. Well, thank you so much. If there's any other questions in the chat, feel free to ask. I'll ask one of my own questions, which is, because I know a little bit about Climate Cardinals, I know you have a hubs network that operates around the world. So I know we have a couple people maybe watching from different countries. So could you speak a little bit about that and how that all works and how people get involved?
Yeah, of course. So we have a global network of chapters that are translating and localizing climate information and disaster education. Basically, it's primarily targeted at people who are students, so within high schools and universities. And what we provide is, global network of peers, regranting, needs-based capacity building. We also pair mentors with our chapter leads too, and then we nominate them for opportunities. And then they've done a lot of amazing activities. So, everything from like a climate science and communications workshop in Minnesota to we have a chapter at Tribhuvan University in Nepal that does like local disaster education in multiple languages, and they've also done relief, and they've coordinated with local governments to support them during times of disaster. We have another chapter at Kampala International University in Uganda that has gone out into rural areas in their district, basically educating farmers and mothers on how changing weather patterns is going to affect crops and how to prepare for that to ensure that they can keep their livelihoods as well as continue to feed their families.
Such amazing work. And it's so, one of the things that I think is so cool about it is how sort of decentralized it is and how much leadership opportunity people have, the volunteers have. Yeah, and it was started by high school students. It's still, powered a lot by high school students and college students. So I just think it's such a cool project and such an amazing, amazing group of people. Awesome. Well, we are just about at time, so thank you so much for joining us on the stream. And have a great rest of your day. Thank you so much. It was great to see you.
Thank you, Haley. So great to see you. And I'll keep on watching. But have a great day, everyone.
All right, everyone. Yes, lots of thank yous in the chat. I hope he is still here on the YouTube. So we will have a speaker in 1 second, but just before we move on, I just want to remind us all, for the people who've just joined, why we're here. So we are still on hour 17. There's been a lot of great talks. This next speaker will also be amazing. And so I just want to highlight one of the things that I talked about at the beginning of the hour, which is the administration's proposed budget for the fiscal year of 2027. So this budget that has been proposed cuts the National Science Foundation and NASA's Earth Science budgets in half. It eliminates the entire research arm of NOAA, which is where I used to work, the Office of Oceanic and Atmospheric Research, and it slashes programs for training the next generation of young scientists, which I know many of the speakers on the stream came up through those training programs, whether it was through NSF or through a specific agency. So this would be pretty catastrophic to the American climate and weather and science in general, enterprise, and all of the things that are downstream from that. Insurance, commerce, every aspect of your life, just whether you know if you need to bring an umbrella or not. So this is absolutely essential that we reach out to our representatives and demand that they pass a budget that supports American climate and weather science. So you can use the link at the bottom of the screen, wclivestream.com/act, to reach out to your representatives, either by calling them or by writing a letter that our walker, Sil, will deliver in person to Congress tomorrow. So if you want to get your letter physically printed out and into the hands of a congressperson, consider writing a letter. And there's also a script if you want to call them on there. So take a couple minutes and do that. And now I would like to bring up our next speaker, David Shiffman. David is an ocean conservation scientist and author, and he will be talking about why sharks matter, the science and law of saving threatened ocean predators. So welcome, David. And
thanks for having me, Haley.
Yeah, thanks so much.
All right, so hi, everybody. I am Dr. David Shiffman. I am a shark conservation scientist. I live and work in the Washington, D.C. area, and I spend a lot of my time talking about the world's most misunderstood animals, which are sharks. This is my book, Why Sharks Matter. You can check it out there. I am on social media at Why Sharks Matter, where I'm one of the most followed scientists, and I'm always happy to share ways for people to get involved and answer any questions that people have about sharks. So there's a few things that I always want for people to know about sharks. One is that sharks are absolutely awesome. They have all these incredible this incredible biodiversity and behaviors, including some things that are being studied to help humans in biomedical research. Sharks do get cancer. You may have heard the myth that they do not, but they are remarkably resistant to a lot of diseases, and they have some of the fastest wound healing of any major animal. It's actually a problem when we're trying to take a muscle biopsy from sharks in the field, because the puncture wound heals so quickly that it's difficult to go back in for a second piece of muscle. There are over 550 known species of sharks, with a new species of shark or shark relative, the skates, the rays, or chimeras, discovered somewhere in the world about every 2 weeks. So for anyone on this call who wants to grow up to be a marine biologist, don't worry, there's still going to be plenty for you to do. The largest fish in the world is a shark. That's the whale shark. They can be the size of a school bus when they're full grown. I actually just 2 weeks ago was in the Maldives on vacation and got to see my first ever wild whale sharks, and it was absolutely awesome. But the smallest shark in the world is smaller than an adult forearm. It's commonly cited as the dwarf lantern shark, though there are lots of species that are about that size, and they come in just about every shape, size, and color configuration in between. You have some species of sharks that live in the open ocean and might never encounter a hard surface as long as they live. You have some species of sharks that live in the deep sea, where it's so deep that sunlight never reaches them, and the pressure would crush us or something that's used to the surface. You have some species that live on beautiful coral reefs that you may be familiar with. You have some species that live under Arctic ice. US Navy SEALs have a saying that if you want to know if there are sharks in the water near you, what you do is you dip your finger in the water and you taste it. And if it's salty, that means you're in the ocean and there are probably sharks near you. And that's true, but it's incomplete, because some sharks spend their whole lives in rivers, not just the bull shark. So these are an incredibly biodiverse group of organisms. They've been around forever. Sharks were swimming in our oceans not only before there were dinosaurs on land, but before there were trees on land. A truly ancient group of animals that have so far survived every mass extinction event this planet has had, which is just absolutely incredible. And we're learning new things about their biology and ecology and behavior all the time. Just last year, just in 2025, we discovered for the first time ever a shark that can make noise. If you read any textbook from before this year, it'll say no sharks can make noise. Then last year, scientists documented sharks making noise. So we're learning new things all the time, which I think is very exciting. When most people think about sharks, you think about sharks being a threat to you and your family when you go to the beach. And it's true that some people are injured by sharks sometimes, but that's really incredibly rare, astronomically rare, really. And some things that hurt more people than sharks. You are more likely to be bitten by another human on the New York City subway system than by a shark anywhere in the ocean. More people each year are bitten on the New York subway system by other people than are bitten by sharks in the whole world. As a social media guy, I love this one. More people are killed by falling off a cliff while trying to take a selfie of the scenery behind them than are killed by sharks. More people are killed by flower pots falling on their head from above as they walk down the street than are killed by sharks. So sharks are just not something you need to worry about, but they're not only not bad, they're actively good. They help structure ocean and coastal food webs. They help make sure that the ecosystem is healthy. When we're talking about protecting these ocean and coastal food webs, you need to protect the whole food web, and that means protecting the top of the food chain, and that is often sharks. Sharks are not always the top of the food chain, something like a dwarf lantern shark isn't. But when we lose top predators, it can have ripple effects throughout the entire ecosystem that have unpredictable effects. Sharks are unfortunately very threatened. We are in serious danger of losing many species forever. These are animals that have been around for 450 million years. We've lost about half of them in my parents' lifetime. And the number one threat to sharks and their relatives, which is also the number one threat to marine biodiversity overall, it's not climate change, though that is a big problem and we should stop it. it is in fact unsustainable fishing practices. Hundreds of millions of sharks each year are killed by unsustainable fishing practices. Sometimes that's being targeted on purpose, not just for shark fins, which many of you may have heard of, but increasingly for shark meat, which many of you perhaps had not heard of. But also bycatch, which is unintentional catch of sharks and their relatives. When you're trying to catch tuna and you accidentally catch sharks and sea turtles and dolphins that were swimming near the tuna. Climate change is a threat to some species of sharks, though most species of sharks simply adjust their range. Climate is a major threat to marine ecosystems, especially coral reefs and some other threatened ecosystems. But for sharks, they can mostly just move. But the good news is it's not too late. We know what to do to save these animals. The number one threat to sharks and their relatives is unsustainable fishing practices. But the good news is we can make fishing practices more sustainable. Sustainable fisheries for everything, including for sharks, exist. The US actually has some of the best managed shark fisheries in the world. Until recently, they provided fins and meat. Selling the fins is now illegal, but they still provide meat. And other fisheries can be made to minimize their bycatch as well as their habitat destruction through a variety of legal and technological means. That's actually the subject of my second book coming out this fall, which is Why Sustainable Seafood Matters. The single most effective thing that you can do to help save sharks as well as to help save other organisms is to not eat unsustainable seafood. Notice I did not say you all have to give up seafood entirely and become vegan. You certainly can do that, but it's not necessary in order to save sharks and their relatives. Sustainable seafood absolutely does exist. And if you don't know what you're looking at, a good first guide is the Monterey Bay Aquarium Seafood Watch program. It used to be a physical card that you put in your wallet. Now it's an app. And you tell it where you are, and it lists the most common seafood available in your area, sorted into a green, which is this is environmentally friendly, eat as much as you want. Yellow, which is you can have it every once in a while, but maybe don't make it a habit. And red, which is this is an environmental disaster, maybe order the chicken. Notably, American lobster is on the red list, the most valuable fishery in the United States. That is because of a bycatch issue, though not for sharks. The way that we catch lobster with the lobster traps is incredibly bad for critically endangered North Atlantic right whales who migrate through the Gulf of Maine area. It's not the traps, it's the lines that connect them to the surface, which are incredibly strong, and there might be millions of traps in the water. So it is a minefield for North Atlantic right whales. So as with other areas of science, the world of shark science is facing some threats right now. It's been a challenging year. There have been funding that's been cut. The world of nonpartisan, expert-based peer review and the civil service system is being challenged. That world is very, very important to help make sure that the scientific recommendations are based on expertise and evidence and data, and not on political opinions. There have been lots of jobs that have been cut. There have been lots of funding that's been cut. There are lots of training programs that have been cut and things of that nature. I have also been involved and have been asked to speak about some diversity, equity, and inclusion initiatives in the world of shark science. One of my favorite is an organization called Minorities in Shark Sciences, or MISS. You can find them at misselasmo.org, and that provides opportunities, including scholarships, travel to conferences, and field training opportunities, as well as mentorship to women and gender minorities of color in the world of shark sciences, which is historically a male-dominated field. There is my team did a study a few years ago looking at Shark Week, which is the biggest stage in marine biology. It is a long-standing documentary series on the Discovery Channel, and it is where more people learn about sharks than just about any other thing out there. Millions of people watch this every year, and we found that not only does Shark Week feature more men than women, Shark Week actually features more guys named Mike than women. But that is not representative of the field. We've done some surveys of our professional society's membership, and we're actually about 60% women. We are more behind than that on people of color, men and women, as well as non-binary folks, but we're getting there. thanks to organizations like Minorities in Shark Sciences. And this is important because a lot of the places where sharks are most threatened are places not in North America. Again, we have relatively good shark fisheries here, and it's important to have everyone have a seat at the table. It's important for people to be able to look up at a presenting scientist and see someone who looks like them, to avoid things like science colonialism and parachute science, where someone like me goes into a developing country and says, hey, what you're doing is bad and you should feel bad and you should do something else. That does not work as well as when you have a local partnership, a local collaboration, or a opportunity for someone representative of that community to provide the same types of information. So another thing that I've been asked to talk about here is this concept of brain drain. What happens when we lose these entry-level science jobs? What happens when we lose these long-term data sets, these long-term funding opportunities? Well, this is a problem in shark world. This is a problem in climate world. This is a problem for everything. And some well-intentioned folks on social media I have seen say, well, that's okay. All the scientists will just go to Canada. We'll just go to France. We'll just go to the UK. We'll just go to China. It doesn't work that way. You have seen some highly publicized opportunities for some top labs to relocate to Europe or things like that. But that's a few $1 million are being thrown at that. That's enough to bring 4 or 5 top scientists. But there are hundreds of thousands, if not more, of scientists who are losing their jobs in the US, and there just aren't enough jobs in the rest of the world. What's going to happen as a result of all of this is not science temporarily relocating to another place. It's just going to be a lot less science. And it's going to be fewer people being trained how to be scientists and then have the next great idea. It's going to be fewer people working in the science infrastructure pipeline. It's just going to be bad for not just people, not just sharks, not just climate, but everyone, everywhere. And who knows what next great world-changing idea won't happen as a result of all these funding cuts. So this link at the bottom of the screen encouraging people to contact the representatives to support science funding. That's important for NOAA, which doesn't just do climate stuff, but also funds a lot of sustainable fisheries work, shark work. When we're talking about saving the whales, NOAA are the folks in the US who do that stuff. They're facing very serious budget cuts as well. These things used to get overwhelming bipartisan support. There are threats at the moment. I have been told to leave 5 minutes for questions at the end, and we are now there. So welcome back, Haley. I am happy to answer anyone's questions about any of this stuff, about sharks, about marine biology, about ocean conservation, the role of science funding in any of this stuff. Again, you can find me on social media at Why Sharks Matter if you want to ask me a question later. So I can't see the questions, so I will let Haley read them for me.
I will read them. You have a ton of questions and a ton of people very excited about sharks in the chat. So our first question is, what is your favorite species of shark?
Oh, what a great question. My favorite species of shark is the sandbar shark. Follow #BestShark and you'll learn all about them. But there's a few reasons why I love my sandbar sharks. One is they're nobody's favorite shark. They don't get no respect. And they should, because they are an incredibly well-studied species of shark. So the longest standing shark research program in the world is at the Virginia Institute of Marine Science, not far from where I am in Washington, D.C., and that's right by a sandbar shark nursery. So they've contributed to hundreds of scientific papers. They were my master study animal. So they're not the first shark I ever saw, but they're the first shark I ever saw a lot of on purpose, which is great. But for millions of kids around the world, they are the first shark they ever see in their life because they're very common aquarium animals. So they are very important. They are very important ambassador species in that regard. So I love my sandbars. #BestShark.
I will definitely be checking those out. That sounds amazing. Another question from WhatDog75. Are we seeing large-scale shark migration due to climate change?
Yes. And that I was part of the team that documented the first ever known case of this, which was bull sharks. Their nursery areas used to be in about North Florida. And there was a long-term data set in coastal North Carolina. I did my undergraduate at Duke and spent some time at the Duke Marine Lab in the Outer Banks. And for years and years and years, we had never seen baby bull sharks in North Carolina Outer Banks. And then after about 2004, 2005, they started seeing them all the time, and they've been there every summer since. And that correlates very nicely with sea surface temperature rise. So yes, we are starting to see that, and it's since been documented in a few other species.
Awesome. Next question is, how do fisheries minimize bycatching? Do they sort through their catch?
What a great question. So there are a few ways to do it, and usually it does not have to do with sorting through their catch, because as you can imagine, that can be quite complicated. It's usually trying to reduce the catch in the first place, and you do that by modifying your gear. You do that by modifying where or when you fish, things like that. So sometimes it's really simple. If you're trying to catch tuna, and not sharks, you have one piece of bait that tuna and sharks both love. You have another piece of bait that tuna love and sharks don't. You use that second bait and you catch tuna and not sharks. It's very rarely that simple, but sometimes it's exactly that. There's one of the most successful things in this world is called a turtle excluder device. And it's basically a trapdoor that goes in a shrimp net. And shrimp are not heavy enough to trigger that trapdoor. So if you're dragging your net and you catch shrimp, the shrimp are still caught. But a sea turtle is heavy enough. So it triggers the trapdoor and it can swim out and be fine. And sea turtle mortality, the number one source of it was shrimp trawl bycatch in the 1980s and 90s. And this fixed that problem. It has led to 98% reduced mortality in the shrimp trawl fishery. This was a device invented by a fisherman, and it works just amazingly well.
I am so happy to hear about that. That's incredible. And so cool that it was invented by a fisherman. Next question, how often are you in the field for your work?
I am somewhat of an atypical case. So I live and work in the DC area. I have been out in the field here once, helping and it was not working on sharks. It was helping Maryland DNR go electrofishing for invasive blue catfish, which was awesome. But I was just in the field all last week down in Miami, Florida. Mostly when I do it at this point in my career, I'm doing it in the context of teaching students how to do field work. And I will note, I have an open enrollment course this fall. If anyone has always wanted to be a marine biologist, Center for Wildlife Studies offers this course that I teach, where it's lectures that are asynchronous online, and then an opportunity to spend 3 days with me in the field, learning how to catch, measure, tag, and sample sharks. You can take it for graduate school credit, or you can take it just for funsies. I'm going to be in the field about 6 weeks this year.
That sounds like such a good opportunity for all the shark lovers in the chat. Check it out. Okay, we have one more question, which is, are sharks significantly affected by microplastic?
Well, that's a great question. And the answer is, we're starting to learn that the answer is everything is affected by microplastic. We don't know exactly what it does, but it seems to have similar impacts to other things, which is sort of endocrine system disruption. Other types of plastic can be a problem as well. There's entanglement hazards. Your stomach can fill up and can't be digested, which means you don't feel hungry, but you can't digest anything. Microplastics, we don't know all the impacts that they have, but yes, there have been sharks documented with lots of microplastics.
Awesome. Okay, I lied. We have one more question, which is just, can you repeat the course information?
Sure. It is through the Center for Wildlife Studies. If you go to my Instagram @WhySharksMatter, I'll share a story with it right now.
Great. Thank you so much. That was so incredibly interesting, and love all the shark love in the chat. You should check it out. Thank you so much for joining us.
Thanks for having me. Have a great day, everyone.
You too. All right. Thank you all so much for all of your emojis and interactions and shark chanting in the chat. That was awesome. So next we have another incredible speaker. And before that, I just wanted to follow up on something that he talked about a little bit and remind us all why we're here. So one of the things that is going on right now that is really threatening American science in general, not just climate and weather science, is political interference in research funding. And actually, breaking news last week, the Office of Management and Budget proposed some incredibly extreme rules on the way that grants will work, which would let political appointees make funding decisions instead of scientists, and make the peer review process optional and not the final decision of what gets funded. It would limit the types of science severely that can receive support. Specifically related to what he was just talking about, it would basically ban, as a condition of the grant, any research into DEI, gender research, or any related topics, and those are very broadly defined and not necessarily scientifically backed in the way that they are being used to restrict grant funding. And it also would severely restrict how scientists share their work with each other and the public. For example, banning and creating a broad prohibition on international scientific collaboration, which is, the lifeblood of how the scientific process works. So this would be a huge, huge problem. So please use the link at the bottom of the screen, wclivestream.com/act, to write and call to your representatives to urge them to oppose these new rules from the Office of Management and Budget. You can also write a public comment on these rules. Public comments are open right now, so please consider doing that and making your voice heard in support of science and the ability to continue doing free, science in support of things that matter the most to all of us. So with that, I want to bring up our next speaker, Molly Robey.
Hi, good morning.
Molly is... Sorry, my thing's not loading. Molly is a professor at the Loyola University of Maryland, a meteorologist, and also a Ph.D. student at Johns Hopkins. So welcome, Molly, and you can take it away.
All right, thank you, Haley. Yeah, good morning, everybody. Thanks for having me today. So I wanted to talk a little bit about some ongoing research that I'm doing at Johns Hopkins. So I am going to be starting my third year as a Ph.D. student there. And as Haley mentioned, I'm an assistant teaching professor at Loyola University, where I teach communication classes as well as a meteorology course. So last year, I had the privilege of talking about the ongoing research, and a lot of that has to do with weather stations in Baltimore City and really focusing in on some educational materials that have been developed. So let's go. All right, so the Baltimore Community Weather Network is a host of more than almost 60 weather stations at this point, strategically placed across Baltimore City. So a lot of these neighborhoods have historically never had access to real-time weather data. So these weather stations can, with Wi-Fi signal, get real-time data online. And so a lot of this work is not only putting up these weather stations, but also making sure that our communities are educated about the weather stations, how to access the data, and then how to use that to better position themselves with climate change and hopefully advocate for change in the future. So this work was funded by the BSEC initiative, which is the Baltimore Social Environmental Collaborative. That was funded through the Department of Energy. We did unfortunately lose a lot of that funding over the past 2 years, but this Baltimore Community Weather Network was really a rebrand out of the BSEC initiative because a lot of these weather stations are pretty low budget and they're already operational. So we feel pretty confident that we can keep those going. And they've been operational for about 2 years now. So today I'm going to be focusing in on about 3 different branches within the Baltimore Community Weather Network: education, the brand kit, and some community engagement initiatives that have been ongoing for the past couple of months. So first up, we have the brand kit, which I'm really excited to share. So as a professor at Loyola, as I mentioned, teach a lot of communication-based courses. So through one of my media writing courses, I had students develop a brand kit for the Baltimore Community Weather Network. Students were broken out into about 5 to 6 groups, and we met with my advisor, Dr. Darren Waugh at Johns Hopkins. He kind of gave us a real outline of what the Baltimore Community Network is, our mission, our focus, and also connected us with many partners. So the host sites of those weather stations that I mentioned prior. So this was the winning logo. The 5 to 6 groups sent off their brand kit, not only to Dr. Waugh, but also through many of our partners. They all voted on a winning logo. And this was the logo that was chosen: real data, real change for Baltimore. What I loved about this was that the students actually assigned kind of slogans for each color. So we can see light blue is wisdom trust. The community can trust our forecasts. Black, we aim to empower neighborhoods. Green represents nature, growth, and harmony. And yellow symbolizes optimism, energy, and warmth. So in addition to the logo and the brand kit, another class, media writing class, in this class, it's very writing intensive. So they're practicing how to write press releases, website copy editing. So I had another class help develop the website. So the students wrote the mission. We broke out each kind of tab on the website, collected interviews with some of our partners, and the students really seem to enjoy these kind of experiential learning opportunities. So not only are they getting a grade for the content they're developing in the course, but it's also living beyond the course. So this really got me thinking about a research question. How does participation in experiential learning opportunities impact undergraduate students' perspective on climate change? And this idea not only came from my work with the Baltimore Community Weather Network, but I also teach an introductory meteorology course at Loyola, and that's with these students are pictured here. We started talking about the wildfires that were burning in California at the time, and the students really suggested that climate change really feels broad to me. I don't really feel like I can connect personally to the issue. Through an in-class activity, they actually developed a full wildfire donation drive on campus, and they collected roughly about 100 materials that we sent to California. And after this, I started hearing things like, wow, after I talked to that person at the YMCA in LA, I really feel connected, and I hope that they, get the help they need and that we're making a difference. And so that started also kind of weaving into this research question is, if we can get these hands-on experiential learning activities to students, how could that potentially shift their perspective on climate change? Now I'm going to move into more of the education side of things. So this is a lot of where I've been spending the majority of my time. And there is past research to suggest that by educating communities that are potentially vulnerable, marginalized communities, by education, we can build their resiliency. And that's coming out of a study in 2014. Additionally, there was a specific study in 2015 that took weather stations, placed them at an institution at a high school, and they found that students felt more empowered, better connected to the weather and the climate by going to the weather station, visiting the weather station, and collecting that data themselves. So this question developed: how does involving youth and weather station related activities increase their engagement and learning in vulnerable communities? So over the past 2 years, I've been helping to set up the weather stations. This is one placed at the Inner Harbor, really beautiful site along the water, and going to schools. This is a look at a picture from the Crossroads School in Baltimore, also at the Inner Harbor, and really focusing in on a middle school age range because they have state mandated curriculum tied to weather. Now, kind of putting a pin in that for a minute, I'm going to come back to the students. What I've been doing this past semester is collecting qualitative research with a lot of our teachers. So many of our weather stations are placed at schools. And over the past couple of months, I've held listening sessions with some of our teachers and personally interviewed 2 teachers and just wanted to share a couple items of feedback. The weather unit can feel a bit dry, so having this resource could really help. I just need to learn how to use it effectively. The next one, I'm still learning some of the concepts myself, the isobars, so having someone walk through it would be really helpful. So really hearing from our teachers that they're hungry for some sort of content related to the weather stations. The curriculum that they have is very dense. So how can we make it a little more digestible? We don't want to change the curriculum in any way, but provide some supplemental activities that tie directly to the weather station that is at their school. So that's where I've been headed and spending a lot of my time over the past couple of months. Let's see. The slides are not moving. Here we go. All right. So After collecting the qualitative research and hearing from our teachers, I took it back to my students at Loyola and I said, in my meteorology class, how can we put together a packet of materials that would provide these activities to our teachers and our students? And I got this inspiration from visiting Assateague Island with my family. So my sons are 3 and 5, and they participated in the Junior Ranger program. I don't know if anyone's familiar, but it was such a cool experience. So we went to Assateague Island. The ranger came out, gave this packet of activities to my eldest son, and said, "You have an hour to complete this. Come back, and we'll swear you into the Junior Ranger program." And it was such a fun activity. My son really enjoyed it. We helped him with it, and at the end, the ranger came out. It was a major deal. He swore my son into oath and he got a badge. So this really gave me some inspiration. If all these kids are there really having fun doing this packet, getting this badge at the end, I wanted to kind of replicate this as the Baltimore Community Weather Network activity guide. So here's just a few pages from the guide that has been put together. And again, the Loyola students really helped organize. They examined the curriculum that is state mandated and really tried to tie each activity to something they found in the curriculum guide. So we have our mission on the first page. We have find the differences in the pictures of the weather stations. And then at the end of the packet, there is an oath that these students can take. We're still working out and getting feedback at the moment, but we hope to provide some sort of gift or sticker or badge once the students take their oath. So just to kind of close out, had the opportunity to test the packet for the first time at the Mother Mary Lane Catholic School. It's a private institution in Baltimore City. And this was with roughly, I'd say, maybe 50 to 60 sixth graders. And they really enjoyed going through the activities. Specifically, they loved the find the differences between the weather station as well as a word search that's in the guide. They are about to take their oath. I just talked to the teacher last week. So we hope to stay in touch with them and continue to test this out this summer. That's really the plan. So get more students engaged. I'm also going to be talking to some Baltimore City public school teachers here in the next few weeks, actually, to get their feedback, not only from a student perspective, but a teacher perspective, and also have an opportunity in August to engage even more teachers. So at this point, really just getting feedback, seeing what works, seeing what can be improved, and hopefully going to leave it for many students in the future to engage with and enjoy. So thank you. I want to leave some time for a few questions. This is a picture of my oldest son, Miles. He got his badge there at Assateague Island. Of course, we had to purchase the Ranger vest. Such a clever idea to have that there for families. And then the other picture is both of my sons and I checking on a weather station at the National Aquarium, which the last talk was about sharks. So if you've ever been to the National Aquarium, you can see one of our weather stations just outside. So thank you so much for listening. We definitely could use funding, and we want to make sure that we advocate and keep funding and support for our scientists and for ongoing and future generations. So any way we can help, we have to do our part. So again, thank you so much for listening, and I would be glad to take your questions.
Awesome. Thank you so much for such an interesting presentation. We have some questions from the chat. So first of all, what are you or some of your students' favorite hands-on climate-related activities?
Yeah, I would say hands down the wildfire donation drive. So that was actually came out of a discussion post. I had said, you know, if we were to help those in California who are dealing with the ongoing wildfires, what would we do? How could we help? And somebody had suggested actually taking money or doing a drive. So that the students didn't really feel like that was work. I obviously graded them and kind of served as their project manager and divvied them up into teams. But, that took about 2 weeks out of our 16-week curriculum to really pull together. But, a lot of our class time was spent doing actual work, making posters, getting the collections, and even, boxing up the materials, getting them in my van so I could drive them. So I think, it didn't really feel like schoolwork. It felt like something that we were actually making a difference doing.
That's so cool. And I've seen a couple studies about the importance of teaching climate with action. So it's really cool that you can do that as part of the curriculum as well. And it also makes it feel, more fun or more, hands-on. So that's really cool. Another question. Oh yeah, sorry.
No, I was just going to say that even with the activity guide, it was a similar experience where, the activities are obviously for elementary to middle school. So the undergraduate students were excited to kind of look at weather in a different perspective, and we're excited to shape that for a younger audience.
So cool. Awesome. So we have another question from the same person. What is my life? What are some challenges you've encountered creating activities and incorporating it into the curriculum?
Yeah, that's a great question. So the curriculum guide that we've worked on or examined, it's over 300 pages. So it is a lot of material, and it can be really, the students and I have found it can be really difficult to tie that to something that can be engaging to students. So one particular page we have is, and I can share the guide if online or on my social media page if anyone's interested, or you can contact me there. But we basically take a flashlight and we hold it over the page and we draw a circle, and then we bring the flashlight higher to really just kind of show students how the solar radiation spreads and how that can impact temperature. And so not only are we trying to make sure we're tied to the curriculum, but we have to do it in a fun and engaging way. And I think that's like really the research question I'm trying to answer. How can we get them engaged and excited about weather and climate?
And perfect segue to our last question, which is, what can I do as a mother to inspire or interest or create lessons for my own kids? They're the same age as yours, 3 and 5 in a few weeks.
Oh, that's great. I love that question. Yeah, I think, we have to get in their minds, meet them where they are. So from my perspective, I was home with my kids in the winter during a snow day, and I thought, we can't go outside, it's too cold. So brought the snow inside, put it in the bathtub, and just let them use measuring cups and sticks and all kinds of things to play in the tub. But through that, really tying that to the change of state of water. Okay, so we're inside now, the snow's melting. So through simple hands-on activities, we can still inspire interest and excitement about science and climate. But I think the point being is that we have to meet them where they are. So if they're 3 and 5, we're literally just maybe letting them touch snow and letting it melt in their hand. If they're in middle school, maybe it's a word search, maybe it's the flashlight activity. If it's a high school audience, which is where eventually we'd like to take things, they're on social media. So how can we maybe get them to create an Instagram reel or some sort of weather forecast that meets them where they are? So I think that's the main kind of point to consider, is meet your audience where they are.
Great. Thank you so much for joining us and for sharing this amazing work. Super excited to see where it goes in the future and hear more about the packet and everything.
Yeah, thank you. And you can, if you want to get in touch or have any questions about the packet, my Instagram handle is @meteormolly.
Awesome. Thanks so much. We have lots of thank yous in the chat. Have a great rest of your day. All right. Thank you all so much. Welcome back. We are now on hour 18 of the stream. It just turned to 9 o'clock where I am in Cambridge, Massachusetts. So maybe beginning of the workday for some people on here. Welcome. I'm seeing some new names in the chat. thank you all for being here. So before we go to our next speaker, I just want to quickly remind us all why we're here with one example of one of the things that is really motivating us all to come out and spend 50 hours speaking about science, and that is the threats to NCAR. So NCAR, which, one second, I don't want to say the name wrong. It is the National Center for Atmospheric Research. I never unpack that acronym, so got to learn to do that. Is an absolutely essential world-renowned laboratory for weather and climate science. It's in Boulder, Colorado. It is a beautiful building. If you haven't seen it, check it out. Google some pictures. And it is currently under threat, not because of a legitimate scientific disagreement or something like that, but because they literally say that NCAR's climate research does not align with the current political priorities. So that is, they're trying to dismantle it and break it up and take the supercomputing capabilities and give them to other, agencies or other things around the government or in the private sector. And that is not something that we can let happen because it's such an important resource, both for American climate and weather science and also for the entire world. So I really encourage you to use the, scrolling link at the bottom, wclivestream.com/act, to reach out to your representatives to tell them to protect NCAR. And we'll be back with a new action in about 20 minutes. And before that, we will have our next speaker, who is Alice Bradley. Alice is a professor at Williams College and we'll be talking about Arctic coastal sea ice. And I also just want to remind everyone that everyone is speaking in their personal capacity. These are all their own views and not necessarily the views of their employer. So everyone's speaking for themselves. And with that, I would love to turn it over to you, Alice.
Thanks, Haley. Yeah, I'm going to take a little bit of a turn toward the north and turn toward the cold from our last talk, which was really interesting. But my work is largely in how we measure Arctic sea ice. So I'm a professor at Williams College. I live in Western Massachusetts, but most of my work happens in the Arctic. And it does so with the help of satellites, of various data products that are maintained by NASA, by NCAR, and others. So I want to talk about a little bit today about a new project that we've got going, and that we've kind of hit an intermediate point on, looking at how we can tell where ice in the coastal Arctic is stable or not. And so what we're really looking at is the frozen surface of the Arctic Ocean. And so every winter, the Arctic is cold, it's dark. Sea ice grows as the ocean surface freezes, and it expands outward from the central Arctic Ocean out towards Alaska, towards northern Russia, and lower latitudes. In the summer, then the southern parts of it kind of melt back and retreat back into the central Arctic Ocean. What I'm really interested in, and what we're talking about here, is ice that grows along coastlines. And this is, to quote the Disney song, this is where the people are. Like, this is where people actually live and work in the Arctic. There are communities all along the Arctic Ocean. I'm not going to say they're huge, but there are people who live here. There are people who use coastal sea ice for transportation, for reaching fishing grounds, for cultural practices. But then also it's a really important way of protecting the shoreline from big winter storms. Coastlines in the Arctic, where they're largely permafrost and mostly made out of kind of combination of frozen mud and chunks of ice, they're going to be really shallow, or really fragile and prone to fracturing and breaking off. And where we have sea ice, we've got that ocean surface frozen right up to shore. That can be this big buffer that'll protect the coastline from waves, from storms that are happening offshore. The thing is, we don't actually know that much about how this coastal ice works. And that's because a lot of our data and a lot of kind of our understanding of the things that make ice near shorelines stable actually comes from Soviet drifting camps and Soviet ice camps in the 1960s to 80s. the Arctic Ocean north of Russia is really shallow. You can get about 100 kilometers, that's the distance, I don't know, Albany to New York City, offshore before the water is more than 35, 40 feet deep. And this makes it a great environment for building up really stable coastal ice, which was the reason there was a lot of investment in kind of understanding what goes on in these areas by Soviet Russia. That said, then the Soviet Union broke up, the Cold War ended, and we stopped paying quite so much attention. And this isn't to say that nothing has happened in this area in the last 40 years, but it certainly has slowed down and had less attention. So what we're really interested in is the process that makes ice near shoreline stable. And that happens because you've got ice on the Arctic Ocean is drifting, it's free floating. And you can imagine if you like laid a sheet of paper on a puddle, that's about how thick sea ice is relative to the ocean. And so those sheets of paper, those floes are going to drift around and they bump into each other. And sometimes they bump into each other with enough force that you get this crumple zone along the edge, and that creates what's called a ridge. And the keel, the bottom part of those ridges, near shore can sometimes be deep enough that they actually embed in the seafloor. And that is what makes it really stable ice. So there's two different routes or kind of two different mechanisms to do that. You can either have a ridge that formed in the open ocean that kind of drifts in and gets stuck, or you can have ice floes collide close to shore and make a ridge right there. But either way, what you end up with is a ridge of ice kind of roughly parallel to the shoreline that is deep enough to get stuck in the sand, the sediment at the seafloor. And what we want to know is, can we tell if a ridge is grounded, that is, if the bottom of the keel is stuck in the mud, from what's happening on top? We, there are people in the Arctic, there are people who live in these areas, but there's not that many of them, and it's also cold and dark all winter. So we don't want to have to go out and like drill through the ice and stick lights and cameras down to see if individual ridges are embedded before we make decisions about whether ice is stable. So we wanted to see, is there a way that we can use the tools that can see the top of the ice, use different satellites and satellite products to tell how grounded, or tell if a ridge is grounded, and from that, if the surrounding ice is stable. And so we teamed up with other researchers to use the IceSat-2, which is a NASA satellite that looks down at the surface with laser altimeters. So it measures really precisely how high the surface is. And there's a way we can process that data that makes those ridges, or the sails of the ridges, really easy to detect. And so we started by doing that. So we got all the sail information, and then we used kind of decades of records about the relationship between the size of a sail and the size of a keel on a ridge. And that gave us a good estimate of what the keel would look like. And then we combined that with bathymetry measurements or depth charts near coastlines, and we can estimate whether a keel is likely to be deep enough to hit the seafloor. And so the first thing we needed to do then is, it seemed like it might work, so we had to go check. And so we found everywhere that basically the weather was good enough to get repeat tracks or repeat visits along lines that were months apart in the winter. And what we found is that whenever there was a really big ridge, like this one here at about 0.7 kilometers from shore, whenever there was a really big ridge, it would then show up in the next track. That is, it stayed around for months. And everything in the direction of shore of that stayed too. We found that things that were not big enough to embed in the seafloor, like what you see just kind of seaward of 2 kilometers, those things would change. And so we could tell what was stable ice that was persisting all winter versus ice that was coming and going over the course of the winter. And so we went ahead and used this approach on all of the ICESat-2 data, so all of the ground tracks of the satellite over winter 2022. We detected ridges in all of these tracks and then mapped them along the coast of Alaska to try to get a good sense of what basically what ridges were where, or what grounded ridges were where. And so we went into this expecting, based on that research from the 1970s, 1980s, and the Soviet drifting camps, that most ridges would be around about 20 meters, 65 feet of water depth. That's where they had been found previously. That's where kind of the conventional wisdom was, to the point that this depth of water is called the Stamuki zone, referring to these grounded ridges. And what we found was along Alaska in winter 2022 that there were almost no ridges at that depth. We found almost everything. We found a lot of ridges, a lot of grounded ridges, but they were almost all showing up around 10 meters of depth, 33 feet or so, and 10 meters or shallower. And so this was kind of all of the analysis, all of the tracks that we had time and funding to do. And so we ended the paper with this question of like, we think we've covered all the bases. We think this is accurate, but does this mean that there's been a shift in landfast ice behavior, or a shift in the behavior in where you're going to find stable ice? And this is really what you always hope and dream for in science, that you will pose a question, like your research will move something forward, will open new questions, and that other people with other ideas and other tools will take these questions and answer them. And this is the like wonderfully collaborative part of the work that we do, because so we published this paper in 2025, and within months, another group had read the paper, noticed this question, said that doesn't make sense with the data that we've seen before. We should go back and look at it. And so they took maps of the stable ice edge, both from another type of satellite, synthetic aperture radar, and then also from ice charts, which are the kind of the forecast or the nowcast products that come out of the National Weather Service in Alaska to tell people who are out in ships where they can expect what type of ice. So they took all of this data and they looked at different time spans to see, is the ice edge and where we would expect to find grounded ridges moving? And the answer was yes. The data we had from 2022 makes sense with the current locations of landfast ice. It doesn't make sense with where ice was 30, 40, 50 years ago. But it makes sense, and it explains a lot now. So that puts us at this really cool position of having made a step forward. We have this new approach. It opens new questions. So it opens new questions, but some of those we've answered and some of them we haven't yet. And so the question of what's next here is we had the time, we had a student who did a lot of this work, who was able to process winter 2022 along Alaska, but we've got, the satellite has data going back to 2018. It's still up there, it's still collecting data all the time. And Alaska's not the whole Arctic. So we would really like to be able to expand this out and detect more ridges, see what things look like in different parts of the Arctic. But that's where federal funding comes important. we kind of did the free sample version of this project, in that we showed that it was possible. We showed that we can get really cool things out of even a limited amount of data. But there's so much more out there. We just need the time and the computer power to process it. So with that, I'm happy to take any questions.
Thank you so much. Oop,
Yeah.
Are we having a technical issue? There we go. You disappeared for a second, but now you're back. So thanks so much. That was so interesting. We have a bunch of questions in the chat, and chat, keep adding them if you would like to hear more about Arctic ice. First question, we will go to Sydney. Does or will sea level rise decrease ocean ice production because the water is deeper?
So the short answer is no. The long answer is yes, sort of. So the Arctic Ocean can form sea ice because you've got a really fresh layer of water floating at the surface. The freezing temperature of water depends on how salty it is. That's why, I don't know, if your front sidewalk is icy, you can sprinkle salt on it and that'll get it to melt. What it's doing is it's lowering the melting point or the freezing point of ice and water, where that salt is kind of dissolving. So we have this really fresh layer. It floats to the top. Ocean ice production in the Arctic is pretty stable because of that. What is changing, though, is temperatures. And in order to freeze ice at the surface, you have to cool down the ocean temperature to the freezing point. And so basically, the warmer it gets in the summer, the more it has to cool down. And so the long answer being yes, but is because much of the sea level rise that we've seen is not actually because we're adding more water to the oceans, which we are, but it's because we've increased the temperatures of the oceans. And so it's the temperature part that's changing, not necessarily the kind of total amount of water.
Super interesting. Next, sort of related question. Does the ice keel trap animals away from being able to reach the open ocean?
So as far as we can tell, and I will reiterate, like the ice keels are difficult to get to. They're under, even just the flat ice is a meter, like 5 feet deep by the end of the winter. The ice keels extend way below that. So we don't necessarily have a really complete picture of the extent of kind of the shapes of all of these ice keels. It's another project, another thing that we're looking at. But as far as we can tell, there is a good amount of kind of passageways through, and they're not so big that you can't kind of go around or over. So a lot of animals do use these as habitat, as kind of a sheltered area to then be able to access both the open ocean if they need to and the more sheltered shore environment.
That is so cool. It's kind of like a cave or a house or
I mean,
something.
Polar bears
awesome.
do use ridges and like caves and ridges as denning. Yeah.
Awesome. We will take one more question, I believe. So does the makeup of the ice matter, or is it more based on temperature or other stuff?
So this ice is all frozen ocean surface. And so the makeup of the ice doesn't actually matter or doesn't change very much. The one thing that we do have is a difference between ice that's fresh, or what we call first year ice. That's ice that has grown out of open water that year, versus ice that has survived a summer melt season and been able to then keep growing thicker the next year. And so that's called multi-year ice. So along coastlines, most of the Arctic, we're dealing with first year ice. It's a little bit saltier than multi-year ice. It's a little bit more fragile, but it doesn't change very much. And the temperature actually doesn't change that much either, because the ocean underneath the ice stays at the freezing temperature all throughout the winter. So what does change is the motion of these ice flows drifting around, bumping into each other, pressing against each other. And so the wind currents that are dragging these flows around or what changes the ice dynamics.
All right. Thank you so much for sharing all of your amazing work with us. And yeah, thanks for being on the stream, and have a great rest of your day.
Thanks. You too.
All right. It is 9:22 here. Thank you all so much for joining. Before we go to our next speaker, I just want to remind us again why we're here. I'm actually very excited for our next speaker because I also used to work at NOAA. You'll hear a little bit more about that in a second, but I just want to say we are here because, especially in the US, climate and weather science is at risk. There are rules being changed so that political appointees, rather than peer review, determine who and what types of science get funded, as well as how people can work together and what they can share. Political interests are being used to justify the dismantling of the National Center for Atmospheric Research, which is in Boulder, Colorado, and is what much of the weather and climate science in the whole country and around the world depends on. And then also the proposed budget by the federal government for this next funding year, which is now being considered by Congress, would gut sometimes up to 50% weather and climate research across different agencies of the federal government. And it would also end foundational programs for young scientists, which support many, many of the people on here to do the work that they do and help to get their careers started. So if you have a second, go to wclivestream.com/act. It's scrolling across the bottom of your screen, and take a minute to either call your representatives, there's a script, or write them a physical letter, which will be delivered tomorrow to people in person. So if you want your letter handed off, printed out physically to a congressperson, write a letter and get it in there soon. And with that, I will turn it over to our next speaker. So welcome to the stream, Craig McLean, who is, as you can see on the screen, retired from NOAA. He was the former director of research and the acting chief scientist. And I will turn it over to you. Thank you so much for being here.
Well, Haley, thank you very much. And I have to say, you and the team that has put this on together, I do nothing but congratulate you. And I encourage everyone that's listening or who may listen to the taped recordings to be the activists that you're being asked to engage in and take up the direction that Haley and others are encouraging you to do. I also want to thank Andrew, who's backstage and making sure that I had all the wires connected here. I'm not very good at this, I'm sorry to say. What I wanted to talk to you about today is looking at the circumstances of NOAA research, which is proposed for elimination. As Haley said in the kind introduction, I was in charge of that up until the year 2022 when I retired. At that point in time, we had a rather secure and optimistic outlook for where NOAA and NOAA research might be headed, and we had excellent leadership throughout the agency. The circumstances that we find ourselves in now is a threat for the elimination of NOAA research, and I want to spend a little bit of time talking about that. And I'll go back to the tune of "You don't know what you've got until it's gone," and that comes from a song that, for some of you more contemporary music fans, would go back to Counting Crows, who performed this song. I believe it was in 2002 that they first recorded it. But the original came in 1970 by a brilliant artist named Joni Mitchell. It was an environmental protest song. And Big Yellow Taxi, you could read the lyrics of it, but there's a line in there that says, "You don't know what you've got till it's gone." And that's basically where we are right now with NOAA research. You can see by the title, the role is to provide unbiased science to better manage the environment, and read into the rest of that for nationally, globally, et cetera, for policy. But we're in the unfortunate circumstance now today where that is being suppressed. The desire is to dismantle it, and it will be disastrous if we do dismantle the NOAA research enterprise. Not because I used to work there and I'm so abundantly proud of it, but because many people have studied this question and they have rejected routinely the idea of breaking up NOAA research and distributing the parts and pieces to the operating line organizations. So let's go on a little bit of tour. May I have the next slide, please? If we go back to the 1950s, 60s, 70s, I show you here the Cuyahoga River in Ohio burning. It did so many times. I think the latest time was around 1951. But then also around that time, you had in the lower left, Rachel Carson's brilliant book, The Sea Around Us. It was an awakening. It was a door opener intellectually to people to realize how valuable and why and how the ocean is important. And then, of course, Cousteau. So we had a wave of environmentalism. That wave of environmentalism resulted in the creation, next slide, please, of new agencies that were designed to protect the earth. You had the Environmental Protection Agency born. You had a Sanctuary and Ocean Dumping Act passed. You also had the creation of the Clean Air Act, Clean Water Act, and the creation of NOAA. The mission of NOAA was threefold. Next slide, please. To be looking at this earth and the volume of water here brilliantly portrayed, as I've cited the makers of this diagram. You've probably seen this before, but it's a surprisingly low number or small number of water volume that you could imagine on something as big as the earth. It's likening it to taking a basketball, dumping it in a bucket of water, and the water that remains on the basketball immediately is how the ocean water is distributed around the earth. So it's not inconceivable that we could be influencing this volume of water. It's also remarkable to realize how that volume of water has absorbed so much heat instead of the land mass, but also how that volume of water constitutes in the 70% coverage of planet Earth. It is the largest biosphere that we have on this planet. Next slide, please. It's also easy to understand how thin this atmosphere is and how we as humans could pollute the water I just showed you, but also how thin this atmosphere is and that we could pollute that atmosphere. So next slide, please. In 1970, NOAA was created for these specific purposes. Number one, quantify, understand, and manage marine resources. Number two, forecast the weather and improve those forecasts. Number three, study the interaction between the air and the sea. And this is an important point. The air-sea interaction we know today as oceanic and atmospheric research. In studying that, we built airplanes, satellites, ships, buoys, gliders, drifters, moored arrays. We hired the scientists. We built partnerships with the academic community for long-term relationships we now call cooperative institutes. We hired the modelers. We hired the people and trained people coming from brilliant universities to come and do this work and become NOAA employees. We built the system to study the air-sea interaction. Now, in 1970, the word climate was a subset of geography. It addressed questions like what altitude in the Andes might bananas grow? What is their range? That is what climate was back in 1970. Since 1970, with all of those elements that I've described, ocean monitoring systems, atmospheric and land-based monitoring systems, we see emerge then what we call today climate science. NOAA did not set out to study climate science. We didn't even know that discipline in 1970, but it evolved through the scientific method, through innovation and ingenuity of scientists to build and understand a knowledge of atmospheric chemistry, ocean physics, physics of fluids, etc. So that became then what is today NOAA's Oceans and Atmospheric Research, the part that the administration wants to terminate. One other thing I'll note for you is that at the time of NOAA's creation, the ocean elements in the federal government were distributed more widely. And the goal was to put all of those ocean, and I know we're talking about weather and climate, but ocean is weather and climate, to put all the ocean elements in one agency. Obviously, the Weather Service was combined with the National Marine Fisheries Service, and we saw NOAA created. But we could offer a guess if you want to take a shot. I'm not sure how we would iterate on this, but how many ocean agencies are there today when NOAA was created to be the one ocean agency? Okay, I'll give you the answer so you could win a drink at your next social outing. There are at least 20 self-described ocean agencies today in the United States federal government. So we've had a number of things change since 1970, and it might be a good time for us to take a look at where we are today, even before the cuts that are proposed by the current administration, but then to look at whether we are fit, organized, and suitable for the purpose upon which we were created. So next slide, please. All right, I'm going to go through 4 high-order questions, which is what NOAA does today. The first one, and you understand the roots of the agency, where the purpose of marine resource understanding, quantification, study, management, distribution, and abundance, it all comes down to how many fish are in the sea. And NOAA does that every day quite well. NOAA has ended overfishing and is today a model for the rest of the world in terms of how to manage national and international fisheries. Next slide, please. Second question, what will the weather be like tomorrow? Again, back to the roots of why NOAA was created. And day by day, year by year, people work very hard in universities and in NOAA labs and in partnership in order to advance the capability of our abilities to forecast the weather. The next slide then is, what will the weather like be 100 years, 10 years, 20, 1,000 years from now? That's climate. Weather times time equals climate. And that's basically what we evolved to in the understanding of how weather is formed. And instead of the old days where the people in New York would just ask the folks in Ohio, what's it like? The Ohio folks would ask the people in Boulder, what's it like? It's very different. We can forecast today based on buoys that are set and Argo floats that are in the Indian Ocean. And that information, as it is read and as it is formulated into models that perform the physics, they will then come to determine what the seasonal forecast will be for the farmer who's in Oklahoma or Indiana or Kansas. And that'll also provide the information that's necessary around the globe, because as we now know, that global circulation is what generates our weather system. And as we perturb it, we wind up with the consequences therefrom. And then the last slide, please. The fourth mission inside of NOAA, which is the question, are we wise to build on shifting sands? And this really represents the coastal management, coastal resilience, the coastal zone management program, National Marine Sanctuaries, Estuarine Research Reserve program, and also the whole notion of the Sea Grant program. And the goal is to make coastal areas safe, secure, resilient, and prosperous. And I think the agency has done a very good job of doing that over the years, but each of those issues that I raise constitute proposed reductions and in some cases elimination by the current cuts, which would be very disastrous, not just for the science that, for example, Sea Grant conducts, but also for the economies and the prosperity and the environmental security of these areas of the nation. Next slide, please. So from those four questions, we wind up now with the organizational elements of NOAA: the National Weather Service, the National Marine Fisheries Service, National Ocean Service, Satellite and Data Information Service, and Oceans and Atmospheric Research. We also have the NOAA Fleet and the NOAA Corps, and that's a supportive element. Sometimes it's included as a line organization, sometimes it's not. But I think the important point is to realize that the mission areas are those five: forecast the weather, manage the nation's fisheries, and understand the ocean biological environment. National Ocean Service is really, one could name it the National Coastal Service, because it really does concentrate on much of the coast. Satellites, we build them in partnership with NASA and the commercial world, but that line organization is also the repository of all the data that NOAA collects. NOAA is the foundation for international organizations and data offerings that are generated therefrom. So that's a very important line organization. NESDIS for short, many of you might be familiar with that. But then Oceans and Atmospheric Research, which was designed to be providing scientific assessment and information, measurements, and the like, to continue monitoring our globe and our atmosphere and our ocean, and to feed into each of these other line organizations. And I'll explain to you in just a short minute exactly how that works and where it comes from. Next slide, please. So the NOAA role is effectively to monitor the patient, the pulse, respiration, blood pressure, temperature. Those are the vital signs of the Earth. And NOAA does that and has been doing it for 50 years to support fisheries, to help inform the genesis of weather phenomena and weather systems. Gray's Anatomy comes down into mapping the ocean, and NOAA does that as well through hydrographic surveys for nautical charts and through ocean exploration in order to map and understand just what is there in that large blue marble that we have in our home Earth, most of which is unmapped today. Next slide, please. All right, so you don't know what you've got till it's gone. So this is a word salad slide here, but my goal is to try and share and illustrate just how much work is done by the agency. So in terms of what we have at risk, and that may be gone from the cuts, we have decades of global ocean measurements. We have defined the El Nino phenomenon and built observing systems in order to measure it and give warning. The reason we know we have a strong El Nino coming is because of what NOAA has built, and several other nations have joined in that monitoring. NOAA built the first tsunami warning system. It's now in use in multiple countries. NOAA in the United States gave that technology to Indonesia after the terrible tsunamis that took so many lives in the Indian Ocean. Ocean acidification was monitored continuously because NOAA scientists, particularly Richard Feely from the Pacific Marine Environmental Laboratory, knew that there would be a signal emerging because of the increase in carbon dioxide in the atmosphere. It would have to dissociate into the ocean. And Feely and his crew continued to monitor until they saw the signal. But what use is an academic signal that could go in a scientific paper? They did the important thing. And because NOAA is interconnected to all mission areas, they brought in the National Marine Fisheries Service and explained to them that as the pH changes, so too will the condition of your early life cycle phases in those commercial stocks that we value and the food that those commercial stocks need to survive. So it opened the door and the aperture to understanding and identifying ocean acidification. The Atlantic Meridional Ocean Turning Circulation, AMOC. I remember some of the earlier cruises that started to define that Atlantic conveyor belt of heat from the tropics to the northern latitudes. I'm not going to go through each of these in this detail, but initially that was done not by the types of systems that are now being withdrawn by the National Science Foundation. In other words, the Ocean Observing Initiative, the OOI, which if you're reading the paper and staying current, you realize that that's right upon us now. But we were looking for tritium and freon because those two gases didn't exist before World War II, and where in the water column we could find them, we could then age that body of water and know that it was on the surface within the last 50 years. So you could read the rest of this. Global Ocean Observing System, NOAA is the backbone of that. It's international, but it started in NOAA. And the United States and NOAA is 53% of the world's global ocean observing system, which informs our weather, which defines our climate outlooks. The systems that we have monitoring that, Tropical Pacific Observing, RAMA, Parata, Argo, Deep Argo, Biogeochemical Argo, all that was developed inside of the United States, inside of our NOAA labs, our modelers, and the like. So we look now also at autonomous vehicles being generated. The NOAA Research Enterprise brought that forward. Let me jump to weather. Every weather model and every weather model modification is coming through our labs, and our labs in NOAA research are 50% populated by academic researchers. We need the research community direly in order to be successful in our mission. And as NOAA has announced at recent hearings, that most of the cuts they anticipate will come from the academic community. That will be disastrous. So, and then lastly, NOAA generated the world's first climate model. NOAA today has the world's best climate model, and also NOAA is responsible for the global greenhouse gas measurement network, and we do that consistently. Next slide, please. So who will miss it? Here's just a short list. Most people that will miss it don't even know where all of this information comes from, but the insurance companies, reinsurers, the P&I clubs, the people who write the checks to backstop insurance losses, they follow NOAA science closely, routinely. Mortgage rates are determined by the uncertainty, and you pay for that uncertainty. So if we don't have these systems operating, you pay more for your mortgage, you pay more for your loans. The cost to the economy goes up. Stock market futures clearly follow the NOAA information. The military gets their climate and weather information from NOAA. Shipping companies, air traffic, etc., engineering standards and the like. Everyone is dependent upon this information for a sound economic future. So let me just offer that every citizen every day is using this information that is proposed to be cut and eliminated. And let me go then to the next slide. Who will miss it? At one point in time, when we saw NOAA used as a cartoon notion for, as you could see, there's a lineup of paired animals looking at NOAA, not the Ark, for global warming. And when you realize that you're now in the news with humor, people are starting to understand what it is that you do. But the last slide is, please, when we look at where the problems are, that is my granddaughter. And she loves the ocean. She loves the earth that she has today. And by the time she's my age, I'm 68 years old. By the time she's my age, I fear that her world is going to look very, very different and not better. And if that's the case, we will not have done our jobs today in order to guarantee her and her generation the future that we need. We cannot allow these cuts to destroy our science. Thank you.
All right. Thank you so much for that. I'm honestly like a little emotional. If you weren't here at the beginning of the talk, I actually used to work at OAR, and I am drinking out of my mug that one of my colleagues made. We were all let go in a Doge cut last summer. So
Criminal,
really
criminal,
thankful.
Haley. Absolutely
It is-
criminal.
Yeah, I mean, literally.
Yeah, it violated the law. It violated the law.
Completely. Yeah, and so we lost people both in the probationary employee firings at the beginning, which OAR lost, and NOAA and the government as a whole lost an incredible amount of people. And then, so I was a contractor, and our contract was messed with at a higher level. So
I am so sorry about that, Haley, and I know that we valued your service, your professionalism, and the work that you did. And there are contractors all over NOAA. And the whole idea of privatization is a ruse, because there's a $10 billion aftermarket weather industry that NOAA is the absolute backbone for. National Weather Service infrastructure, NOAA researchers, the combination of attributes is infinite.
Absolutely. So I just want to thank you so much for getting the word out there, and all of your work before that as administrator and as acting chief scientist. And thank you so much for just continuing to make the case for NOAA.
Thank you, Haley, and thanks. Congratulations to the whole team, and thanks to everybody who stayed up for all of this. This is terrific.
And we'll keep doing it. And we actually have another panel on NOAA this afternoon at, let me just check, at 6:40 p.m. Eastern time. So we'll be back talking about NOAA, and then there are various other NOAA former and current employees talking throughout the stream. So we will keep, banging this drum and keep making sure people know about the importance of the work of NOAA, as well as NASA and NSF and all the other amazing agencies that we're featuring on the stream. So I just want to thank you again so much for being with us today.
Thank you. Good luck.
Thanks so much. All right, and really quickly, just to remind everyone while you're here, Craig just made an excellent case for the importance of federal funding for climate and weather science and all the different ways that it impacts us every day. So if you're feeling pumped up about that like I am, go to wclivestream.com/act, call your representatives, write them a letter, and it will be hand delivered by Sil, who is walking to DC right now. He will give it physically to Congresspeople tomorrow afternoon. So make sure you get your letters in soon. Thank you all so much. And with that, I will turn it over to our next speaker, Dorothy Petit. She is, here she is, amazing. And everything sounds good. And yes, so you can take it away.
Okay. Hi there, everyone. I work at NASA in New York, as well as at Lamont Doherty Earth Observatory. And today I want to talk to you about the importance of tidal marshes. In particular, the ones around New York City. And there's some red dots in front of you in the map in the center of the screen. I want to talk about Jamaica Bay, about Piermont, which is a little bit upriver, and Pelham also on the screen there. Why do we care about these wetlands? Well, they're incredibly important for us. And because we've lost, in New York State, we've lost 50% of our wetlands, California, 90%. They're so important for so many different reasons. They're sponges, so they're aquifers for us. And the in-state wetlands, in the Catskills in particular, really are responsible for New York City water that we get. It's the best in the nation. But coastal wetlands do the same thing, but they're also important nurseries for the whole aquatic system around us, so the estuary. A lot of birds. Well, Jamaica Bay is actually a national park because there's so many birds on the flyway going north. They protect us in storms. Hurricane Sandy was a great example. And because they're water and land, they're an ecotone between uplands and the ocean in this case. And then for us, they're incredible archives of environmental history. And I'm going to talk to you about that and also about the carbon that they store, because only in the last 10 or 15 years have we realized how much carbon they store for us. The rate is much, much higher than forest carbon storage. And they have a really high sedimentation rate so that we can look at fine scale changes through time. But we are losing them at a huge rate. In Staten Island recently, there are a lot of warehouses that are being built on top of them. This is particularly dangerous because New York City is a hot spot for sea level rise. But this coastal carbon is called blue carbon because it interacts with the ocean. And generally that includes salt marshes, tidal marshes, mangroves, and seagrasses. But about half of total carbon in ocean sediments is from these types of coastal carbon. And as I mentioned, the rate is much, much higher, 50 times higher than forest. But you don't hear people saying, go plant a marsh, but you hear them say, go plant a tree. And that just tells you this tremendous carbon storage rate tells us that we should protect them just for that reason alone. As I mentioned, so many have been lost and are threatened as we go forward. Here's an example in Jamaica Bay of what the peat looks like. That's about 2 meters of peat with the plant Spartina alterniflora in Jamaica Bay, and you can see that it's eroding pretty rapidly. So we wanted to ask a bunch of questions with our research. How have the Hudson marshes changed? What's the human impact? What is the accretion rate exactly? And how does the carbon storage shift with climate change and with human impact? And finally, a goal is to really figure out how we can save these marshes because they're so important. So we go out, and I want to thank all the students and colleagues that have helped us over the years. We've been doing this about 35 years. We take sediment cores and look at what's in them. And that photograph on the lower left shows you a core sample with, there are two components really, the organic and the inorganic part. The organic part is anything that was living. So it tells us what the vegetation is. We can get climate from it. We get nitrogen history, and I'll show you why that's important. And we can get a chronology from the site too, from the organic matter. And then the inorganic matter is mineral. So we have sand, silt, and clay. And from that, we can understand what the depositional history is, where this material is coming from. Because a lot of the mineral matter has its own signature based on what kind of minerals are in it. So this is Jamaica Bay. Joko is the highest elevation marsh. Some of the others are being swamped now with sea level rise. And that's JFK, the airport right next to it. That used to be an incredible marsh that's now overtopped with fill to make the airport. And this is one of the things that has happened through time. But you'll see all these graphs, and I'll just go quickly from the left to the right. We do pollen analysis, and we look at the tree tree pollen amount through time. So the orange arrow on the left is when Europeans arrived around 1650 in New York. And you can see that they cut down a lot of trees during the industrial era. We have ragweed rise and then decline as trees have come back in the 20th century. That's the ambrosia there. You can see high amounts of charcoal in the industrial century. And then we have nitrogen isotopes, nitrogen 15 and percent nitrogen, which has just skyrocketed. The axes there, it's increasing on the right. The isotope on the left shows the isotope, which, and a big change in 1900 when sewage treatment plants started processing a lot of the sewage. And then in the 70s, you see zinc and lead dropping towards the top of the diagram. That's due to the Clean Air Act. So that's a really positive, really mark that we see in our cores for human impact, that we can change things. Finally, on the right, you see this pink curve, which is the inorganic decline in the marshes. This is a big problem, and titanium is one mineral there, the last curve there. Titanium and the sand, silt, and clay have been so declining because so many of the streams that fed the marshes with sand, silt, and clay are being blocked now because of the shoreline hardening. So basically, we're starving these marshes of mineral sediment. And on the lower screen there, you see the same thing from another one of the marshes in Jamaica Bay, which is called Yellow Bar. So to summarize, there's a very large decline in sand, silt, and clay since the 1800s. We see that in both marshes. A surprising increase in the accretion rate, and that's probably because there's higher production with higher nitrogen in the marshes. But that lower graph shows you that slight increase of organic matter, but the huge decline in the sand, silt, and clay. And we published a paper on this a few years ago. All of these signals in our cores can tell us both good and bad things about what's happening. But one of the big things we see is that this heavy metal, lead, copper, zinc, is being released into the water as the marshes are eroded. And this causes really a lot of concern for all the fish, the whole food chain, and even the birds that are using the marshes. So we're very worried because we see some big declines in some of our iconic birds, such as the black-crowned night heron in the marshes. Then if we calculate the blue carbon loss with this marsh erosion, this is one of our students, Nathaniel Getz, and this was his master's thesis. You see Pelham has lost 60% of its marsh, lost since the 70s, and that translates into 1,625 tons of carbon that then probably goes into the water, but a lot of it is released back as CO2 into the atmosphere. Then I'm going to move to Piermont Marsh. You see Phragmites, the invasive species, coming in the background, and the Spartina, the natural vegetation, on the right. If you haven't been to a salt marsh, try to get to one. They're wonderful habitats before they get invaded with Phragmites. But now I want you to focus on this red and orange lower part of the diagram that has circles. What that's showing is the medieval warm time in this Piermont core, and this core is deep. It goes down to about 13 meters, but I've only shown you the top 2 meters. We see a huge signal that in Europe we know was warming. They grew grapes. But here in New York, we have huge amounts of charcoal. It turns out a lot of the forest was burning and the marsh was burning, and we changed from a dominance of oak to pine, which is white pine's a drier plant. So this is the first time we've really seen this drought signal in the marshes. We also see a big signal of European settlement with trees being cut down and ragweed increasing, just like we saw in Jamaica Bay. And we also see this huge increase in industrial metals, lead, copper, zinc, in Piermont Marsh as well as with the ambrosia rise. And then over on the right, here's nitrogen again, with very large increases in this part of the Hudson estuary. If we look at the carbon, in particular, this black line, we see that during the medieval warm period and the Little Ice Age, we had much less carbon stored in the marsh. And we think that's probably because in the medieval warm, it burned off. And in the Little Ice Age, it was cold. In fact, the first frost was in August in New York in the Little Ice Age. But they also took a lot of hay off the marsh, which would remove the carbon from being stored. And you can see the old way that they used to take hay for chinking the houses, feeding the horses, etc., from this painting. So finally, to summarize, the sedimentation rates we see in Piermont range from 1 to 6 over the last 2 millennia. But right now, we're facing sea level rise of over 4 millimeters. The average is 2. And so they're really at risk for being flooded out. They need thin layer placement. That has worked in Jamaica Bay some. And here are the carbon sequestration rates that have quite a range. And then to go ahead and look at increased nitrogen, we think that this is making the roots less stable too. But here's our long-term predictions of sea level rise and our rate, and you can see that these marshes just cannot keep up. How about future climate that we're facing? We know that warmer temperatures may cause droughts. New York City is at risk for drought, but we're also seeing erosion. We know there's greater storm frequency and intensity, sea level rise. And for adaptation, we think that we need to clean up the water with more sewage removal, add sediment, and also conserve wherever we can places that marshes could migrate. And with that, I'll close and hope you have some questions.
Hello, thank you so much.
Sure.
And but I want to also welcome Samantha to the stage, who will be taking over for the next 2 hours. There were a ton of questions for you. We only have time for a couple, unfortunately, but people are very excited about estuaries in the chat. So here are some of the questions. Maybe we can go really quickly.
Sure.
So the first one, how has human harvesting impacted our supply of peat?
The human harvesting of the straw has been used up, of course, in the old days. But we still do have a lot of peat in Piermont that is stored there. The peat moss that's sold now should not be used. Really, we're sort of taking everything from Canada now. That peat, we should find substitutes, and there are some substitutes for peat moss that people are buying. Yeah.
Interesting. And then we had a bunch of questions that I'll combine around building over marshes. So there's a question on, can they be rebuilt? And also, how does the water flow change when we build something like an airport over a marsh?
Well, yeah, the water, sometimes Kennedy does flood, but basically the marsh stops growing and you're losing that whole area to, right now they're building peat and they're storing carbon and taking CO2 out of the atmosphere. And when you build over them, you're just sort of shutting all of that off and shutting off the food supply for animals too, and birds and habitat. So it's not a good situation when you build on them. Yeah.
Yeah, absolutely. And especially when there's such important migratory stops for all the migrating. Yeah. Well, thank you so much. It is now
10
a.m.
Thank you for having me. Yeah.
Yeah. Thanks for being here.
Okay.
Have a great rest of your day. All right, we are now on hour 19 of the stream, and it is time for me, unfortunately, to go to work. So I will love to pass this over to our next host, Samantha Kramer, and I will be back on the stream at 6 p.m. Eastern Time tonight after work. So have a great next 2 hours, Samantha, and yeah, you're getting a lot of welcomes in the chat.
Good morning, everyone. As I promised last night on the stream, hopefully we'll get an appearance from both cats. They are not currently cooperating, but our Cats Against Science cuts will hopefully make an appearance as promised. So thank you for joining us. If it's early morning, if you're on the Pacific Coast, or kind of your mid-morning on the East Coast, we still have plenty of great streams coming, talks coming. And I just want to take a second to talk about why we're here. The US has been a world leader in climate and weather science for decades, and that didn't happen by accident. It happened because we, the American people, invested in it through NOAA, NASA, NSF, research universities, and decades of building infrastructure that the whole world depends on. We're talking about satellite systems that track hurricanes, forecast models that tell fire departments about a red flag warning, and air quality networks that tell you whether or not it's safe to let your kids outside to play. And that investment is under threat right now. Weather stations are short-staffed, climate labs are being shuttered. The proposed budget for fiscal year 27 would cut NSF and NASA budgets in half and try to eliminate NOAA's research arm entirely. There's also active efforts to dismantle NCAR, which weather and climate science in this country and all around the world depend on. These aren't abstract cuts, they're real forecasts, real warnings, and real decisions that affect our lives. So before we get started with our speakers for this top of the hour, just wanted to remind you that the House and the Senate are making these decisions right now. There is a link in the video description that will take you directly to a tool to contact your representatives. It takes 2 minutes, and if you've watched any of today's talks and thought, you know what, this does really matter and it matters to me, that's the most direct thing you can do to help. And speaking of talks that matter, I'd like to introduce our first speaker of this time block, which is Michael Diamond, who is an assistant professor at Florida State University and will be talking to us about temperature swings in the Atlantic. So welcome, Michael.
Awesome. Thank you so much. And thank you everyone who is still here on the live stream on this lovely Tuesday morning, and for all the work everyone's doing. So my talk today is going to be about whether humans or nature are the primary cause between some historical temperature swings we've seen in the Atlantic Ocean. Even though I'm presenting this, this work was actually led by my former master student, Tony Frevoletti, who I'll show a little bit more about at the end. So one of the things I've been studying climate change for now, I don't know, more than 10 years. And one of the big things that I really like about climate change as a scientific problem is this challenge of how do we disentangle what is happening naturally in this really dynamic, ever-changing Earth system versus what's being caused by man-made changes to the Earth system from things like emitting greenhouse gases and also particle pollution. So I really like this figure from an overview paper by Clara Desser and colleagues looking at something called a large model ensemble. And I'll talk a little bit more about what those mean. So basically, you have a bunch of different computers running the exact same climate model, but with slightly different initial conditions. So maybe New York's a little bit warmer in one and a little bit colder than one at the beginning. And that totally changes how the weather noise or the weather evolves in each of these different computer simulations, the classic butterfly effect. And over the globe, this doesn't really matter that much. All those little, it's hotter here versus colder here things kind of average out. But for certain individual regions or even whole countries, so this year is showing I think this was about 20 different computers that ran this climate model. So here's the warmest the US could be and the coldest the US could be compared to the average, which you can kind of take as the true signal of what global warming was doing to the US. And we could see quite a bit of a difference over the course of decades just by, how a butterfly flapped its wings at the very start of that simulation. So you can think about it as, well, this computer over here, if you're living in Seattle, you're seeing a crazy ride of warming, versus if you live in this computer, you're really not seeing that much warming. But over the very long term, those will average themselves out as the weather kind of, gets back around. I should mention also this picture is courtesy of my former postdoc office mate, Nicola Marr. So these natural sources can matter a lot. What do we understand about them, and how do we actually go about separating them from other sources of human-driven climate change? So one of the big ones that we care about a lot in the United States, especially the east coast of the United States, is called the Atlantic multi-decadal oscillation. And exactly as it sounds, it's this multi-decade-long oscillation in sea surface temperatures that we've observed over the Atlantic. In particular, we saw kind of this long period of relatively warm Atlantic sea surface temperatures in the 40s to about the 70s, some cool temperatures in the 70s to about the mid-90s, and then since then we've been back on this warmer period. So the big question then becomes, should we expect in the future to go back into one of those cooler periods, or is it just going to be up, 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 up as we keep increasing greenhouse gases? And this matters not just for, general surface temperatures, but also a lot of regional climate issues. So how much hurricane formation we get in the tropical Atlantic is a function of the sea surface temperatures there. So maybe some of the reason we had less historical hurricane activity in this lower period here might be because of this Atlantic multi-decadal oscillation. We've long studied this because of its impacts not only on North American hydroclimate. Here I'm showing some correlation between rain gauges in all these different places across the US and this Atlantic multi-decadal oscillation as shown before, but also African hydroclimate. There's actually a big thought that some of the issues or the same weather patterns that were causing a hurricane drought in the US was causing an actual physical drought in the Sahel region south of the Sahara Desert in Africa. So we really care about what might be causing this temperature pattern and what might happen with it. And as the name suggests, Atlantic multi-decadal oscillation, we originally thought that it was genuinely an oscillation up and down. But more recently, we've come to realize that maybe this quote unquote oscillation isn't an oscillation at all. Maybe it's actually this complicated pattern that's being created from this long-term increase in greenhouse gases that are warming the world and these pollution particles that actually have a cooling effect on the world, especially particular regions of the world. And one of the things that people noticed was that in the red here, I'm showing different time series of different kinds of air pollutants in the US. And for a lot of them, they go up, 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 up. And then we have the first Earth Day, the Clean Air Act, et cetera. Air pollution goes down, actually a huge triumph of environmental policy. But if you look especially at the sulfur dioxide pattern here, especially from like the peak in the 70s and then the decline over there, it looks oddly suspiciously like the inverse of the Atlantic multi-decadal oscillation. And there's some reasons to think that we know from the physics of why sulfur dioxide in the atmosphere can become sulfate particles. Those particles can reflect sunlight directly. They can also get into low-lying clouds and make those clouds brighter and maybe even make those clouds rain a little bit less so they stick around for longer. Both of those reflect more sunlight, cool off the earth, shade the earth, and produce that local cooling, especially over the North Atlantic, where all this North American and European pollution was. So that went up, 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 up until about the 70s and then down, 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 down. So maybe that's actually what caused the oscillation, in which case, unless we really change our air policies, we shouldn't expect to go back into a cool period. So how can we figure out which of these things is right? What is the role of this internal or natural variability and these human causes. Well, Tony and I decided to look at a new-ish, I guess now about 10-year-old technique called low frequency component analysis, which doesn't quite do this, but it's a really clever way that our colleague Robert Wills discovered to separate out modes of temperature variability by their timescale. So this is a kind of toy example where you're just separating out into 3 different patterns or modes. When I say mode, just think pattern. Where one, we have a global warming pattern, relatively uniform warming everywhere. Our last low frequency mode would be our high frequency mode. And by low frequency, I mean slow. By high frequency, I mean fast, would be El Nino. There's going to be a lot of talks on this live stream about El Nino. We understand really well that El Nino is a naturally occurring weather pattern in the Pacific. And you see the red and blue, red, blue, red, blue, red, blue. That's what I mean by high frequency. And in between, we have this Pacific decadal oscillation, which again, like the Atlantic multi-decadal oscillation, multiple decades. So this can separate things out into fast and slow, but how do we know these things that are not as slow as very long-term global warming from greenhouse gases, but maybe something in between, like an aerosol increase and decrease? How could we use this to separate out if that's not just the time scale, but what's causing it? And for that, we're going to add another word to this already too long name of the method: rotated low frequency component analysis. So that is what my student Tony came up with. And it's a brand new tool to try to separate out internal or natural versus quote unquote forced, or you can think about this as man-made patterns of climate variability. If you're familiar with this field, I've actually just spoiled the rest of the talk with this slide. But what I want to show for right now is just what we're trying to do is, instead of just separate this out into slow versus fast, we want to separate it out into forced versus internal. And let me show you a little bit about how we're planning to do that before I explain really what's happening here. And one of the big things is that we're now, we couldn't figure out how to do this with only observations. We do need to go into the world of climate models. So what we're going to do is we're going to use what we call single model initial condition large ensembles. Again, a really long acronym. Has a great acronym, SMILE. So we're going to use these SMILEs. And what these do, again, if you think back to Nicola with all the computers conducting them, we're going to run like 20 different computers of the same Earth with slightly different weather, and we're going to average them out. So, one of them's in an El Nino, one of them's in a La Nina, but when you average over all 20 of them, the only thing that's left is the man-made forcing that's in all of them. So what we're going to do is we're going to figure out the low frequency or long time scale components of those human fingerprints. So we're going to get those different fingerprints that each model comes up with. And I should mention here, actually, all of the models we used here, this wasn't on purpose, but all of them are actually supported by the US federal government in some form. The first two, the Community Earth System Model 1 and 2, are supported by the National Science Foundation via NCAR, or the National Center for Atmospheric Research. For those lucky enough to hear Jen Kay's talk last night, she talked a lot about NCAR and the importance of NCAR, and NCAR's really been in the political crosshairs recently. For those who saw Nother's talk also a little bit later on the previous night, this NOAA model here is from the Geophysical Fluid Dynamics Laboratory, one of our OG modeling institutes. And the last model here is actually a new one from the US Energy Department. So lots of US government support going into this. So what we're gonna do is we're gonna take these patterns and we're going to take from each single realization. We could think about this as like the historical record we get. We don't have 20 Earths. We only have one Earth. We only see one example of how the flap of the butterfly's wings change things. But we can take each of those individual computers just like that and see, okay, what if we rotate out, or basically take the signal out of those forced patterns, which we have in the red here, and then we're left with what we have in the blue, this on-forced time series. Can we use that on each of these individual ones and actually get the right answer or not? And unlike in reality, we know what the right answer is here because we can average over all of these ones. So one reason we actually think that this works is that when we try to extract the forced versus unforced pattern out of these 20 different members for each of these models, I'm just showing one of the models here, but you can do the same thing for all the other ones. What we think is the forced or the man-made response correlate with each other really nicely. So that's shown in the dark red colors over here. The mean correlation is about 90.95, almost 90% similarity between them. For what we think is the unforced or random weather noise part, you could see it really does look random. The mean correlation is about 0, and there's just as many that look the opposite of each other as the same as each other. All members of each 4 of these models agree with the general answer. So I should mention here, in gold, we have the true value for what is the forced component, and the purple, we have the true value, which we get from averaging over the whole ensemble or using the whole ensemble. Each of these individual dots are what each individual realizations, like what each individual historical period would tell us. What we could see here is that, well, first of all, all of the 4 models agree that the Atlantic multidecadal oscillation, which maybe we shouldn't call oscillation, variability, is mostly man-made. And importantly, every single realization would give us that answer, even though there is quite a bit of scatter. Also importantly, if we look at the Pacific, which we believe is mostly natural or internal, this method gives us that answer, that they are mostly internal. So it's not like this method just has all of the signal always in the forced and will just always tell you that things are forced. So if we then go ahead and apply that to the observations, so this first row here is our actual observations, what happened in reality. We can separate that out. And if we use these reference patterns from each of the 4 different models, we don't know which one is closest to reality, but we can kind of look at all of them together. All of them agree that historically the Atlantic is mostly forced and the Pacific is mostly internal, although with maybe a mix, but basically no internal signal in the Atlantic. So we should not expect to actually go back into a cool period. We really should just expect the Atlantic to continue warming at this rapid pace, which is really important for thinking about how we actually respond and adapt to climate change. And before I wrap up and take questions, I just want to quickly thank and recognize that this work would be impossible without support from, including financial support from the federal government, particularly NOAA's Climate Program Office here. And they supported me, but more importantly, they support students. As Craig mentioned earlier, one of the things at the chopping block, if we do have these grant cuts, would be grant funding to universities. And that's kind of like eating our seed corn, right? That's how we actually support these master's and PhD students to do this work and become the next generation of scientists. So with that, thank you so much for listening, and I'm happy to take hopefully a couple of your questions.
Thank you, Michael. That was great. We'll have time for just one quick question. Some folks we're looking at your AMO chart, and we have 2 questions related to that chart. The first one from What Is My Life 6927. It looks like temperature drops in the past were greater than the temperature rises. Do you have any comments or notes to add up on that line?
Yeah, that's a really good observation. So part of this is we're defining anomaly relative to some period. So that might be a little bit of an artifact of just where we decided to put our period to kind of make things look relatively equal. One thing you could see at the end here is the temperature is going up right now, and we would expect if we kept that baseline the same that we're going to get warmer and warmer and warmer.
And a follow-up question to that is that someone noticed a temperature spike in what looked like the 1960s and 80s time period. Do you have any comments on that spike, or is that related to any of those other items you spoke about earlier?
1960s and 80s. Okay, I'm unfortunately not entirely sure what folks are looking at there. I will mention that the values I'm showing here are kind of smooth, so we get rid of a lot of like year-to-year things. But one of the things we actually can see is sometimes when volcanoes go off, even though they're relatively fast climate signals, because the pattern looks like the small pattern, we actually do correctly note that. So like when Pinatubo goes off in the 90s, we actually do get a small blip, and we are able to accurately say that that's a forced signal, not man-made in that case, but forced, not natural.
Got it. And we are short on time, but there is one really important question that just came through. Since natural variability and force variability also feed on each other, is it okay to try and separate them?
Yeah, so that is one of the biggest sources of uncertainty in here, is how do we actually cleanly separate out forced and natural uncertainty? And maybe they, do feed on each other. So it's really tricky to be able to sort out, but we do really want to know what is going to happen in the long-term future and what should we expect to keep happening. So I think it is important to try to get at these signals.
Great. Thank you so much, Michael. I hope you have a great rest of your day and keep the good science going. All right. Before our next speaker joins, a quick reminder, the U.S. Weather and Climate Science is the foundation for forecasts, warnings, public health guidance, and millions of people depend on this every day. This foundation is under really big pressure right now from the proposed budget cuts and agency changes. If you want to do something about it, there's a link in the description that will guide you to call your representatives. There is a script there to make it as easy as possible to call and tell them that this matters to you and how important it is to the U.S. population. All right, and now let us go to our next speaker, who is Martha Buckley, and she is a research professor supported by NOAA, NASA, and NSF, which she'll also be talking about some ocean drivers.
Thank you so much to the organizers. Can you hear me okay? So today I'm going to be talking about the ocean, and I'm going to call it the Great Integrator. This work was supported by the NSF Physical Oceanography Program, like many other researchers here. So this figure shows the heat accumulated in the climate system due to anthropogenic forcing over the period 1960 to 2020. And shown in blue is the heat that has been stored in the ocean. And it's obvious from this figure that the majority of the heat added to the climate system has so far been stored in the ocean. And the reason the ocean is able to store this heat is because of its high heat capacity. Sort of less well known is the role of the ocean heat capacity in internal climate variability. So those are the variations of the climate system that happen in the absence of anthropogenic forcing or other like solar forcing, which we consider external to the climate system. So in the extratropics, sea surface temperature variability can to large degree be explained by the integration of stochastic or random atmospheric forcing by the ocean mixed layer. And so this is shown in this toy model here. The black shows the stochastic atmospheric forcing, and the blue and the green curves show the ocean response, the sea surface temperature response, for mixed layer depths of 50 meters in blue and 500 meters shown in green. So it's apparent that the ocean responds on longer timescales than the atmospheric variability, mostly due to its high heat capacity. And the response is at lower frequencies, meaning longer memory, the deeper the mixed layer depth is. Okay. So to understand this response of the atmosphere, of the ocean to stochastic atmospheric forcing, I would like to consider a case study, which is the response of Atlantic sea surface temperatures to the North Atlantic Oscillation. The North Atlantic Oscillation is the most energetic mode of wintertime atmospheric variability over the North Atlantic sector. For a positive phase of the NAO, shown here, the Azores high and the Icelandic low are both anomalously strong. As a result, the jet stream is anomalously strong and displaced polewards. For a negative phase of the NAO, both the Azores high and the Icelandic low are weaker than usual. The jet stream is weaker than usual and more zonal. Shown here is the time series of the NAO, and to first order, the NAO can be understood as white noise forcing. So the NAO leads to a distinct spatial pattern of SSTs, or sea surface temperature anomalies, which is shown here. During the positive phase of the NAO, the winds are increased in the tropics and in subpolar regions. This leads to anomalous heat fluxes out of the ocean and cold sea surface temperatures. During the positive phase of the NAO, winds are decreased in subtropical regions. This leads to anomalous heat fluxes into the ocean and warm sea surface temperatures. So this is called the North Atlantic Oscillation Tripole, because it looks like there's 3 lobes, right? So tripole of sea surface temperature anomalies. Okay, so far I've just described the response of the ocean mixed layer that's fixed in time to stochastic atmospheric forcing, the NAO in this case. However, in the real ocean, of course, the mixed layer depths vary seasonally. So mixed layer depths are much deeper in the winter hemisphere. Okay, so here it's northern hemisphere winter, and here it's southern hemisphere winter. And then they're shallower in the summer hemisphere. So zooming in on the Atlantic, we can see that in March, there are very deep mixed layer depths on the order of 500 to 1,000 meters. But in September, the mixed layer depths are much shallower, less than 100 meters. And then, of course, the ocean has very strong currents, and those are also important to climate variability and variability of sea surface temperatures. Shown here is a still of a movie, which is really great, that you can see from the NASA Goddard Space Flight Center. And the lines show the strength of the ocean currents. So you can see the northward flowing Gulf Stream here. And where it separates from the coast at Cape Hatteras, it has strong meanders and eddies. And so variability, the Gulf Stream, both its strength and its position vary in time. And that's very important to sea surface temperature variability. So now I'm going to discuss a little bit of my work trying to understand the role of both one-dimensional and three-dimensional oceanic dynamics in sea surface temperature variability, specifically the NAO tripole. And so in this work, we used a hierarchy of coupled models based on the NCAR Community Climate Model version 2, CSM2, to understand the roles of various ocean dynamics in sea surface temperature variability. And so in all of these models, the atmosphere, ice, and land models are the same, but the ocean models have different complexity. So people are probably familiar with NCAR's contribution to CMIP6, the Coupled Model Intercomparison Project, and also the IPCC AR6 report. But you may not know that NCAR actually provides its climate model to researchers and provides computational resources for these researchers to run the model themselves for process studies, etc. And so this work is made possible by NCAR, which, as you know, is in danger of being sort of cut/eliminated, which is very disturbing. Okay. So to the science a bit more, we have 3 different ocean models of various complexity. One is the full ocean model, which you are familiar with. So it has all ocean dynamics, including 3-dimensional ocean currents. Now I'm going to describe the simplest model. This is called the slab ocean model. And in this model, the atmosphere only interacts thermodynamically with the ocean, which has a layer depth that is fixed in time. Of intermediate complexity is this multi-column ocean model. It simulates one-dimensional ocean processes through these columns, but it does not have 3-dimensional ocean dynamics, meaning currents. And importantly, this model includes it concludes mixed layer depth variations, including the seasonal cycle of mixed layer depth that I just described. So what I'm going to do is I'm going to be looking at the response of the ocean to the North Atlantic Oscillation in these 3 model configurations. So first, I'm going to compare the slab ocean model to the multi-column ocean model to show the impact of one-dimensional ocean dynamics on sea surface temperature variability, specifically the role of these seasonal mixed layer depth variability on the response of the ocean to the North Atlantic oscillation. So the figure on the left shows the response of this slab ocean model, which is just interacting thermodynamically, to the North Atlantic oscillation. So you can see this classic NIO tripole. The plot on the right shows the response of the multi-column ocean model to the North Atlantic oscillation. Recall that this multi-column ocean model has this seasonal cycle in mixed layer depth. And so you can see, comparing the magnitude of these, that this one-dimensional ocean dynamics actually reduces the variance of the NAO tripole. Now, if we look at the time series, and I've also looked at power spectra and autocorrelation functions to confirm this, we can see that one-dimensional ocean dynamics actually enhances the memory of the NAO tripole. So now I'm going to explain why this is the case. Okay, so first, why do one-dimensional ocean dynamics damp the response of sea surface temperatures anomalies to the NAO? Okay, so in order to understand this, you need to think about the seasonal cycle of mixed layer depth, which is deeper in the winter and shallower in the summer. So if we have a SST anomaly sitting here in the summer, and the mixed layer starts deepening, we can see that fluid will be brought up. Fluid that was not originally in the mixed layer depth is brought up, and that will damp the SST anomaly away. So this explains why the response to the NAO is actually weaker in the multi-column ocean model, which has this seasonal cycle in mixed layer depth. Okay, so now why do one-dimensional ocean dynamics enhance the persistence of the NAO tripole? Okay, so again, here's our seasonal cycle in the mixed layer depth. So imagine we form an SST anomaly in winter. When the mixed layer shallows in the summer, this anomaly can be isolated beneath the seasonal thermocline, and it can stay there during the summer. And when the mixed layer depths increase the following winter, it can be entrained. This process is called reemergence, and it enhances the memory of sea surface temperature anomalies. So now we can understand why one-dimensional ocean dynamics has both reduced the amplitude of the NAO tripole, but enhanced its memory. Okay. So as a final comparison, I want to understand the role of three-dimensional ocean dynamics in modifying the NAO tripole. So as a result, I'm going to compare the response of sea surface temperature in the multi-column ocean model, which lacks 3D ocean dynamics, to the full ocean model, which of course has three-dimensional currents. So on the left is the response of sea surface temperatures to the NAO in the multi-column ocean model. You can see the classic NAO tripole forced by air-sea heat fluxes. The plot on the right shows the response of the full ocean model to the NAO. You can see that the SST pattern has changed in its centers of action. In particular, a positive phase of the NAO leads to a northward shift in the Gulf Stream path and strong SST anomalies along the North Atlantic current here and in the central subpolar North Atlantic. Additionally, looking at the time series, we can see that ocean dynamics enhance low-frequency SST variability. Okay, so to conclude, I wanted to show you that most of the extratropical sea surface temperature variability can be understood as the response of the ocean to stochastic or random atmospheric forcing. A primary example of this is the tripolar sea surface temperature anomalies due to the North Atlantic oscillation. One-dimensional ocean dynamics, primarily due to the seasonal cycle of mixed layer depth, damp the NAO tripole. Three-dimensional ocean dynamics, primarily currents, modify the response of sea surface temperatures to the NAO. A positive NAO leads to a northward shift of the Gulf Stream path. This change in ocean currents leads to sea surface temperature anomalies along the separated Gulf Stream path and in the central subpolar North Atlantic. And I would like to acknowledge that NCAR is essential for the work of atmosphere, ocean, and climate scientists in the US and across the world. My work would not be possible without NCAR, nor would the work of many other researchers, as well as the work of people interested in climate projections and predictions. Thank you.
Great. Thank you so much, Martha. That was an excellent presentation. So one of the comments we had was that that beautiful image from NASA Goddard that you shared, that the swirls seem much bigger next to the coast. So I'm hoping maybe you can comment on what those swirls are, those eddies are, and what their role is in moving the temperature and what their role is in the ocean dynamics.
Okay, so after the Gulf Stream sort of separates from the coast, it sort of becomes unstable. And so it can meander, and there's these large eddies. Those eddies do transport heat. And so they are important. It is, it's interesting to note that, the coarse resolution models don't represent those eddies as beautifully as shown in that picture. So I'm actually interested in applying some of this work to some higher resolution models as well, because you should go see the movie. I didn't put it in because it was a little choppy, but there's a beautiful, if you search this image from NASA Goddard, there's a wonderful movie that shows all over the ocean these currents changing with time.
Great. We also have another question from Hannah Palco 2307. What consequences could we expect from that northward shift?
The northward shift in the Gulf Stream. Okay, so if the Gulf Stream shifts northward, the Gulf Stream carries a lot of heat, right? And so if you shift the Gulf Stream northward, you get a very large sea surface temperature anomaly. So if you shift it northward, what used to be cold subpolar water is now replaced by warm subtropical water, and you have huge sea surface temperature anomalies. So actually, that's actually why, when I compare models without three-dimensional ocean dynamics to ones with, not surprisingly, the biggest difference in the Atlantic is the changes in the Gulf Stream path.
Great. And one last question for you before we move on. What is my life 6927 is asking, how is this data collected across such large areas? I know we had one Argo float talk yesterday, but is there anything else or anything more you can talk about in terms of data collection for this kind of work?
Okay, so the direct comparisons that I showed were model-based. However, the start of my talk was sort of all observation-based. And so those observations were sort of, so let's see, there's Argo that observes the ocean. There's also altimetry, which measures the surface of the ocean, which is very important for ocean currents. And then there are assimilating models that can be run at high resolution that assimilate the ocean data, but also have a model to make the dynamics consistent. And so that is another piece of, estimating what the ocean is doing through time.
Great. Thank you so much, Martha. It was such a great pleasure to have you speaking here on the live stream. And we'll be moving on to our next speaker. While she gets set up, let me just kind of remind you all why we are here. If you've been here a while, thank you. If you're new to the stream, welcome. And we are here because the weather forecast you checked this morning depends on a network of weather stations, ocean buoys, weather balloons, aircraft observations, and satellites that took decades to build. And that network, the foundation of everything else, parts of it are quietly being allowed to erode right now. And it's really a big deal, not just for the scientific community, but for everyone, internationally and here in the United States. So the House and the Senate are making decisions right now on the fiscal year 2027 budget, which is currently looking to cut the funding for these types of measurements and observations. There is a link in the video description that will take you directly to a tool to contact your representative to tell them how much this matters and how much it matters to you. And so that is the best way you can support the continuation of this science. All right. Our next speaker is Dr. Sydney Kramer, a postdoc climate scientist at Lamont Doherty Earth Observation, and also my sister. So once again, you get a brief moment of both S. Kramer doctors on one stream. Good morning, Sid.
Morning, guys. I'm happy to be back and super happy if anybody came back from me hosting yesterday. Really excited to talk to you today about hurricanes and definitely pointing out our middle initials are important because we are both, in fact, S. Kramer. Can you see my screens?
Yes, we can. Take it
awesome.
away.
Okay, so like she said, my name is Sydney Kramer, and I currently work at Lamont Doherty Earth Observatory at Columbia University. And I started doing tropical cyclone risk research when I came to Lamont in February of 2025. And I am lucky enough to get to work with Adam Sobel, who started off this whole live stream, and Susanna Camargo and Chai-Ying Lee. That storm back there is Hurricane Michael in 2018, a Cat 5 that hit the Panhandle, and you'll see a couple examples of that through my talk. So hurricanes need a really specific set of environmental ingredients to form. Just like baking a cake, if one ingredient is missing, the storm might struggle to develop or it might weaken quickly. And first, hurricanes need warm ocean water. As water evaporates from the surface, it's able to rise into the atmosphere and releases heat when it condenses into clouds and rain. And that heat provides the energy that powers the storm. Storms also need to form away from the equator, where Earth's rotation helps them spin and organize. We also need low vertical wind shear, which is the change in wind speed or direction with height. And strong wind shear can tear storms apart and prevent them from organizing. Hurricanes also require moist air. Dry air can really weaken storms, and moist air really helps them continue growing. The atmosphere also has to be unstable, which means allowing warm air to rise easily from the surface higher up, and that fuels development. And then finally, hurricanes usually begin with a pre-existing disturbance, such as a tropical African easterly wave or a cluster of thunderstorms that can organize if the other ingredients are favorable. So we've talked about the environmental ingredients that hurricanes need, and climate models, also commonly known as general circulation models, are able to simulate these conditions across the globe. And to do this, the Earth is divided into a three-dimensional grid. And at each grid point, the model calculates the physics of the atmosphere and ocean, which means that a finer grid is the same thing as saying higher resolution. And rather than simply describing climate patterns, these models are actually able to solve the physical equations that govern how the atmosphere and ocean evolve over time. And climate models are fundamentally built on all these physical equations, just like these. And you don't need to understand any of these scary equations here. But the important point is that they describe how the atmosphere and ocean move energy, moisture, heat, and momentum around the planet. And because these models are based on physics, we can change things like greenhouse gas concentrations or ocean temperatures, and we can simulate all these different climate states, whether they be past, present, or even the future. And that allows us to ask really important questions, such as how might hurricane environments change in a warmer world, or how could coastal risk evolve in the future? And I know we've talked about this a lot throughout the whole live stream, but running climate models requires an enormous amount of computational power. And the National Center of Atmospheric Research, which is under threat, develops and maintains the Community Earth System Model, often called CESM, which is one of the most widely used climate models in the world. CESM is publicly funded and publicly available to all, meaning researchers across universities, government agencies, and the private sector use it for climate and hazard research. Importantly, these models and experiments are typically run on NCAR's supercomputing infrastructure known as derecho, which you can see here on the left. And this kind of research and development is only possible because of the sustained federal investment in scientific institutions, climate modeling, and high-performance computing infrastructure. And it's really integral in our weather forecasting, risk assessments, infrastructure planning, and climate resilience efforts. If you'd like to learn more about NCAR and why it matters, if you're not getting enough from the live stream, there's a QR code in the upper left corner that links to a great short video also made by this group, and I would highly recommend checking it out at some point after the live stream. So climate modeling capability has advanced really dramatically over the past few decades. On the left, you can see how model resolution has improved over time. And in the early 1990s, climate models had grid cells hundreds of kilometers wide. Today, models can represent much smaller atmospheric and ocean features with far greater detail. And so they've become also more sophisticated vertically. So we have a higher resolution in the vertical as well, with many more layers in both the atmosphere and ocean. And these advances together are especially important for hurricane research because hurricanes are relatively small compared to the size of our planet. And as model resolution and physics improve, so does our ability to simulate hurricane environments and other extreme events. The trade-off can be that higher resolution models do require substantially more computing power, and thus they cost more to run. So even though these climate models have improved enormously, like I said, hurricanes are still really small-scale features. And so often we need to get to even finer spatial scales than what we can get from the global climate models, or directly or get to a finer scale than we want to pay for to produce with a full global climate model. So we can do something called downscaling, where we use the environmental information that's simulated by the climate models all the way on the left, and we downscale from those large-scale conditions to simulate the kind of hurricanes that could realistically develop in that environment. So in the middle panel here, we're able to identify hurricane-favorable environments from the global climate models, where storms can form, where they're likely to travel, and how intense they can become. And then all the way on the right, we're able to generate thousands of physically realistic synthetic hurricane tracks. So these are storms that could happen in these environments but haven't been observed. And that's really important because our historical record for tropical cyclones is relatively short. And that's especially true for rare extreme events, maybe some events that haven't actually occurred yet. And synthetic storm modeling allows us to estimate hurricane risk beyond the storms we've directly observed in the past. And so just a shout out to the Columbia Hazard Model, which is most of what I use now at Lamont Doherty, which was produced originally by Chiang Lee. And it's a really, really cool resource and publicly available on GitHub. So once we've simulated realistic hurricane tracks, we're able to model those hazards that the storms produce. So again, this is an example using Hurricane Michael from 2018. And hurricanes are really complicated because they rarely generate just one hazard, right? They can produce damaging winds, flooding from rainfall, storm surge, and these all often interact together as compound hazards. So this example is generated using an open source storm surge model known as GeoClaw, which was originally developed and is still used and maintained with federal funding. And on the left is the hurricane wind field as the storm approaches the coast. And those winds push water towards the shore, which produces the storm surge, which is an abnormal rise in sea level during the storm. And then shown on the right, we can see the storm surge that results from those winds. So in the northern hemisphere, hurricanes rotate counterclockwise around a low pressure center, and a hurricane is an intense low pressure center. That rotation is important because the winds on one side of the storm push ocean water toward the coastline, and then on the other side, it pushes water away. So the red colors show where water levels rise above normal sea level, and then blue is where they're being pushed offshore. So these physics-based simulations help estimate coastal flooding risk from storm surge generated by hurricanes. Similarly, hurricanes also, like I said, produce really damaging winds and extreme rainfall, which can interact with storm surge. And on the left is the simulated hurricane wind field using a model called COAMPS-TC, which was developed and is maintained by the US Navy at the Naval Research Lab, as well as NOAA. And it's used widely by civilian and military forecasters. The strongest winds are typically located near the eye wall surrounding the center of the storm. And those winds can cause widespread structural damage, power outages, and falling trees, causing a lot of damage to people and property. And on the right is the simulated rainfall footprint associated with the storm track. And that's using something called TCR, which is a parametric rainfall model that was developed originally by Carrie Emanuel at MIT. But as hurricanes move inland, like I said, they can produce these very large amounts of rainfall over really broad regions. And that can lead to flash flooding, river flooding, and long duration inland flood impacts. So it's not just coastal towns that we're concerned about for tropical cyclones. And a coastal community may experience a combination of all of these hazards throughout the life cycle of the storm. So these hazard events really need to be broken down into all of their individual components to figure out what our biggest risks are. And these compound hazards become risk when they interact with people, infrastructure, and vulnerable coastline environments. So the figure shows how flood risk can vary across coastal communities depending on things like elevation, their distance from the shoreline, what kind of wave action is happening, and flood protection infrastructure that's already been built. For example, the same hurricane can produce very different impacts depending on whether homes are elevated, if those flood defenses already exist, or if the communities are located in low-lying coastal areas. So these modeling tools help us better understand and identify the evolving hurricane risk for coastal communities. And also understanding this risk is important because these results are used well beyond academia. So these types of climate hazard and risk modeling tools support decision-making across many different sectors. For example, government agencies and emergency managers use them for disaster preparedness and evacuation planning. Coastal planners and engineers use them to design more resilient infrastructure. And the insurance, reinsurance, and finance sectors use these models to better understand and manage risk exposure. So these diverse sectors and stakeholders really rely on publicly available scientific resources, as well as climate models and federally supported computational infrastructure. So as hurricane environments and coastal conditions continue to change, these modeling capabilities become increasingly important for improving the resilience and preparing for future risk. So I'll just leave these key takeaways up. But basically, to conclude, hurricanes form from really identifiable environmental ingredients, and climate models are able to simulate those large-scale environmental conditions and ingredients across the planet, which help us better understand the environment that's able to support these hurricanes forming. And using those simulated environments, we're able to generate synthetic hurricane tracks, or hurricanes that haven't actually happened yet in the real world. And by combining those tracks with hazard models, we can better understand how storm surge, rainfall, and wind hazards may impact communities. So these methods now support real-world applications in sectors that help drive the U.S. and global economy and inform resilience that can save property and lives. And lastly, I just want to say none of the work that I've done throughout my entire career, undergrad, grad school, and now, could be done without the resources from NCAR. So it's really important, and reach out to your representatives. Thank you.
Great job, Sid. That was amazing. Every time I hear that you talk about hurricanes, it just brings me back to our time in South Florida. And I did think it was really interesting that you commented on the different resolutions. And I think it's really interesting, between us, we have 5 academic years difference. And back when I was in grad school, the resolution was the entire state of Florida could have been one grid cell. And then looking about the investment that the federal scientists and the federal science resources have made to improve that resolution so you can fully see a hurricane, which to many of our viewers probably seems really, really large, is considered a small scale. So can you talk about how the federal investment to improving resolution, improving those computing resources has benefited the research capabilities today?
Absolutely. And while we use these downscaling efforts, we actually now do have models that are at high enough resolutions to directly simulate hurricanes, which is incredible. Something called, very fun name, high-res MIP, we call it. There's different model intercomparison projects that have really high resolution runs. And so there's all of these new tools that are becoming available to us to study these tropical cyclones. And this is a really, really costly hazard. And so I just want to stress, yes, there has been a lot of public investment into these tools that's helping guide this research. But the economic output from that investment is so large because, again, so many private sectors really rely and use this data. It generates millions of dollars, and these storms are generating billions of dollars in damage. So, I'm sure a lot of the people on this live stream that are in southeast the US, you felt the panic of a hurricane coming towards you, and watching, Jim Cantori out there, and, we all know the importance of what we're dealing with here. So it's a really important thing to keep investing in. And it's also, important to state again that investment is coming back to us tenfold.
Great. We also have a few comments directly from the chat. Cambrian Anopakaris, I apologize if I mispronounce that, asked, does a hurricane hitting a thunderstorm or other rainstorm make it worse? And I think this goes back to your ingredients discussion.
Yeah, so like I said, a lot of these tropical cyclones form from a cluster of thunderstorms or from a pre-existing disturbance, and those storms are all kind of able to get wrapped up and integrated and joined together and create the hurricane itself, right? It sort of pulls from all of that disturbance and all of that moisture to create one big massive storm or one stronger storm. And where was I going with this? I lost my train of thought. But
Energy.
yes, energy, right? You're kind of you're building off of that, and as it's moving, it's sort of sucking all of that up from what's going on around it. So yes, to answer your question, more thunderstorms and more stormy weather do add to a hurricane.
Great. We have 2 more at this time. People are really excited about this topic. From Sydney Linquist, 8243. Is there an upper limit where a hurricane will never be able to become stronger beyond a certain point, or does the warmth enable them become bigger over time continuously? That's a tough one.
That is a tough one. And I definitely want to say that it is my firm belief that storms are definitely able to get stronger than what we've ever observed in the past as we move into the future in a warming world. As more heat becomes available from sea surface temperatures, storms can get stronger. And so this is one of the big things we're looking at. But I also want to say it's a lot more complicated than that. There are a lot of other factors, right? Like those list of ingredients. There's certain things that could be changing that could be helping hurricanes, but there's also other conditions that might be changing that hurt them. Things like maybe we have warmer sea surface temperatures, but we have an increase in vertical wind shear. Just like in the case, hopefully, this year going into an El Nino event, we tend to have more vertical wind shear in the Atlantic, and that kind of hinders storms from forming. So there's a combination of things that we want to look at, and it's not all linear. We also look in the Pacific, right, where they're called typhoons, and it's not like hurricanes everywhere are necessarily getting more frequent or stronger. That is true in some places, but not everywhere, and there are trade-offs. Some places are getting less favorable as well.
Great. All right. One more question for you, Sid. Does your work contribute to improving models, or does your research focus mostly on using the models themselves? And that is from LEB 119.
A little bit of both. So currently, there's just absolutely incredible work coming out of Columbia with Chai-Ying Lee's Columbia Hazard Model. She's doing a ton of work, constantly iterating it, making it better, using different statistical methods and different bias corrections. So most of the work I'm doing is helping tweak how we use the output most usefully, but I'm not exactly developing the model itself. That was already done and is continuing being done by the mastermind herself, Chai-Ying Lee. So I really recommend looking at her work. She's fantastic.
Great. And we do have a comment from Adam about what it's like to have siblings in the same fields, and the fact that we both studied at the U, and our love of tropical weather. I will say it is interesting because we have the same initials as Kramer, which is why we have to use our middle initials in our publications. Otherwise, it would look like we accomplished a lot of work in the last few years. But really, it's amazing to be able to have a bit of like family legacy involved in the work that we do, and just be able to bounce ideas and find connections. I think it's pretty clear that we work on very different topics. Sid with hurricanes and hazard models, with a lot of ocean drivers, and I focus on wildfire, smoke, and aerosols. And we have found connections in our work together, which is really, really amazing. Sid, did you have anything to add?
Yeah, I always say, Sam kind of does the dry stuff and I kind of do the wet stuff. And it's been really cool having really different focuses. But now that I'm working back on hurricanes and she's working on wildfire, we do have this shared interest in hazard and risk with extreme climate events. And it's been a really cool thing to sort of have like a super network, right? If something in my work comes up with wildfire, I have a million people to ask, and vice versa for her. So that's been great. Occasionally we get the wrong email because somebody sent it to the wrong S. Kramer. But it's really crazy. Just so if people are curious, our parents were not in this line of work. They were not scientists at all. And our dad didn't even finish college. So Sam and I just kind of stumbled both into this, and it's been really cool. We definitely have really interesting dinner table discussions. So it's been great.
Thank you so much, Sid. And I will say we do have a visit from one of the cats. This is Miss Catalina. So this is the first cat against science cuts.
Yes.
And also, Miss Catalina loves Sydney very much and likes to sleep on her pillow.
She's the best. Thanks so
All
much,
right.
Sam.
Thank you so much for joining us, Dr. Kramer. All right. That was an awesome moment for us all. So before we move on to our next speaker, I just want to remind us all why we're here. Like I just mentioned, I study wildfire and smoke for a living, and one thing my research makes very clear is that the science infrastructure behind wildfire forecasting, evacuation planning, and smoke health guidance, it's a chain, and every link matters. So federal forecasts feed those state warnings and local evacuation orders to help people get out safely and help protect their health against smoke that doesn't stop at any border, that does go state to state and internationally. And right now, the investment in those chains is under threat. Again, we have weather stations that are short-staffed, climate labs are being shuttered, and the budget cuts that are proposed for 2027 would really hinder and impact all of this really important science that impacts each one of us on a daily basis. So once again, there is a link in the chat. It will take you directly to a tool to contact your representatives. There's even a script if you don't know what to say, but just letting them know that this matters and is important to you is extraordinarily helpful for us all. All right. I will now get a chance to introduce our next speaker, which is Samia Kirshner, who is an associate professor of architecture and urban design at Morgan State University. And she'll be talking about seascape urbanism. So welcome, Samia.
Hello, everyone. Thank you for having me. It's been really nice to hear Dr. Sidney's work. I'm an architect by profession and practice. I do a lot of urban design practice, but I also teach, and I've had a privilege to teach in many beautiful port cities. I'm hoping you can see the slides and hear me clearly.
Yes, we can hear you.
Okay, I wasn't sure. Yeah. Okay, all right. So right now I'm in Morgan State University in Baltimore, which is a port city. I've lived in Sharjah as well as Honolulu and Karachi. I'm originally from Pakistan. And water has always been a source of inspiration for my design and research. So in design, I always respect the terrain, because my research shows that when you disrespect the terrain, the water will take over. I've also in my research, I look at urban flooding and the causes and the root causes of it and how to prevent it through design. And I also look at the impact of dams on regional watersheds. So that's my research. In my teaching, I ground all my teaching in my research so that the students can understand how to ask a research question, hunt down a relevant methodology, and produce assignments that can lead to future grant writing. So all of my teaching, whether it is a seminar course, whether it's a capstone project, or a studio, urban design studio, is all grounded for the moment in Central Park Heights since I joined Morgan State University. The reason for that is that the Jones Falls, which is a river, one of the three main rivers that runs through Baltimore City, is a very important urban watershed. It contributes to the urban watershed and then ultimately to the health of the Chesapeake Bay. While Baltimore is very well known for its waterfront, I am of the opinion that water does not have a front or a back. It just flows from higher ground to lower ground. And the more work we do in the higher ground, the better the result will be in the lower ground. So when I moved to Baltimore, there was a lot of research that was happening. My colleague, Dr. Lawrence Brown, had just finished his book on black butterfly, which shows how disinvestment in certain African American populated neighborhoods has created disparities at the urban scale in Baltimore City. It just happened to be that the parts that he was identifying as the black butterfly, the shape of the butterfly that he noticed and contrasted with the white L, where predominantly white neighborhoods are in a much better condition and state of affairs. So he historically traced this current condition with the redlining map, the HOLC map of 1920s, which actually earmarked African American populations as neighborhoods that were not safe to provide loans in. So the federal authorities had actually mapped out where banks should not give loans, and if they do, they will do it at their own risk. So that redlining has impacted Baltimore's current state of affairs. It just happened to be that the area that I wanted to focus on happened to be in the black butterfly. It is the largest vacant lots and vacant properties in the city. And it also, my interest as an environmental scientist was that it was also at the highest plateau, straddling two watersheds. So Central Park Heights is at 480 feet above sea level, and it has the largest vacant lots. It also faces extreme flooding when it rains. And the flooding is not just from the watershed, but also from the basement. The basement water, and I believe it or not, I've actually tasted the basement water, it has salt in it. So there is a lot happening that we are documenting and looking at the location of flooding, identifying the core area where the flooding happens and looking at the drainage and really carefully plotting what is the cause of this flooding to understand, and then get to urban design and really do the work that needs to be done. So the Jones Falls watershed is failing water quality grades because of the storm runoff and also very industrial and commercial hardscapes that contribute in that area. Because when there is vacant lots, industries come in. And in Park Heights, the story is visible in the flooded blocks and the pollutants that come into the Chesapeake Bay from those flooding. So what we started doing is really identifying the core assets in Central Park Heights and locating our efforts there, identifying the vacant lots. And you can see the largest vacant lot is in Plantation Park Heights Urban Farm. These are residents who have taken over vacant lots and created urban farms. And during the COVID, they fed 300 families just through volunteer efforts. Here is what the farm looks like. And since the COVID, I have actually started doing a lot of urban design studio work into this farm so that we can help support them in any way we can. So it's really a socio-environmental aspect of my work at Morgan State University. I'm also part of the Baltimore Social and Environmental Collaborative, which is across 67 scientists that are working in 5 different universities, coming together to really look at Baltimore and its conditions so that we can monitor its urban heat index, storm water flooding, as well as climate impact of climate on the residents. So our basic goal is to really look at the watershed in a holistic way, provide urban design and architectural expertise to neighborhoods so that they have access to the watershed. If they can see the water, they will be better custodians of water. We have actually put in place a lot of monitoring devices along all the urban farms that are coming across the city, along the watershed, and the monitoring is helping us see how much stormwater mitigation is happening and how can we increase that and what has its impact been on the Chesapeake Bay. I will end here and open the floor for any questions, if there are any.
Great. Thank you so much, Dr. Krishner. We have definitely gotten some questions.
Oh, good.
Yeah. So one of the first, I'm going to generalize slightly, but Cambrian also asks, I've heard that the air quality is markedly worse in disadvantaged communities, but they didn't realize that water is also worse. So can you just talk briefly about that disparity?
Sure. So this disparity definitely is there. I think the issue is that, we just completed and published a joint paper on air quality, and it was really critical that not only is air quality worse, there is monitoring apartheid. My colleagues like to call it monitoring desert, but I don't like the word desert because desert happens in nature, but this is by design. So there weren't any monitoring devices in the red line, what my colleague Dr. Brown calls the black butterfly. We installed those monitors through the BSEC grant, that's the Department of Energy grant, that was given to Johns Hopkins, and Johns Hopkins created a consortium of 5 universities. So we are spearheading the community engagement because communities don't want to be monitored. So we took 3 years to build trust with communities to put in place the monitoring devices that can actually lead to the conclusion that yes, air, water, and food are critically less available in the divested neighborhoods than the rest of the city.
Great. Thank you so much for commenting on that. It's really important. We have another question from, well, I'm not going to attempt to pronounce that. Tyvri Mad Mayhem. Do you interact with the EPA? Does the EPA play a role in regulating the water and the water quality in the Chesapeake Bay?
Yes, the EPA does a lot of monitoring itself. The state of Maryland also creates a Chesapeake Bay water report. And then we have at the local level, Blue Waters Baltimore, BWB. And we work with all of these 3 agencies. And it's things that I'm learning, and I'm an architect, I'm not really a biologist, but I'm learning things about, we were so excited that Jones Falls, because of the Friends of Jones Falls, we go there and clean. Now the urban farmers are also keeping the Jones Falls clean. And it was just a very exciting day for us to see an American eel. And I had no idea that the American eel, because I'm not a biologist, I did not know, or a zoologist, I did not know that the American eel goes all the way to the Bahamas to spawn eggs. And then the small baby eggs swim all the way back to Jones Falls. It's an amazing story, and to not have eels, and the biologists that were working beside me, Dr. Stan Kemp, he basically said that I haven't seen in 25 years, I haven't seen an eel. So things are improving and there is hope, but to keep the hope alive, there is a lot of work that needs to be done.
Okay, we also have a question from Hannah Pelko. Has there been any work on opening up the area for groundwater seepage?
So there is a big effort going on at the local level, and all of our university students, faculty are all joining the Friends of Jones Falls so that we can start daylighting the streams wherever strategically we can. So there is a plan in progress right now.
That's great to hear. We also have another question from Cambrian asking, could rooftop gardens be a real solution to green space lack?
Most definitely. As much water as we can absorb when it falls, it's better. And for Baltimore, because we have 16,890 vacant properties, it's really important for at least me, to focus on the vacant land so that we can capture that. I'm also working with the community land trusts so that this land becomes community commons, so that the neighborhood associations start taking care of it as opposed to giving it to developers who will put hardscape on it.
And speaking of hardscape, we did have a comment in the chat that green spaces are also important for mitigating heat waves, the connection between air quality, water quality, and a heat wave, and that, concrete covered areas can make flooding worse. So I guess, is there any additional comment you want to make about those green spaces and the compounding benefits they provide?
Absolutely, because that's so important, and there is so much public education that is needed in that area, because one of the worst neighborhoods for flooding in Park Heights is Towanda Neighborhood Association, contacted us, asked us our expertise, because we have a community engagement platform where any neighborhood association can say, help us out with this architecture or urban design issue or city planning issue. And we put a team together and go to the neighborhood. So the Towanda Neighborhood Association contacted us for their flooding issues. And it was really interesting because I was like, okay, your backyard has concrete in it. So it's like, yeah, that's because it floods. That's why we put concrete. In fact, the Vulcan concrete factory gave us free concrete to do this. And I had no idea that there was a hidden factory in the neighborhood. So I went and walked the factory. It was all paved, and that was the source of the flooding. And the more the neighborhood complained about flooding, the more they supplied the concrete for free to shut them up so that the water can flow beyond there. It doesn't sit in their backyards. So the root cause was that there was too much concrete. So the education of the neighborhood, that the more concrete you put, the more flooding there will be. And you have to create you have to stop creating impermeable surfaces and resort to permeability so that the water is absorbed. So we are working on both the community education piece, but also working with the industry to make sure that they understand that in urban areas, they have to operate more ethically and less with the bottom line in mind.
That was an amazing example. I really appreciate you sharing that. We have another question from LEB. How does the science community help build trust with communities? You mentioned the importance of designing research questions with your students. Do they also practice rhetorical skills?
Absolutely. That's a big question, and it's a totally different presentation. I think my challenge has not been building trust with community. My challenge has been convincing scientists to stop asking research questions prior to engaging communities. That is much more of a challenge. Building community trust is a piece of cake. All you have to do is show up without a research question and ask, how can we help you? That's the simple bottom line of building community trust.
That's amazing to hear you
So
say.
the problem is with the scientists' mindset, not with the community.
Absolutely. On my recently funded NOAA work for wildfire weather, the first thing we did is we went to the dispatchers and the agencies and say, what do you need?
Exactly.
I'm not going to ask the research questions until you tell me what you need. And that made all the difference for making the science have a bigger impact and outcome.
And to continue in that, if I may, people think that funding agencies require you to write a research question. That's not true. We just got a Maryland Sea grant in which we openly claimed we will take 2 years to co-create a research question with the community. And we got the grant.
Thank you so much for adding that in. It's something that all grants, if you're a grant writer listening in, we really encourage asking and working with the community, even finding a community partner to serve as a advisor to your projects, just so they're in the loop and know if they're kind of on track is extraordinarily beneficial for both the science and the communities. And with that, Samia, we want to thank you so much for joining here. It was an incredibly impactful talk. And we are so grateful to have learned so much from you, especially in this area.
Thank you very much for hosting me.
Absolutely. All right. Well, but before we move on to our next speaker, I want to remind us all why we're here. The U.S. weather and climate science is the foundation for our forecast warnings and public health guidance. And all of us really rely on this. Every industry relies on this. Every single person relies on these weather and hazard predictions. And that foundation is under pressure from the proposed budget cuts. So please use a link in the chat and make sure you're reaching out to your representatives to explain to them why this matters so much. And I will also add that the other science cat has also joined the stream. We have Mr. Kaiju also is against science cuts, cats for climate change. So with that, I'm glad we got both cats in appearance as promised in yesterday's stream. All right, our next speaker is going to be Christopher Callahan, who is an assistant professor at Indiana University, and we'll be talking about El Nino, which has had quite the flurry of conversations in chat today. So thank you so much, Christopher. Take it away.
Thank you so much for having me. I'm really excited to be here. Can you hear me okay? Can you see my slides? All right, awesome. I managed to catch the live stream last year, but wasn't able to speak. So I'm happy to be here speaking this year about El Nino, which is, as you say, I think a really hot topic right now heading into this winter. So I'm going to talk about sort of two things. The first is a sort of brief primer on El Nino and what it means and why we should care about it for folks who may not be as familiar. And then I'm going to talk a little bit about some of the specific work that my advisor and I did a couple of years ago during my PhD, which was about the economic and social impacts of El Nino. That was work that was very directly funded by the National Science Foundation. And so there's a direct line from public funding of research that makes it possible for graduate students to be funded to pursue their interests and be able to come up with this kind of work. So we are talking about El Nino right now partly because you all may have seen some fairly recent headlines. They're sort of all over the place at this point. You have things like a rare super El Nino as seen in Bloomberg, a strong El Nino highlighted by the New York Times a couple of weeks ago. And if you think it's hot now, time to brace for what's coming next. And so if you read the sort of climate or environmental press, you're going to see these kinds of headlines about this coming winter. And indeed, the current forecasts are for a very strong El Nino. So what you're seeing here is a plot from the Climate Prediction Center, which is run by the National Weather Service. So this is a publicly funded federal agency effort that uses basically a forecast model to project how the tropical Pacific is going to evolve over the next several months. And so the black line there is what we've already observed. And then the colored lines going into the future are our future projections of how the ocean in the Pacific Ocean is going to evolve over the next couple of months. And you can see they go up as the tropical Pacific Ocean warms, and we get the potential for a very strong El Nino. Nino 3.4 is an index of how strong the tropical Pacific is in terms of how warm it is. This is a plot from yesterday. This was the most recent forecast produced by NOAA as of June 1st, so Monday of yesterday. And so this is our sort of best expectation of a very strong coming El Nino later in the fall and into the winter and then the spring. But before we talk about the details, I wanted to briefly discuss what is El Nino and why we should care about it. Basically, it is an episodic fluctuation of warm and cool temperatures in the Pacific Ocean. So on the left, you're seeing a map of sea surface temperature anomalies. So red means warmer than usual conditions. So the left is an El Nino event where you see this big swath of red across the equatorial Pacific. You see red conditions indicating warmth in the eastern Pacific. And then on the right, you see a La Nina event, which is blue in the central Pacific, indicating relatively cool conditions. And so over the course of decades, the tropical Pacific flips back and forth between these two different conditions, going from warm to cool back to warm on intervals of approximately 2 to 7 years. So I'm showing a plot here over time. This plot has the title ENSO, which stands for the El Nino Southern Oscillation, which is just another phrase for this sort of oscillation over time. This is a plot that runs from 1960 to 2019, so about 60 years of data. And it's showing something called the E index, which is just a sort of index of the strength of El Nino, where positive means El Nino events and negative means La Nina events. So you can see over the course of several decades, you get this flipping back and forth of positive to negative, punctuated by these couple spikes of really extreme El Nino events in particular years. El Nino events reorganize the global atmospheric circulation and affect weather around the world. They cause very wet conditions in the tropical Pacific near the east, like Peru and Ecuador. They cause very dry conditions in Australia, Indonesia, the Philippines, and they sort of radiate out weather effects around the world. During El Nino years, we've often seen things like drought and fire in Indonesia and the Philippines. We've seen floods in Brazil and Peru and Ecuador from extreme rainfall there. Historically, we know that California has been really strongly affected. So this is a lithograph from the winter of 1862, where there was an extreme flood that turned Sacramento into a lake and turned the Central Valley of California basically into an inland sea. And if we see events like this recur in the future, it's likely to be driven by very severe El Nino events. We also know that El Nino affects hurricanes. So this was mentioned earlier by one of the presenters, that during El Nino years, we actually tend to have quiet hurricane seasons in the Atlantic Ocean, but relatively active hurricane seasons in the Pacific Ocean. And so you can reorganize the global pattern of hurricanes as well during El Nino years. So this was all relatively well known by the time that we started our research, but this gives us a sense that El Nino can have really significant weather and climate impacts around the world. The specific question that my advisor and I asked was, what was the global economic effect of El Nino? So how does this propagate into human economic growth? And how will this impact evolve under climate change? So we want to move into sort of some social science here. We're going to sort of try and bridge some physical science insights and social science methods to address how El Nino affects human societies directly. For the technically minded among you, I'm going to mention a couple of methods very quickly. We're using something called a regression model, where we are correlating changes in country level economic growth against annual indices of El Nino. We're tracking how different countries' economies respond differently based on how teleconnected they are, quote unquote, which means that we are allowing tropical countries to respond strongly to El Nino. And we sort of see how mid-latitude countries like the US and countries in Europe maybe are affected less strongly because they are not directly affected by tropical oceans. And then we project the impacts of future El Nino changes with global climate model simulations. These are like the IPCC style climate models that project how El Nino might change in the future. This was collaborative work with my colleague Justin Mencken, who is in the Department of Geography at Dartmouth. So thanks to him for all of his work on this as well. The key finding of this work is that there is a significant effect of El Nino on economic growth around the world. So I'm showing a plot here on the x-axis where you have the years since the El Nino event. So 0 is the year of the event, and then 5 is 5 years later. On the y-axis is the cumulative change in economic growth around the world. And so what we see is actually that in the tropical countries that are strongly affected by El Nino, we see consistent and accumulating economic growth losses following these events. So we see, for example, roads and bridges are destroyed and are not rebuilt. We see infectious disease outbreaks that tend to have really significant socioeconomic consequences. We see floods, droughts, and so on, all of the things I mentioned before. And what this results in is a sort of persistent depression in economic growth relative to how countries would have evolved otherwise in the absence of the El Nino event. I've been hinting that different countries are affected differently. So we were able to show that the economic growth reduction that results from El Nino tends to hit the tropics most. So you're seeing a map on the right, which is where each country is colored by the reduction in economic growth that that country experiences following El Nino events. And so you see a lot of red in the tropics. So Brazil and South America, Central Africa, Indonesia, the Philippines, Malaysia, and so on. And so those are the countries that are really being hit by these fluctuations in tropical sea surface temperatures on a year-to-year basis. And then when you move out into the mid-latitudes like the US and Europe and Russia and so on, you see much, much weaker events and so effects. And so these effects are really structured by the global distribution of exposure to El Nino events, same as much other sort of structuring in the global economy and in the global climate. The next question we asked was, what does this mean for the future of El Nino? So we know that these events can have really significant economic consequences. What does that mean for climate change? So we went into climate models. So these are global computer simulations of the climate. And we asked, how strong is El Nino in these climate models in the past and in the future. So the x-axis here is El Nino amplitude, which basically means how variable El Nino is, how strong are the highs, how strong are the lows, how much are you fluctuating on a year-to-year basis. So this is what the climate models tell us historical El Nino looks like. We have a distribution across climate models. So different climate models give us different answers, but some say we have relatively strong El Nino, some say we have relatively weak at present. And then we ask what the future looks like. So if you go into the rest of the 21st century with more greenhouse gases and more climate change, these climate models tell us that generally El Nino strengthens. So you see this red histogram move to the right relative to the gray distribution. What that suggests is that climate models are generally projecting an intensification of El Nino, an increase in the amplitude of these year-to-year fluctuations, which other researchers have tied to the strengthening of the coupling between the wind and the ocean. So El Nino is driven basically by feedbacks between the atmosphere and the ocean, and those feedbacks might strengthen in a warming world, driving stronger and stronger El Nino events. Although I will say that there's a lot of uncertainty around this change and different models behave differently, these climate models are also notoriously poor at simulating the climate of the tropical Pacific anyway. And so there's lots of questions we still have about this change. But we were able to show in our research that if the El Nino amplitude increases, if we get a stronger El Nino, trillions of dollars are on the line. So this is the plot I'm showing where on the x-axis is the percent change in El Nino amplitude. So increase means a stronger El Nino in the future, and decrease means El Nino might weaken in the future. On the y-axis is the global GDP change cumulatively over the rest of the 21st century. So we're adding up all the economic growth loss over the rest of the 21st century. And we see that if El Nino strengthens significantly, we might risk $200 or $400 trillion in global GDP lost over the rest of the century. This is a very significant economic penalty due to the amplification of this mode of natural climate variability. The last finding I want to show was calculated more recently by Dr. Alex Gottlieb, who's a research scientist at Dartmouth, and he took the actual NOAA forecasts, which I showed before. So these are the federally funded, federally run forecast models that project how El Nino is going to evolve over the rest of this year. And we see that there's going to be a strong El Nino event because the sea surface temperature anomalies are going to be very positive. And so what Alex was able to calculate based on our previous results is that over the next 5 years, the global economy stands to lose more than $10 trillion cumulatively between now and 2032 due to the strength of this El Nino event. Because it has such a major economic penalty, countries in the tropics stand to be much worse off than if the El Nino did not occur and stand to experience substantial monetary penalties associated with all of the climate stress that happens during these El Nino events. And so these are very socioeconomically significant events. I want to leave you with a few key takeaways that I hope you sort of remember from this talk. Publicly funded research helps us both forecast El Nino on a short time scale, so between now and the rest of the rest of the year, and understand its broader socioeconomic impacts, the way it affects our societies and our economies around the world. This winter's El Nino is likely going to cause substantial economic damage if it continues to be a strong event like that is projected, but there are adaptation measures that we can take, including disaster risk reduction measures, potential spread of insurance for farmers and fishers who need to withstand the economic harm of this event, and so on. And the future of El Nino under climate change does remain uncertain. Despite some projections of its increase, there's lots of disagreement about this already. And so I would argue that even more publicly funded research by NSF, NOAA, NASA, all of these agencies is absolutely essential to understanding how El Nino and other modes of climate variability are going to evolve in the future. Thank you very much. Happy to stay on for questions if there are any.
Great. Thank you so much, Christopher. Chat has been blowing up and talking about El Nino, and we have quite the flurry of questions. So I guess let's start off with Sydney Lomquist asks, I'm curious as to your opinion about this season. Is this year likely to be as bad as people are saying it's going to be?
I think likely yes. There is going to be a very significant El Nino this year. It is not totally clear exactly how bad it's going to be. That's the kind of thing that the models are still showing some differences on. I think there's a lot of headlines you'll see that are about this thing called a quote super El Nino, which is sort of a colloquial term. And so it's actually not totally clear if it is going to be the worst El Nino we've ever seen, like some of the models are forecasting that it will be. But I think the thing you can hang your hat on at this point is that there is going to be an El Nino this winter, and it is likely to be very significant.
And to that point, how can these vulnerable countries and in the tropics protect against these economic issues associated with this year's upcoming event?
I think there's a lot of options that have been raised previously in the literature, even just putting into place early warning systems or other sort of short-term predictions that allow countries to know when, for example, major rainstorms are likely to occur or major wildfires are likely to break out, can help these countries prepare. I think more generally, we need to ensure that these countries have the sort of economic base that is resilient to sort of climate stress. If you have a place where people are vulnerable, people depend on, for example, in Peru, a lot of fishers depend upon the highly productive fisheries across right outside the coast of Peru, which is driven by all these nutrients upwelling that gets shut down during El Nino events. And so Peruvian fishers are really vulnerable to these events. And so ensuring that those fishers either have insurance, either they have a government support, they have other economic options in the face of these disasters is really essential.
Great. And we did have a comment when you were showing all those previous examples about the flooding in California in 1862 flooding. Do you feel we are ready for this major El Nino this year, especially given the funding limitations and cuts if they were to keep going with the upcoming budget changes?
It's not totally clear. I think one thing that is worth saying is that El Nino does have a very big impact on a lot of tropical countries. What it means for the US is often a little bit more questionable. Every El Nino is different and often has very different effects. And so some El Nino years in the past for the US have been very catastrophic and some have been basically negligible. And so I think we're still a little bit unclear on exactly what this year is going to mean for us. I will say that another agency that has really taken a hit recently alongside the weather forecasting services is FEMA. Right, is the federal disaster aid infrastructure that is built to help states withstand disasters. And so I think if a major disaster were to occur, like a flood in Southern California driven by El Nino, I am worried that our disaster response capability is not going to be able to withstand that event.
Great. Thank you so much for that insight. It's really important that we talk about these impacts with the budget cuts. We do have a few more questions. Does a strong La Nina also cause large damages, or does it affect other parts of the world?
This was a pretty difficult question for us to figure out, partly because there are not as many strong La Ninas as strong El Ninos. So El Nino is sort of asymmetric, where you have a lot of strong El Nino events, and then the La Nina events tend to be kind of weak and like less strong. And so we actually found that some La Nina events actually provide benefits, because maybe you get some moderate rainfall, you get some maybe moderate warmth that is maybe better for your country. There is other research out there showing that La Nina can be damaging in the way that the commentator is suggesting. So I actually think the economic impacts of La Nina are kind of still uncertain. Like, that's a place where there's still a lot of research ongoing. And I think we actually know less about it than we know about El Nino.
And to that question, LEB asked, does public funding also help you collaborate with scientists at other universities to move this research forward?
Absolutely, 100%. It is absolutely essential for us to be able to build both national and global networks, to be able to both monitor the global tropics, which is essential for forecasting and understanding El Nino, and drawing on the expertise of all the scientists around the world that know about this phenomenon, because it is a truly global phenomenon. One thing I will say is that one recent move by the current administration is not necessarily beyond budget cuts, is also to restrict the ability of researchers to collaborate internationally. So there are new regulations that are being attempted to be put in place that would require researchers to basically pre-register foreign collaborations and allow funding agencies to cut funding if researchers have foreign collaborations that are seen as undesirable. And so I think that, even along with budget cuts, will be really catastrophic for our global understanding of the climate.
Absolutely. That is a very important point to make, that we are talking globally when we're talking about weather and climate. It does not exist in a bubble. Lastly, we have one last question that's more on the technical side. Why is Australia so much less affected by El Nino compared to Southeast Asia or South Africa? They would have expected more red there. So any comments on that?
This was actually a question we had for ourselves as well. Like, we were surprised at how little we found the effect to show up in Australia. I think one reason for that might be just that we were looking at country level economic growth. So economic growth across the whole country and the sort of teleconnection of El Nino to the whole country. I think if you looked at, for example, like Northeast Australia or specific sectors in places that were closer to the areas that are affected by El Nino, you actually might see more significant impacts. I also wonder where Australia might be a place that's actually more affected by La Nina, which tends to bring really significant rainfall to the Western Pacific and maybe on that northeast coast of Australia. And so I think that's something that is maybe just sort of a limitation of our sort of coarse global approach and might be better answered by sort of more local or more fine scale methodologies.
Great. Thank you so much, Christopher. That was a really informative and very topical discussion on El Nino as we're going into potentially one of the biggest El Ninos on record. So we really appreciate your time and hope you have a great rest of the day.
Thanks so much for having me. Really appreciate it.
Yeah. All right, everyone. Before I introduce the last speaker of my hosting block, I want to one more time remind you, if you're just joining us, welcome. If you've been here a while, thank you so much for joining us. The U.S. has been a world leader in weather and climate science for decades. And that didn't happen by accident. It happened because we, the American people, invested in it through our institutions like NOAA, NASA, NSF, NCAR, UCAR, research universities, and building all this infrastructure that we depend on. And we're talking about satellite systems that track hurricanes, forecast models that tell fire departments about a red flag warning, air quality networks that let you know if it's safe to be outside. And this investment is under threat. The weather stations are short-staffed, the climate labs are being shuttered, and the proposed budget cuts for fiscal year 27 would cut NSF and NASA budgets in half, reduce NOAA's research arm almost entirely, dismantle NCAR, which is what weather and climate science in this country depends on. So these aren't abstract cuts. They really affect the forecast, the real warnings, the real decisions that affect our lives. The House and the Senate are making these decisions right now, so please take time to use the link in the chat. Please feel free to use the written script if needed. Tell your representatives why this matters to you and to our country. And I will also, as a personal note, in case I don't get a chance before signing off, thank you so much for having me as a host. Of course, near the end here, both of our climate cats are cooperating. We got Catalina and Kaiju that are Cats Against Science Cuts. So thank you all for having me and supporting both me and my sister on both of our streams the last 2 days. All right, the last talk I'll introduce today is by Ross Dixon. He is an assistant professor in regional climate and atmospheric numerical modeling, and he's going to be talking to us about snowmelt. So take it away, Ross.
Fantastic. Thank you so much for the welcome. This is a really great opportunity to share some of the interesting work we've been doing that is funded on a NOAA award, thinking about what makes snow melt during impactful rain-on snow events, and how this is represented in models, how we can better represent this in models. And, you know, my background is actually large-scale tropical dynamics, but I've been in Nebraska for the past 5 years and was starting to chat with some colleagues. And one of them said, have you ever thought about looking at rain-on snow events? And I said, no, tell me more about these rain-on snow events. And it ends up, it's just when rain happens to fall on snow, the snow can melt and it can lead to really big, impactful flooding events. For example, back in 2022, Yellowstone had a really big flooding event. And that was due to both a lot of precipitation, but also a lot of snow that melted at the same time, leading to really impactful flooding. There was an event in New Hampshire just a couple years ago, 2023. And from someone who's been in Nebraska, we had a really big event in March of 2019. And so this is what the surface, this is Omaha, Nebraska, right here in the center, river systems around it, the Missouri River, the Platte River. And you can see that in the beginning of March of 2019, there was a lot of snow on the ground. And just a few days later, all that snow was gone, and you can see how swelled the rivers are, right? This is because a big bomb cyclone came through, dropped a whole lot of precipitation, but also all this snow melted. This is what the rivers normally look like in a normal March, right? You know, they're full but not overflowing. This is what it looked like mid-March of 2019. Really big flooding events. Here's some pictures from the town of Dannenbrog. Here's a photo of, you know, just infrastructure, right? There was a lot of rainfall, but even more melting of snow, right? 5 fatalities, billions of dollars in damages, right? These are really impactful events. And people are really interested in what is the future of these rain on snow events? How will these rain on snow events change in the future? So there's been a lot of studies that have done, a lot of them have focused on Canada or the western part of the United States. And so we were starting to think about, okay, well, how well are these events represented in the center part of the United States, across the Great Plains, across even the eastern coast of the United States? So how well are rain on snow events represented in models is what our project was looking to address. This was led by Zach Siriano at Western Kentucky University, Tirthankar Roy in the College of Engineering at UNL. And we were able to hire a postdoc, Eric Jansen, who worked with us on some of the modeling work. And this was supported through NOAA. And so we wanted to see how well these big events, and we were going to use this big 2019 event as a case study. So we fired up a numerical simulation. We used a model called Weather Research and Forecasting, developed out of NCAR. And so here's where our model domain is. This is the domain we're going to make this simulation for. We're going to run it for 10 days during this big rain on snow event. And then we're going to do analysis around the Omaha region. So when I talk about doing a numerical model, I'm talking about discretizing the equations of motion, right? Thinking about turning the numerics of what happens in our atmosphere and our Earth system really into numericals, into numerics representing subgrid scale processes, right? But then we also want to do analysis of what comes out. And what are we going to compare that to? Well, we've got flux tower locations which measure energy into and out of the surface that are right here at this red dot close to Omaha. We've got satellite measurements of, say, snow cover and precipitation. And we've got reanalyses, which is a combination of model and observation for some fields we don't have great spatial structures of from observations. And so this is what our simulation looks like compared with radar. So this is rain and snow in the lowest model level, thinking about what a radar might bounce off of. And so here's our observed, right? Here's that cyclone that comes through. And you can see that our simulation produces the cyclone pretty accurately. But when we look at the snow amount, right? So we've got snow amount on this axis here, and we've got date and time. And so our red line is our simulation, and we've got a whole lot of other products where we're thinking about how much snow exists around Omaha. And you can see that the snow melts more slowly in our simulation than all these other estimates of how quickly the snow melts. Why is that? Why does the snow melt too slowly in our simulation? So what makes snow melt anyway? Well, energy into the surface melts snow, right? And that energy could come from shortwave radiation, energy from the sun, right? That comes through the atmosphere and hits the surface and warms it through shortwave radiation. Everything that has a temperature emits radiation. So our atmosphere and clouds, they are all emitting radiation, but at cooler temperatures, so at longer wavelengths. So that's long wave radiation. If we have air that's warmer than the surface, that imparts sensible heat into the surface. So that's energy into the surface. If we have a lot of moist air that comes over that surface, it can condense onto the surface, and that releases latent heat. We're going from a vapor to a solid. So we're releasing latent heat. So these energy fluxes into the surface can melt snow. And so when we compare our simulation with reanalysis, we see our precipitation here. Our solid red line is our simulation, and the dashed line and the black line are observations and reanalyses. And you can see that for precipitation and radiation and sensible heat flux, our simulation looks very similar to what we see in observations and reanalyses. But this latent heat flux is underrepresented. And we think that this might be a major reason why that snow doesn't melt as quickly as it does in observations. You can see this really clearly in these spatial plots, right? These red lines are energy into the surface from latent heat flux. And the blue filled space is where snow is. And here we see strong negative fluxes into the snow. But in our simulation, it just stops. It just stops right here at the edge of the snowpack. We think that that's not correct. But it could just be us. We could just be bad at doing simulations, right? So we also checked this in some simulations that were performed at NCAR with really high resolution simulations. And we also, this is known as CONUS 404. A lot of really, really smart people worked on this simulation. And we also see these negative fluxes just go right up to the edge of the snow and won't go over top of it. And in fact, these latent heat fluxes are really important. We did some snow modeling where we forced it with fluxes from the flux tower site. And we can see that as we decrease the amount of latent heat that goes into our simple snow model, the time it takes to melt all of this SWE or snow water equivalent increases by about 20% in time. This has huge impacts for runoff, right? The longer that 10 additional hours doesn't seem like a lot, but it means a lot in terms of how much runoff we get, the maximum amount of runoff, and how quickly that runoff really peaks. So this is a big deal. So the last thing we worked on is thinking about how we can improve the representation of latent heat flux in this WRF model. And Eric was really responsible for this. We had to think about how the model represents the latent heat flux. And I don't want to, this is a whole talk in itself, but we had to think about taking the equations and digging into the source code, right? And really asking several colleagues, folks from NCAR, folks who worked on developing WRF, how does this work? Eric spent a lot of time thinking about how do all these different parameters have an impact on the these latent heat fluxes. And so he was able to run a control simulation and change some of these parameters. So here's our initial simulation where this negative flux doesn't enter the snowpack, but when he changes some of these parameters and improves the representation of that latent heat flux, here we can see as he changes these parameters, those negative fluxes can go into the snowpack. This can really help represent the melting of snow. So in summary, we started by just identifying a really challenging forecast problem. Snow melts too slowly during these impactful rain on snow events, right? We tested this with actually a bunch of different case studies, but this was the biggest one, so we wanted to show you this one. We compared our simulations with observations and really detected that it's not representing these latent heat fluxes properly. And we improved the model code so that we can better represent snowmelt during these impactful rain on snow events. And I just wanted to say that without federal funding, this would not have been possible. Without funding through NOAA, we wouldn't have been able to hire Eric, who did a lot of this really great work. You don't learn modeling just by reading a book or taking classes. You have to really spend a lot of time doing it. And a lot of that, for me personally, came from doing workshops and training sessions at NCAR. Really meeting a lot of really brilliant people there who really helped me become an expert in modeling myself. So just wanted to show you some of the really interesting work we're doing, impactful work that should help better predict flooding during these rain on snow events, and really highlight the importance of federal funding to this work. I'd be glad to take questions.
Great. Thank you so much, Ross. It's such a really interesting topic that I don't think we all think about until the impacts are really being felt, until you have that extreme flooding. We do have a question from Hannah Palco asking, could the snow model be incorrect because it was created on historical data that did not account for the current weather patterns due to climate change?
Yeah, that's a great question. And this is something that I particularly think a lot about when we're thinking about using machine learning and AI to train some of these relationships for future climates. Where we come from in terms of our numerical modeling, we're thinking about how do we best represent these physical processes. And so what Eric went through was thinking about, okay, well, what is the physical analog? We go from our observations and our theory to mathematics, and then we take that mathematics and turn it into numerics. So here we were basically just trying to think of a process that is always been there and isn't always important, right? What we're really seeing is that only for these really impactful rain on snow events, we're not trying to say that the models, you just throw out the model, right? 99.9% of the time, it's representing these fluxes really well. But what we're seeing is that during this really impactful event, the fluxes aren't there. So we need to think about how to move and improve that model. Thanks for that question.
Yeah. We have another question on from Cosmo Conjurer. Can this rain on snow issue start impacting elsewhere dramatically more? This person lives near a lot of May flood areas, and their temperatures fluctuate insanely quickly. Could a cold flux followed by a rainstorm really, kind of increase or happen more frequently in those types of areas?
So this is something that folks are really interested in, and depending on where you are is also so that's one part that we've just started kind of exploring, is thinking about, okay, well, where do latent heat fluxes have the biggest impact during these rain on snow events? Are there certain hotspots in the world where we really need to get those latent heat fluxes correct, and other places where maybe they're not that important, right? There's a lot of folks who are doing, for example, Zach Suriano, who's one of my collaborators. That's one of his major areas of research, is thinking about how do the characteristics of rain on snow going to change in the future. So that's a really great question.
And I have a personal interest. Is there a role as a wildfire and smoke and aerosol person? Part of that snow melt, in my opinion, is when you have a lot of this dusty particles that are dark land on the snow and contribute. They absorb heat and contribute to that. And so, is that something that future models should be maybe taking into consideration? So when you have dirty snow, it tends to melt a lot quicker than very clean, white, fluffy snow.
Yeah, no, this is a great question, and I loved your talk last night. It was fantastic work, and really, really cool. Yeah, I mean, one of the things that Eric was looking at was snow roughness, right? What are the properties? And in the model, this is just set as a parameter, right? How does snow roughness change over time? Does it get rougher or smoother at these different levels that are important for the processes we're trying to represent? How does black carbon, which falls on snow surface, change? Those are all super, and our models are really good, but there's always things we can do to improve them. And a lot of, my group's work is trying to identify what those things are and work to improve them.
Yeah, and one of the things that I absolutely love that you highlighted was the use of observations, right? You have to give the model, you have to compare it against something, you have to, have a goal. And those observations are so important. And instrumentation and getting field data is very, very difficult. Do you have anything to kind of comment on the
I'm a numerical modeler, right? So me, I love being in my modeling space, but it is so important that we compare our models with observations. And making observations takes a lot of expertise and money and equipment, and that's not something I can do, right? None of this work I've done in a vacuum, right? I've had fantastic collaborators on my team. But also, I've been so fortunate to be in an ecosystem where there are people outside my group that are doing all these different observations, satellite folk, flux tower, Ameriflux people, folks who are continuing to work on models, and we can bounce ideas and get support off of. This science doesn't happen in a vacuum.
Absolutely.
So very, very fortunate. Yeah.
And speaking of numerical modeling, one last question for you. Ellie B asks, this is actually a great question. What has been your biggest failures in modeling? Have you ever tried something, but it failed in a funny way? And I know I've personally gone down research rabbit holes that have, I think maybe my record might be 3 months where the results just never really materialized. And it was a great lesson in what not to do. And that work is equally as important on what not to do and save time for the future.
Yeah.
So do you have any comments?
Yeah, if it works the first time, you haven't done it right. That's no, modeling is something, like I said, you can't really become a modeler by reading a book or just taking a class. It's something that you have to do, and you have to be willing to test a lot of things. Graduate students often come in and say, okay, well, look, I did this one thing, I made some plots, this is a paper. And I say, well, look, a lot of these simulations you do are never going to end up published, but there are important steps to figure out what is the full story that you want to tell. And so, yeah, that's a really great question. Thanks for that.
Yeah, thank you so much, Ross. It's been great having you. That was extremely insightful and, just such an interesting topic that we don't necessarily think about day to day, but it is so important and it is so nuanced to represent in these forecast models.
Thank you so much for having me.
Yeah, have a great day. And with that, I will be turning over the hosting session to Robert Pincus next. So he's about to join us here, and I hope you all have a great day. And do not forget to use the links in the chat to call your representatives and talk about how much this science matters, and it matters to you all. Thank you.
Thanks, Samantha. All right, I'm back. Those of you who were up at 5:40 this morning saw me incoherently babble. That was too early for me. It is noon. We are beginning hour 21 of the Weather and Climate live stream. This is station WCLS calling you from New York and worldwide. It is noon on Tuesday, June 2nd. It's 1 o'clock in the morning in Tokyo and 6 p.m. in Paris. Why are we here? We are here, dozens of us, maybe hundreds of us are getting together to do two things. One is to give you a flavor of what it is that we do in the weather and climate enterprise in the United States and by extension internationally. And we're doing that because our field is very much under attack at this point. We have a number of very strong headwinds, and we'd like to encourage you, to motivate you to get in touch with your elected representatives to push back just a little bit on that. You can see in the cryon underneath, a website where you can go to get information about how to call your representatives. One thing we'd like you to tell them to do is to repeat from last year what they did, which is reject the presidential budget, which is extremely, which will essentially destroy the scientific enterprise in the United States. We have entire agencies whose research budgets have been proposed to be completely eliminated. We have vast cuts for all of weather and climate science. What I hope you're taking away from these talks is that weather and climate science has enormous practical value. It also has, I hope this is also coming through, enormous sort of social value. When they were building the first large accelerators in the United States, the director of Fermilab was called before Congress and asked, what does the accelerator contribute to national defense? And he said, it makes the nation worth defending. And although times have changed in those 55 years since that comment was made in 1970, the truth of that, that the work has both enormous practical implications. It's very important. It keeps people safe. It keeps people alive. It saves people money. But it also has enormous social value. And so I hope you're taking that away. I hope that will motivate you to get in touch with your representatives, give them a call, and tell them to reject the very dramatic budget cuts that have been proposed for the coming fiscal year. Our next speaker is Paul Roundtree. He studies big waves in the atmosphere and ocean, and he is a professor at the University of Albany. Take it away, Paul.
Thank you for having me. I'm really excited to participate. I must say I've loved science since I was a little child. My mother described me lying on my back on the grass watching the clouds. I actually grew up in poverty. My father was a farmhand and my mother was a cafeteria dishwasher at a local hospital. And sometimes I relate that my nearest neighbor where I grew up was a sheep. So growing up on the farm kind of had me isolated from a lot of the things that I ultimately learned about later in life. I got a degree in physics, a bachelor's degree in physics, and And I always wanted to go into atmospheric science. And so I earned my PhD at the Pennsylvania State University way back in 2003. Today, I want to tell you about what I've spent the last roughly 20 years of my life studying. I want to kind of simplify the story a little bit to help understanding. I'm going to be discussing these waves in the atmosphere and the ocean called Kelvin waves and their role in the Madden-Julian oscillation. Some people have called this Madden-Julian oscillation the maddening Julian oscillation because we have trouble really understanding or agreeing as a community what it is. I'm going to also make a connection between this Madden-Julian oscillation and the El Nino phenomenon, which is emerging right now in the tropical Pacific. My research work has been funded by the National Science Foundation and the National Oceanic and Atmospheric Administration of the U.S. Department of Commerce. A little bit of background is needed in order to understand this kind of wave dynamics. If we're moving, the Earth's rotation makes a sense of force toward the right if we're in the northern hemisphere, and toward the left if we're in the southern hemisphere. This is called the Coriolis force. It's not a real force, but it's something we feel because the Earth is spinning, and when we move, we're kind of conserving angular momentum on the planet as we move around. Early military people, when they first started firing rockets, learned, or cannons even, they learned that they had to alter their aim when aiming over large distances in order to hit their targets because of this effect, altering the direction that the cannonballs would move. So I'm first going to describe the simplest form of a Kelvin wave. This is a mountain range right here. The mountain range is oriented north to south. We're going to assume that we are in the northern hemisphere and assume a surge of cold air. Think about this east of the Rocky Mountains in central Canada. Arctic air is heading south. And as it does so, this southward flow of air experiences a force to the right, again, because of the rotation of the Earth. And that piles up a ridge of air to the east, just to the east of the mountains, which damps out as you move away. And so the Coriolis force toward the mountain comes into balance with the pressure gradient. Think of the ridge right here as pushing the air back away from the mountain. And these two forces come into balance, and so the wind only heads toward the south. And this forces a surge of that cold air that can go all the way down into Central America. People down the lee of the Rocky Mountains know and understand this kind of cold outbreak well, but it's driven by this phenomenon or mechanism known as the Kelvin wave that works this way with this kind of force balance. When the wave reaches the equator, so we're going to change the schematic now and draw a line right here, horizontal across the center, that's the equator. And here is a ridge, and the wind is blowing toward the east in that ridge, and this is a trough, and the wind is blowing toward the west in that trough. And if you find yourself on one of these points right here, you've got eastward flow, and the Coriolis force goes toward the right, so toward the equator, and the pressure force is pushing you toward the north. And these come into balance, and so you only have eastward flow in the ridge. And a similar thing happens in the trough, but in the opposite sense. You've got going this direction, going toward the right means that the Coriolis force is pushing you this direction toward the north, while the pressure gradient force is pushing you toward the equator. The wave propagates because the convergence of mass, you can see the wind is blowing from the west here and from the east here. So that means that mass has to be building up right here. And that mass builds up east of the present ridge location. And so the ridge moves here, even as to the east of the trough, mass is being removed. And so this whole thing moves from west to east around the world. So this is called the equatorially trapped Kelvin wave. Now, here's what these things look like in the real world. We're looking in the upper atmosphere, and we're looking at signals moving eastward over the Indian Ocean. You can see the equator along the middle here. You've got eastward flow in the ridge, westward flow in the trough, and you've got divergence of mass. So mass is being moved out by the wind from this middle section. And so this trough in the blue contours is advancing from west to east. As it does so, this thing modifies the atmosphere, temperature environment, and increases rainfall intensity at this location where you see the blue shades. And this signal moves from west to east around the world, and we track that rainfall signal using satellite data, measuring the outgoing long-wave radiation. So objects are emitting heat radiation based on their temperature. The cloud tops here are very cold because these are deep, strong thunderstorms. And so this signal is sensible in the satellite data, and we can track it around the world and then find the circulation signals associated with it. It's a little different from a Kelvin wave in the observations because the convection is, the thunderstorms are changing the distribution of mass here, and so they create flow away from the equator. So it's not strictly just east and west winds. It builds a ridge to the north and the south, and then there's this, we'll call it a wave response in the atmosphere to the north and the south. What we'll call the Kelvin wave is right here along the equator. And now some of what my research has shown is that if you go to slower signals, now we're looking at signals that are moving eastward at 6 to 11 meters per second. So this is significantly slower than these really fast ones, but they look the same. You've got eastward flow in the ridge, westward flow in the trough, rainfall in between, and then this associated extratropical wave pattern. And finally, we're going very slowly at 2 to 5 meters per second, the same kind of signal, eastward flow in the ridge, westward flow in the trough, and then this associated pattern that goes off into the middle latitudes and affects all of our weather. This signal right here is known as the Madden-Julian oscillation, and people have been struggling for many years to figure out how this thing works. Turns out that back then they noticed that the relationship between the ridge and the westerlies and the trough and the easterlies, they observed back then, but the signal was moving eastward too slowly for it to be a Kelvin wave. And so they rejected the idea ultimately that a Kelvin wave could be causing it. Only just recently I've published results that explain why it moves so slowly. And it turns out the simple answer is that this wave coming from the west hits a headwind. So the wind in the background is blowing from east to west. And so this wave comes in from the west and it slows down because it's being blown westward. And that's the main reason why the thing is going this slowly. Now, I want to show you here what how the MJO, the Madden-Julian oscillation, matters to our global weather. We're going to look in the tropics here first, and the shading here is reduced rainfall, and the blue means enhanced rainfall. And I'm going to page through forward in time, and you're going to see the rainfall is intensifying over the Indian Ocean. You've got westward flow in the trough and more eastward flow in the ridge over here. And it builds a signal, a wave signal that goes all the way into the middle latitudes and around the world. So I'm going to back up to 1 now and watch you can see the rainfall moving eastward across the Indian Ocean to the Western Pacific. Back it up again. And now watch how the weather changes in North America. this is the way these events tend to behave in January. You get a ridge in Alaska and a cold trough in the east. This is a favored pattern for cold weather in the eastern United States. But as the rainfall pattern moves eastward around the world, comes to the region north of Australia, switches, and now you get a trough in Alaska and a ridge in the east. This signal helps explain why the weather varies across the middle latitudes. So I've explained what caused the MJO. It's a Kelvin wave that's slowed down by a headwind from the east over the Indian Ocean. Why is it important? It affects the day-to-day weather everywhere around the world, including whether it's wet or dry or warm or cold. Provides an anchor for weather forecasting. Finally, I'm going to show you it influences the development of El Niño. In the ocean, along the equator, the Pacific Ocean, warm water floats on the surface. And there's cold water deep beneath. But normally there's trade winds that blow from east to west, and they pile up warm water in the west. But recently, a Madden-Julian oscillation event has produced a strong westerly wind burst over the Western Pacific. And I'm going to show you what happened since March leading up to very recently. Watch how the temperature changes across the Pacific Ocean in response to that MJO event. You'll notice the warm water that was previously mostly just in the far western Pacific has spread from west to east across the basin, and the eastern Pacific has warmed, and this bottom figure now shows that the subsurface of the East Pacific is now 6 degrees above normal. This 6 degrees Celsius. These are bigger than degrees Fahrenheit, right? This is a big signal, and it's expressing at the surface right now as like 3 or 4 degrees above normal next to the coast of South America. It could become one of the strongest El Niño events that we've ever observed. So the summary about the Kelvin waves, they're one reason why weather regimes can set up for weeks at a time, and they explain how El Niño emerges differently each time. And in this case, we have a potentially very strong El Niño event emerging that's going to realign the weather for the next year around the whole world, rendering places that are normally dry, wet, and places that are normally wet, dry, and changing the temperature profiles all the way around. So it's an exciting time to watch nature evolve. Questions?
I think we will have some, but I wanted to ask you something. Adam Sobel, so thanks. That's, I love that stuff. Adam Sobel said last night that he thought that the MJO, the Madden-Julian oscillation, after 20 years, had been sort of, there was some beginning of a consensus about how it worked. And I wonder how that tied in to the Kelvin waves, because you were mentioning this connection.
So Adam Sobel has proposed a moisture mode hypothesis for the MJO, and a great many scientists have come on board with this. What I'm showing is what's going on in the upper troposphere. And I've demonstrated in my recent work that this controls the propagation of the MJO from west to east around the world. It sets up the phase speed as it interacts with the background wind. But the moist processes that govern the rainfall are sensitive to what's going on in the lower troposphere. And so evidently what's happening is this upper tropospheric Kelvin wave thing is helping to set the environment for the moisture mode or moisture processes that Adam is talking about, which then emerge and drive the winds in the lower troposphere. But my work has demonstrated that the propagation dynamics of the MJO are mostly dry, actually. They're up in high up in the upper troposphere, well above where the moist processes, the rainfall is occurring. But it's also forced by the rainfall, because the rainfall forces the Kelvin wave above it, which then propagates downward and then interacts with the temperature cross-section and influences the condensation and the development of the moist processes. I suspect that consensus is going to evolve toward a coupling between these upper tropospheric and lower tropospheric signals working together.
Okay, let me get to two of the viewer questions. One's from Hannah Palko. Says, not a quick one, not quite related to your talk, but is the temperature chart behind you quilted? It is lovely.
Yes, this is my wife is a fantastic quilter, and she took the data from the weather station on my roof at home. And every day for a whole year, she plotted the shading on this thing and then found the right color of fabric and stitched this thing all together like this. It's an astounding amount of effort that went into making it. She made another one that's on the wall at our house that's much, much bigger. But I love it. This is like just blending the science with the art. It's really special to me.
Oh yeah, thanks. And thanks to you for your question. LEB had another one that I wanted to ask, which is how do these satellite data? How do we get these satellite data about rainfall, and what kinds of satellites, for example?
Yeah, so I'm using really simple, simply made satellite data that have been available since the 1970s. The technology is really simple. It's like a camera that detects only signals in the infrared range. So it's signals associated with, we'll call it long wave radiation. It's like when you're standing next to a hot stove and you can feel the heat radiating to you. That's what this satellite is measuring. And the satellite moves across the world from north to south and south to north like this, while the Earth spins underneath it and takes pictures of swaths. And so it is able to then take the measurements and then record them in a large data set, which then people use to track the rainfall signals.
Amazing. Paul, thank you so much. It's been lovely to hear about your work and to see your art. Thanks a lot. There's other questions in the chat if you have time to answer those.
All right, cool. Thank you. You
sit through those. If you listen to National Public Radio, you get appeals all the time for money. We don't want your money. We want your action. We want you to be in touch with your elected representatives and help beat back a little bit this attack on science. I talked to you earlier about funding. There's a whole lot of reasons. Maybe I'll add some reasons a little bit later that are specific about why such a dramatic budget cut would be really devastating. I want to talk about another threat that you've heard about if you've been listening, which is the threat to the National Centers for Atmospheric Research. So for those of you just tuning in, the National Center for Atmospheric Research was established in 1960. It's an institution, it's in Boulder, Colorado, that maintains infrastructure that supports weather and climate research. And the administration has proposed to basically dismantle NCAR. Roughly, a federal judge found yesterday because they're annoyed with the state of Colorado. And I can't describe to you, others have described very well, just what a dumb idea that is, roughly speaking, because NCAR provides support to the entire academic community. And that includes, many, many students and trainees at various stages and undergraduates. But it also provides a lot of support to the commercial side of the weather and climate enterprise. And so this dismantling of NCAR, which came for purely political reasons, is another thing that we'd like to ask you to go and speak to to tell your representatives to push back on that. Okay, so our next speaker is Dominik Stiller, who is a Ph.D. student in climate science at the University of Washington.
Hi, Robert.
And there's Dominik. Hi. I will hand it over to you.
Thank you so much. Yeah, thanks for having me. Thanks for hosting. I'm Dominik. I'm a PhD student at the University of Washington in Seattle, and I'm talking about my research today on simulating Earth's energy imbalance over the last 1,000 years. Earth's energy imbalance basically tells us whether Earth is gaining or losing energy, and it's defined at the top of the atmosphere, basically where the atmosphere meets space. And at the top of the atmosphere, we have incoming solar radiation, and some of that is reflected right back to space, depending on the surface albedo, so how bright the surface is, like clouds and ice are very reflective. And then there's also outgoing thermal radiation. Basically, warm regions emit more thermal radiation. And if you add up those numbers, they cancel each other out approximately, but usually a small difference remains, and that's what we call the energy imbalance, or EEI. And a positive energy imbalance means that we're gaining energy on net as a climate system, and negative means we're losing energy. And this might seem like a kind of abstract metric at first, but the energy imbalance is actually the fundamental driver of any climate change. And so, for example, if we gain energy, the temperatures are heating up globally, the precipitation globally will be enhanced, sea levels are rising, and ice is melting on the sea and on land. So this is a really important metric that we should study more. And we know from satellite observations that over the last 20 years or so, we've had a positive energy imbalance. So that means we've been gaining energy. And if you look at the trend here, it's actually positive, which means we've been gaining energy faster and faster. And so looking at this satellite record, we can ask ourselves, for example, how much of this increase and the year-to-year variability can be attributed to human influence versus natural variability? How would this energy imbalance vary over even longer timescales, longer than this 20-year record can tell us about? And ultimately, we want to know what this can tell us about future warming. So to answer these questions, we have a couple of options at our disposal. And the first one would be to look at the satellite observations, which we already just saw. And this is the most accurate record. Those are direct measurements, but they only span this very short 2-decade period where we have a strong human influence. So it's hard to understand the natural variability. So climate models have been used a lot. We probably heard about them a lot already in the live stream. And typically there's an ocean model and an atmosphere model, and these two interact both ways. And by using these coupled climate models, we can extend the simulations back into the pre-industrial period. So at the bottom here, I have a little timeline. The satellite period starts in around 2000, at least for the series energy budget observations, and coupled simulations extend much further back, back to over the whole last millennium and even further. One issue, though, is that they disagree with satellite observations over this recent period, so they're not a perfect option. Option number 3 is to use an atmosphere-only model. So we're keeping the atmospheric component of the climate models, but now instead of having an ocean that reacts to the atmosphere, we are prescribing what the ocean is doing. So we're prescribing the sea surface temperatures, basically how warm is it at every grid point, at every time step. And those simulations then agree pretty well with satellite observations. However, the existing atmosphere-only simulations start in around 1870. So that's a short period, which means that we can't look at what happened before humans started influencing the climate system. And also the natural variability sample size is limited, especially for very slow modes that vary over decades. So for my research, I'm extending these atmosphere-only simulations to span the whole last millennium. So we're starting in 850 AD, and we're running these simulations up to the year 2000, which means that we're extending the existing simulations by more than 1,000 years, which then allows us to investigate these slower modes of energy imbalance variability. So how much energy is Earth gaining on these decadal to centennial timescales. And also we can look at what happened to Earth before humans started altering the Earth system. And that's currently in preparation with my co-authors. The atmosphere model that we're using is called CAM6, the Community Atmosphere Model version 6, which is the atmospheric component of the Community Earth System model. And this climate model is developed by the National Center for Atmospheric Research. And this is the one in Colorado that Robert was just mentioning. To run this atmosphere-only model, we need a sea surface temperature data set. And over the historical period, so basically 1850 onwards, we have pretty good instrumental observations. Basically, someone took a thermometer and measured what the sea surface temperature was. But going back even further, we need to rely on climate proxies. These climate proxies somehow naturally record the temperature. For example, tree rings are sensitive to temperature and moisture, and similarly for corals and ice cores. And we're using a reconstruction that's currently in review that's based on our prior work. And in addition to the sea surface temperatures, we also need atmospheric forcings. So over the last millennium, volcanic aerosols, basically volcanic injections, are very important, but also greenhouse gases and solar and orbital forcing. And we repeat this simulation 12 times so we can estimate the uncertainty in our simulation. And it comes out to more than 13,000 years of simulation, which is taking months to run. And these simulations are only possible with the help of NCAR's supercomputers, where we run these simulations and where we analyze them. These are way too computationally expensive to run on your own laptop. Okay, let's get to some results. These are the global mean surface temperatures that we are giving the model to simulate the atmospheric response to. So just to orient ourselves, we're starting in the year 850, and we're moving onward to the year 2000. On the vertical axis, we have the global mean surface temperature relative to the 20th century. And this shape of temperatures over the last millennium is called the hockey stick curve, because we have the slow cooling trend up to about 1850, 1900, and then pretty strong warming. And in blue, I'm showing instrumental temperatures very similar to the one that are used in the existing atmosphere-only simulations. And this shows that our proxy-based reconstruction, which is using these tree rings and corals, agrees pretty well with the instrumental measurements. So this is, gives us confidence that the simulations are correct. Okay, in response to this temperature trend, this is the energy imbalance that is simulated by the CAM6 simulations that we're running. And I'm showing these as relative to 1850, and negative here means Earth is losing energy, so negative energy imbalance. And we see that essentially over all of the last millennium, the energy imbalance was more negative than 1850, meaning that Earth was actually losing energy while it was cooling in this hockey stick curve trend. And that makes intuitive sense. If Earth is cooling, then it must be losing energy. And I want to focus on two key features now. The first one are these big spikes. Those are from volcanic eruptions. Basically, volcanoes emit sulfur into the atmosphere, which then forms aerosols. And these are highly reflective and reflect sunlight back to space, cooling Earth. And the second key feature is this kind of slow trend toward energy gain. So while the energy imbalance is remaining negative, it's slowly increasing and approaching zero. And this trend toward energy gain is actually a response of the climate system to the cooling. So the mechanism here is that when Earth cools, then there's less outgoing radiation, for example, thermal radiation, but also other processes play a role, which is called the radiative response, which then means that we're actually gaining energy, emitting less, which then counteracts the cooling. And this is typically, these feedbacks, this is a critical feature of the climate system. If this kind of negative feedback of cooling responding with energy gain or warming responding with energy loss were to happen, then the climate system would be unstable. So this is a very desirable feature. And typically we write this mechanism as the simple equation where the radiative response or the energy imbalance caused by the temperature change is proportional to the temperature, and the constant of proportionality is this climate feedback parameter. And a lot of people are working on constraining the value of lambda and narrowing down the uncertainties because it's a key uncertainty in predicting future warming. Essentially, if Earth were to emit more radiation in response to warming, that would dampen any greenhouse gas induced warming, for example. But one uncertainty in this lambda parameter is that it's actually a time-varying value. And so in my simulations, this feedback parameter lambda actually varies on decadal timescales, on centennial timescales. It has a pretty wide range. And so understanding what this range does to the climate is a key priority. And in our simulations, these variations are associated to this sea surface temperature pattern, mainly focused in the Pacific, which is called the interdecadal Pacific Oscillation. And it has the strong west-east contrast, which then changes what the clouds are doing primarily. And so by extending the sample size of variability that we have in our simulations by more than 1,000 years, this can help us constrain and understand the recent energy budget record and hopefully constrain future warming. I'll leave up my conclusion slides, but I do want to emphasize again that this research would not have been possible without the funding from the National Science Foundation and without the climate model and the supercomputers provided by the National Science Foundation's National Center for Atmospheric Research. And I'm happy to take questions now.
I wanted to ask, so sorry, I said love it, but I had muted myself. Thanks, Dominik. I wanted to maybe ask you to amplify something, which I think maybe not all of our viewers in Radio Land will understand. You know, you said that you reconstructed the past ocean temperatures from corals and tree rings and stuff like that, but you got a tree ring over there and you got a coral over here. And how do you go from these sort of widely dispersed measurements that are sensitive to different aspects of temperature and, you know, accumulate that signal over different time periods? How do you go from that to sort of maps that vary in space and time uniformly?
Yeah, thanks. That's a really good question. So there's a bunch of different methods, but the one that we're using is called data assimilation. It basically combines these sparse proxy measurements that are distributed all over and combines them with climate model simulations. And these simulations span the whole globe, and they can tell us about the statistical correlations between temperatures at all different places. And then we use a statistical method called a Kalman filter that essentially takes these statistical relations from climate models and compares them to the proxy measurements, and then gives us a full field that's combined both the proxies and the climate models.
Your colleague, Brian PM, has a fairly technical question, but I think we'll ask it anyway. So this is Brian Medeiros at NCAR. He says, CAM6, when driven by SSTs, that is sea surface temperatures that are not from CESM, has a pretty strong imbalance, EEI, in your framing. Do you have any kind of normalization to account for this? Or do you take the absolute imbalance over the full time series? You don't. Brian looks to be drinking a bottle of wine there, so I'm not sure how serious this question.
No, that is definitely a concern. So the absolute values are +4 watts per meter squared. So definitely much stronger than anything that would be reasonable, which is why we're showing the energy imbalance relative to 1850. So we're taking the 1835 to 1865 as baseline. And that's certainly an issue also with the historical AMIP simulations, because they also have, I think, like a +2, +3 watts per meter squared imbalance. But the anomalies are definitely useful.
There's two that are a little bit personal. I hope you don't mind, but it sort of speaks to how you're reaching people outside our field. Here's one from Kelsey Ward, who says, what made you choose to start a PhD, if you don't mind sharing?
Yeah, I think I just really enjoy research and kind of exploring topics, learning about topics. I've always liked to, so my research is very computational, and there's a lot of different types of research, like field work and wet lab research. I can only speak for a computational PhD, but I've just always liked to code and analyze data. And I think the PhD gives me the option to do that for 5 years, applied to like a really important topic. And also I think the PhD is great for being embedded in a community of people that cares about the same issues. I think all of science is like, it's really fun to talk to people at conferences and know these are people who think about exactly the same things as you.
Amen to community. Let me ask you a question in sort of just the last minute. As a PhD candidate, do you have any dream jobs or scientist heroes in your field? This is from LEB. If you had all the funding you wanted, what studies would you conduct?
I haven't thought about the second part of the question, but I think in terms of dream jobs, definitely working at NOAA or NCAR, those people do really cool work, and that's all federally funded, and they're at the forefront of science. So my future research interests are mostly in decadal predictions, so predicting the climate out maybe like 1 to 10 years, and definitely places like NOAA and NCAR are at the forefront of that. So I would love to be a research scientist there.
Thank you so much, Dominik. Good luck with your PhD. Shout out Washington.
Yeah.
University of Washington. We are going to switch to our next speaker in just a moment. But wait, I'm not done with you. I would like you to please call your representatives. We give you some tools to help you do that here on WCLS, livestream.com ACT. If you're not upset enough about the fact that that the U.S. plans to divest itself from decades of scientific leadership, if you're not upset enough that it wants to dismantle one of our nation's sort of shining scientific accomplishments, think about how it would feel if you were a scientist. I was trying to think of an analogy to this. Maybe I'll do it in the next hour. To have your work reviewed, your very technical, very complicated work, vetted not by your peers, but by a political appointee. I kind of don't care who's appointing the appointee. I just know that me and my peers are in a better shape to understand help sort the good ideas from the bad ideas. So on Friday, the Office of Management and Budget proposed a whole new set of rules related to grant making in the United States. They proposed that every single grant from every single federal agency, all of the ones in weather and climate, but all of the ones in medical research and every other kind of granting agency, would have to be vetted by the political appointee. Those are the people that do not spend their decades working in these agencies, but come in to advance a particular administration's agenda. So every single grant would be subject to political review. Every single grant could be terminated at any time for no reason. Every single grant would have to have its investigators reviewed for membership in organizations that this particular administration in charge deemed appropriate or inappropriate links. So if that doesn't sound like a good idea to you, and I'll be honest, it doesn't sound so great to me, then I would really encourage you to be in touch with your elected representatives. Please follow we will make that easy for you at wclivestream.com/act. But hey, do it any way that will get their notice, because that's a terrible idea too. Okay, our next speaker is a postdoc in the geoscience department at the University of Arizona. It's Ronnakrit Rattanasriampaipong. I'm guessing you're Thai.
Yeah. Yes.
And he studies lipids, and I'm going to just let you take it away. I'm dying to hear about this.
All right. Thank you, Robert. Hi, everyone. I'm Ronnie, and as you can guess from my last name, I'm a Thai postdoc right now at the University of Arizona. And today I'm going to make my talk a little bit like an introduction for paleoclimatology and how we can use lipids from cell membranes of microorganisms in the oceans to tell us about ocean temperatures in the past, over the past hundreds of millions of years. So why we wanted to study past ocean temperatures, as you may have heard from many speakers throughout these live streams, that ocean temperatures pretty much have a closely linked connections with Earth climate, and it's pretty much determine the weather patterns. For an example, the super El Niños coming up this year is making headlines, and it's expected to be one of the largest extreme El Niños, and that's pretty much the consequences that we can learn from past climate if we have a better understanding of how ocean temperature change in a much warmer environments. So you may have seen these Keeling curve from previous speakers showing that our atmospheric carbon dioxide concentrations have increasing over the past 150 years since the pre-industrials. And right now, currently, this is the chart from May 27th, showing that our current atmospheric CO2 level is roughly around 430 ppm, comparing to roughly around 280 ppm during the pre-industrial. And these pre-industrial CO2 levels is coming from the paleoclimate archives, like ice cores that they're trapped gas bubbles, and we can measure the carbon dioxide concentrations directly from the gas bubbles that trapped in those ice cores. And you can see that if we extended these CO2 records further back in time, so we have a pretty good collections of these ice cores that we can measure the CO2 concentrations over the past 800,000 years. So during these 800,000 year histories, we can see that our CO2 level in our atmosphere change. It's going ups and down. And every time when it goes up, it's usually staying around 280 ppm. And that is our interglacial period, including our current climate scenario. So we are living in a relatively warmer climate scenarios comparing to the past glacial periods where our atmospheric CO2 usually is staying around 180 ppm. And we can see that from the last glacial maximum, which is around 20,000 years ago, our CO2 increased about 100 ppm over the past 20,000 years. But with our carbon emissions from human activities, anthropogenic CO2 emissions increase our CO2 concentrations around 150 ppm over the past 175 years. And if we extended our CO2 reconstructions from paleoclimate archives further back in time, we can see that it was a period of time that our atmospheric CO2 was much higher than our recent histories. And it can be up to around 1,000 ppms, which is well within the future projections of our warming world when we're looking at those climate models that, for an example, Dominik just have shown you that we use those climate models to project how our Earth surface temperature will increase with the increasing amount of CO2s that come in from our carbon dioxide emissions. And reconstructing these ocean temperatures from the past greenhouse world would provide us a great extreme conditions that we can test our climate models and validate whether their future projections are reliable or not. And from my research, as I study archaeolipids in marine sediments, these are the organisms that helping us understand or know how warm the ocean temperatures in the past could be. So the way the proxy works is that these marine archaeas living in the surface oceans, and when they're living in the warmer or colder temperatures, they like to adjust their membrane lipids according to the water temperatures. So what we understand now is that these marine archaea like to add their rings into their internal membrane structures. And you can see from these cartoons that when the water temperature increase, these archaea trying to add the cyclopentane rings in their membrane lipid structures. And they're doing that to make their membrane a little bit more rigid in a warmer temperatures, because they wanted to prevent their like energy expense in the extreme conditions. So they're trying to make their lipid membranes better for living in a more extreme conditions. And when these marine archaea die, their cell membrane and lipid membranes fall down to seafloor and get preserved in marine sediments. And it's get transported from surface ocean down to marine sediments from in the form of these marine snow, which is the organic matters that come in from like when the phytoplanktons or zooplanktons eating some of the organisms, and then they died, and then they made like a fecal pellets, which is like a marine poop, and these poops falling down to seafloors. And there are scientific ocean discovery research vessels like the JOIDES resolution in the pictures here, which is part of the which is the research vessels of the International Ocean Discovery Program that has been drilled marine sediments from all over the world for over the past 50 years. And NSF is one of the major sponsors for these international ocean drilling program. Unfortunately, this program has decommissioned in 2024, and we still don't have any future plans for what we gonna have a supplement drilling ships for the IODP program for the US research. But just to show you the extent of how of the impact of how these IODP program made in terms of the scientific discoveries in earth science. So these are all of the drilling locations of IODP and their predecessor programs over the past 50 years. And their sedimentary cores we have on the left here, it's like a tree rings that recording climate informations over the past millions of years. And for my membrane lipid works, what we usually do is that we collecting the marine sediments from these ocean drilling cores, we grind them to homogenize the sediments, and then we extracting our lipid compositions using these ACE machines, which is like an espresso machines. We crunch a bunch of sediments, and then we trying to extract lipids under high pressure, high temperature conditions. After we get the lipid extracts from these marine sediments, we can throw our samples into these like liquid chromatography mass spectrometry and detect the mass of those lipids. And we can see the distribution, whether we have higher ring lipids or lower ring lipids. And just to make a quick note that archaeolipids, it's very important for greenhouse climate because it's only a few proxy system that we can reconstruct ocean temperatures in these greenhouse world conditions. And because of the time constraint, I wouldn't be able to like talk about my research in details, but I just would like to highlight that all of my PhD education and my postdoctoral training in the US as a Thai is all been supported by the federal research, federal fundings. I am a Fulbright student and supported by the Schlanger Fellowship Program, which is part of the IODP Fellowship for PhD students who study marine sediments. And I got NOAA Climate and Global Change Fellowship to continue my work as a postdoc here in the US. And the discovery I made relating to the archaeolipids, it's trying to improve the paleothermometer that we used them to reconstruct ocean temperature in the past. And just to quickly shows you how we have improved the paleothermometer through the discoveries I have made. throughout my PhD and postdoctoral journeys with the federal support. This is the map showing the temperature residues that have reduced when we incorporating some of the non-thermal factors that haven't been accounted in the previous versions of the temperature calibrations of these archeolipids, and incorporating these non-thermal factors, improving the ability for us to reconstruct past temperatures better with these archeolipids. And with that, I'm just going to end with this last slide saying that American taxpayers' money support international research, including myself, and to tackle global climate problems. And every sediment course that I study is also coming from the research drilling program that's supported by the American taxpayers' money as well. And with that, I'm ready for any questions that people may have.
Man, that was so fun. Thank you so much. I was getting a bunch of tea on Ronnie, like the fact that he has coccolithophore tattoos and the fact that he runs ultra marathons, 100-mile races and stuff. But let's go to some more. That was just such an interesting talk. I want to ask you all about fats. But maybe let's start with some of our viewers. So there's one from Kelsey Ward, which says, I think it's so fun when researchers and scientists from landlocked institutions do work with the ocean. It's like studying lakes from a university located on the top of the mountain. And I wonder if you can talk a little bit about how it is that you come to study something that's buried in the ocean floor from a place in a desert.
So as many of the speakers may have mentioned already, and especially for paleoclimatologists, we studied something that happened in the past. And our climate information in the past that we are studying is preserved in the sedimentary records. So it's just about how you collect, how you get those samples. But after we get those samples, whether the sample is coming from the open oceans, like 1,000 miles away from shorelines, or it's from lakes that is like 1,000 miles away from the desert that I am in, it's not impact our ability to reconstruct or collect information from these past climates, because we already have the sample materials that collecting from those remote locations that we can analyze and measure in our laboratory equipment and instrumentations anywhere in the world. I guess it doesn't have to be in the desert, but we can measure them anywhere.
Hannah Palco had sort of a more technical question. Does the increased number of lipids work like saturated versus unsaturated fats?
So yeah, so I use the oil and butter as an analogy when we see that the structures of the archeolipids change by having more rings in their internal structures. It's making the lipid molecules in their cell membrane can closely packing together, and that's making the membrane rigidity a little bit more saturated, and it's making it being a solid phase in the same temperature, comparing to if we have less ring, the molecule is clunky, it cannot be well packing. So it's more like an unsaturated fat. So it's loosely packed, and it's become a liquid form. So that's why I use the analogies of oil and butter to explain the change in chemistry of the lipids.
Ellie B had a question. Do you collaborate with a lot of paleontologists?
Not paleontologists in the sense that, for me, paleontologists is people who study macrofossils like dinosaur fossils and stuff like that. I have to collaborate with a lot of microbiologists because I study something is very tiny, and they don't really have a hard parts that preserved in the sediments. So these are all the like biomolecules in our soft tissues. So it's not like we have bones like dinosaurs that preserves in the sediments, but these are like how we be able to understand change in these like biomolecules is more in these microorganisms is more about microbiology rather than just the paleontologist perspectives, I guess.
So maybe could you showed these pictures of these little critters at the beginning, these little lozenges. How big are they?
It's they're very small. They're in like a micron scale, probably like 200 to 400 microns. So probably smaller than our hair diameters, I guess.
Okay. I think what I'm gonna do is say goodbye to you, Ronnie, but before you go, I want to highlight one of LEB's sort of comments, which is the International the other one, the International Discovery Program, and I love to see the collaboration. And I wanted to highlight that on Ronnie's way out, because I don't know if you noticed, I would be willing to bet that Dominik was also not born in the United States. And within my research group, we were having a conversation last night about what it's like to work in the United States. And I said, the US has maintained all this scientific leadership, not because we have all the smart people here. This is something Adam Sobel said last night. Not because we have all the smart people, but because we have been welcoming to the smart people from other places, including you. So thanks for coming and working here. All right, see you later, Ronnie.
Thank you so much.
When we welcome people here, we pay them, of course. And so one of the things that we would like to ask you to do is help keep this long-standing investment in scientific research paid for. And that payment comes from the federal government, of course, as it has been, since, well, mostly since World War II, but even before that. We really think this is a public good, and the proposal from the administration, the president's budget for next year is, of course, just as dire, if not worse, than it was last year. Entire research arms from the National Ocean and Atmospheric Administration, NOAA, that research arm is scheduled to just be dissolved. Funding for the geosciences in other agencies like NASA and the National Science Foundation is set to be cut by half. So there was a similar proposal last year, and thanks to public outcry from people like you, in large part, Congress, who has the power to make the decisions about where that money goes, directed the spending to be at or roughly unchanged over time. That lets us train people. And I wanted to maybe add, without outing anybody, I wanted to add sort of a personal story to this. I became a professor. I worked in weather forecasting and stuff like this for about 20 years, and I came relatively late to the university. And my first PhD student graduated about 9 months ago. And I have a bunch of great students. She is extremely talented. And she applied for fellowships all around the United States. And in my assessment, in a normal year, she would have gotten several offers. Every single one, with one exception. So of 7 programs that she applied to, 6 of the programs themselves were canceled. And she's now working in France. So the United States has lost the opportunity to train this person as a scientist to work in the United States, and she's instead moved to France. And not only she moved to France, she had what we dorks refer to as a 2-body problem. So we're partners now in France with her. So one atmospheric physicist, applied mathematician, one neuroscientist gone to Europe, and that's one of dozens that I know, and hundreds. And this is what happens when we don't invest in the future. And I would maybe point out too, if it's not obvious to you viewers, that this live stream is primarily almost entirely run by people in the early parts of their careers with the most to learn. So help them out, help us all out, get in touch with your representatives. We're making that easy for you in the crawl, in the cryon, down there, wstreamlivestream.com, please act. And now we will move to our next speaker, who is a documentarian, Anna Horn.
Hi, it's so nice to be here. This is actually my first time being on a live stream, so that's pretty exciting. Yeah, my name's Annika Horn, and I made a film about the Goddard Institute at Columbia University. And I made this back in 2025. This was after the climate lab there had been evicted. And so I will play this film and the story sort of speaks for itself. And I also wanted to quickly mention that the scientists who appear in the film they were speaking to me on their own time, expressing their own views and opinions, rather than commenting on behalf of an agency. So I'll go ahead and play the film now.
Working as a scientist in the US has not been normal since January 2025.
We got pulled in this big meeting with a lot of higher ups from NASA, and they were just like, you're moving out at the end of the month, nothing you can do about it. What? Why? When? What?
We were being evicted in an effort to save money for the government by Doge. Oh. Yeah, my friend, he did say that he was going to leave. It's too depressing. This belongs to the government, so I can't take it with me. Where do I begin this story? The city I grew up in is called Midland because it is midway between El Paso and Fort Worth, which if you are familiar with Texas, this would tell you it is in the middle of nowhere. When I was in high school, I was fascinated by genetic engineering. And I thought that's what I wanted to do. This was very hot stuff in the 90s. My teacher came into the room and she said, now, I know I'm supposed to teach you a section on evolution, but I'm not going to because I don't believe in evolution. And have you ever heard about analogous body parts?
When I was at GIS, I was a PhD student. Most of my research looks at droughts and extreme rainfall and what happens when those two happen at the same time.
My specialty is in the water cycle. So Goddard Institute for Space Studies, we do a few things. We produce this annual global temperature record. So if you read the front page of the New York Times, it says like 2024, hottest year in 100,000 years. That is one of the things we do that's most famous. Another thing that we do is we try to produce simulations of the climate. A lot of rain, drought, all the things that you can envision go along with climate change. Everything changed this year. So I guess this must be one of our screens. Oh. This is probably a fire code violation of some.
As I remember it, there wasn't really any justification given. It was just this guy at Doge says, you're out, you gotta get out.
And they did use the word Doge during this announcement. Also during this announcement, I heard that NASA had been told to keep paying the lease for now. And we all knew that we just barely had gotten in the building with this, fresh off the presses renovation. Our renovation is in fact still not paid for.
I guess it would be a lot easier to say that because GIST does a lot of climate science, that's why they wanted to kick us out. But I think, honestly, they were doing a full front press on all science. And so, just a few weeks prior, all that stuff for the grants to the National Institute of Health came down. So I think really they were just like, that seems like an easy target. Let's just do it.
And our lease did not end until August 2031. And so everyone was like, how did you cancel the lease? You signed the contract. There is no lease canceling.
one of the wonderful things about climate science data, and specifically the climate models that I work in, is there is a giant international project funded both by the US federal government and also governments all around the world to build these models and release them publicly such that anybody can download them. I can download them, you can download them. You don't have to get any special permissions. The worst you might have to do is set up an account. And then you can download terabytes and terabytes of climate data totally free.
So NASA in a typical year will have about 500 employees quit through natural attrition. They're retiring, they got a new job, whatever, about 500. This year, we're around 4,500.
We are losing data, we are losing people, and there's gonna be sort of a dropout during these years, which is gonna be very scary. Hopefully we can start building it back, but there's still gonna be a blip where we're gonna have less good data from these, this decade, maybe even into the future, which sucks.
Well, you're a bucket of cheer.
Well, thankfully, I kept in touch with Allegra and Miriam, and both are, continuing their work as scientists in various ways. So that's something to be happy about. And yeah.
So just for the viewers, I'll say that both Allegra and Miriam started the walk with Syl. They both walked from Central Park to, well, Miriam, I think, went all the way in support. And Allegra went all the way.
Yeah, and Miriam's been making all these videos and clips for just kind of showcasing all the people they're speaking to along the way, which is wonderful.
Let me ask you what inspired you to make that? I mean, it's maybe kind of a shallow question, but I'm just really curious how you came to that story and were inspired to make that film.
Right. Well, I made it about a year ago. Well, I kind of made it in two phases. So there was first I did the initial interview with Allegra, and Allegra I was connected to through an organization. I was living in Inwood at that time, way up in northern Manhattan, and so I think I had met Allegra through there, and she mentioned that this was all of this, historical data. And the library of materials at GIST and all of this was kind of going to waste, and they had just done this renovation and now they were being evicted, and it was all kind of shadowy about what the justification for these changes were. So she yeah. But I was already working on the kind of broader story of cuts to science because I had been following, the cancellation of grants from the NIH prior to this.
So maybe this leads into LEB's question for you, which is she says thank you, or he or she says thank you, but then asks, does your video journalism focus on the sciences, maybe in general?
Oh, it has since probably since the middle of 2025. Prior to that, I majored in history, so I had done some films about history, and that was more my focus. But this is, not a happy story. But in early 2025, my sister had cancer, and so we were trying to get in clinical trials. And this was kind of at the same time as all of the NIH things happening. And so there was like mass chaos at university hospitals where one would go if you need to be in a trial, as opposed to just do standard of care. So that inspired me to start covering science. I don't have a science background, so I just have so much admiration for the expertise and how long it takes to become a scientist. That's something I really admire.
Kelsey Ward asks if your video is available to share anywhere.
Oh yes, it is. Well, it's on both my personal YouTube channel, and then it's also on Crafty Short Films, which is a bigger channel that has distributed it there. I believe that I can post it in the chat, maybe, or
yeah, maybe in the YouTube chat, or
let me see if I
directors
can.
or other hosts is able to do that.
I'll put it. Okay. There's the link that
yeah, there it is. Oh, yeah. Let's see. I can't do it. Oh, Ash. Yeah, there you go. So we will get that posted in the chat. Other questions? It's so interesting to me in this year's. Yeah, there you go. Thanks. It's so interesting to me in this year's live stream how many people have wanted to sort of speak to and support science in general, whether in climate forecasts in particular, weather and climate science in particular. Has meeting those folks and looking at what they're doing, has that inspired you to pursue other documentary ideas?
Yeah, I've done, I think, 4 shorts covering various topics in this kind of broader umbrella of science funding since 2025, and I'm continuing to work on some. I'm going to be publishing one with Noam Ross, who is one of the founders of Grant Witness, and that's a big open source project that's aggregating all the data of what's been cut. So it's kind of a story of how he and his co-founder created this archive that I think will be very helpful in future years.
Yeah, let's not hope too far in the future.
Yeah. I mean, it's been helpful now. I've actually found some initial stories through Grant Witness.
And one thing I notice is Miriam is relatively early in her career, and Allegra is let's say mid-career.
Mm-hmm.
Do you find that they had different sort of perspectives on this experience? I would imagine that for someone like me, well, both of them maybe, it feels like getting their feet kicked out from under them, but I wonder if their perspectives wind up being different in ways that, yeah.
Yeah, I think so. I mean, well, first of all, Miriam also is a video creator and has a very great YouTube channel that you can follow. And she had a background in journalism before, I think, beginning her PhD. And Allegra is someone who is pretty illustrious in the field already and has been a federal scientist. So this is less the case now, but before, if you're a federal scientist, you have pretty good job protections, and so I think that maybe Allegra felt that she had a bit more discretion to comment publicly, and I really admire that they were both so brave to kind of speak so candidly about their experiences, because this was in a really turbulent time. I mean, it still is a very, very turbulent time to publicly comment on anything about politics. So yeah, I know Miriam she's continued on in science, and that's very great.
She's working for my next door neighbor, actually. I mean, at my work. So LEB asks if arts and documentary funding is also under threat, and whether that's affected your work at all.
Yeah, I think arts funding has typically been quite precarious. There has been a lot of cuts to government funding for the arts, and also there's a bit more of, well, I guess the big story is like ITVS, the funding arm of PBS is kind of kaput. So public access documentary kind of oriented, like broadcast TV was a big distribution outlet for documentaries in prior years. And, PBS is now doing things with YouTube that are really innovative, but definitely the funding opportunities for documentary and journalism are much diminished from what they were.
Interesting.
I think that's sort of part of a larger pattern, though, that has even begun for many more years, sadly.
You mean specifically for documentaries, or do you mean for?
Yeah, because well, there was like a big boom of documentaries for a few years, and then since then there's been so much consolidation. So there are just so many fewer companies that will buy and distribute documentaries, and that's something that's accelerated for sure.
There's so much love in the chat about PBS. It's sort of crazy.
yeah. It's, I mean,
well, tell your
but
Congress.
there's still many ways to support PBS. I mean, it's not all public funding. So if you can afford like the PBS passport, it's a great investment.
Okay, super cool. Thanks for sharing that with us, Annika. That as sad as that might be. Okay, and so we will go to, well, we will not go to our next speaker. I will harangue you for a few minutes, and I'm going to do it on schedule, if that's all right. And I'm going to do this. I'm going to encourage you to call your Congress critters according to the, you can follow the instructions here, livestream.com/act. We've talked about what happens when you don't invest in science in the US and how that changes the culture of science really for the worse. We've talked about why it's important to fund science, and that's partly that if you're worried about practical things, there's practical reasons to keep funding science. And if you're worried about impractical things like what the country supports as a culture, it's also important to do that. We have a particular sort of point of focus in our field, which is the National Center for Atmospheric Research, located in Boulder, Colorado, established in 1960, and supporting all of weather and climate research in the academy, that is to say at the universities, really across the federal government in some ways, and with tendrils deep into the private sector. So you may, we've seen over the course of the live stream examples of NCAR making aviation safe, making weather forecasts better, developing technologies for observing our planet up close, things down to the scale of individual cloud drops and very large, pioneering work in GPS, which helps your phone tell you, where you're at, which end of the subway station to get out of. And so, all of this is under threat. The administration has tried to destroy NCAR, to dismantle it. They tried to give the supercomputer, they said they were going to give the supercomputer away. Then they offered the supercomputer to the University of Wyoming. So the fact that they didn't know that ahead of time maybe tells you that all they were trying to do was bust the place up. That act that was the subject of a court order earlier this week. And so that particular act is now under injunction, but much of the threat to dismantling NCAR, which is still present, and that is very much a political act. There's no real, no scientific justification or organizational justification given for it. And so, among the things we'd like to ask you to do is to call and write and get in touch with your elected representatives and put pressure on them to have the administration back off to support NCAR in its current form or something like it as a resource for both the private and the public good in the United States. And with that, we will move from the arts toward and communication back towards the technical side. And as we do that, we will have Shel Winkley come and speak to us. Shel is the Senior Engagement Specialist and a meteorologist at Climate Central. And maybe among other things, you can tell us what Climate Central does. Look forward to hearing from you.
Yeah, and I would say we're going to stay on that communication arc. So this weave together perfectly. And I will also add, huge PBS fan. I grew up on PBS. I actually just had a chance to go hang out with a bunch. This is not part of the talk. This wasn't planned, but there's a great new series on PBS called Climate California. It's put on by NorCal Media. It's syndicated across the United States, but it's a really cool just way to see how climate change is impacting communities around the state of California. So I highly recommend checking it out. I believe it's on YouTube also, if you don't get your YouTube film. Yeah, okay, so let me tell you about Climate Central first. My name is Shel Winkley. I am a meteorologist. I spent 17 years as a broadcast meteorologist here in this great state of Texas. I spent some time in the Texas Panhandle, and then I spent most of my time in Bryan College Station, Texas for the CBS affiliate. Past couple of years, though, I've been working with Climate Central. I actually used Climate Central's resources on air for about a decade here in Central Texas. But what we do at Climate Central, we're a nonprofit, non-advocacy that is basically doing science for communication. We can do science really well. We can do data very well. We localize that, especially for about 200 and 245 US cities here in the United States, because the one thing that we can do is the science and the data, but the one thing that you can do, your local meteorologist, your local journalists, content creators, is that they can really tell the story and why it matters to cities. So with that, that's kind of my spiel there. But one thing that we do here at Climate Central is what is called attribution science. And as I started putting this together, I didn't want to assume that everybody knows what attribution science is. So we'll kind of go into that. But what I really want to touch on is how we can use this new science in order to tell the stories around climate change, why it matters to individuals as they walk out the door. To start with, though, kind of like we're dealing with a lot of things, the communication landscape today, you're part of it. The way you get your news has changed. People aren't sitting down for appointment television anymore. So we call this a broken shards of glass media. You're getting a lot of algorithm-friendly, short-form video that's likely coming into your algorithm because it's something that you're already interested in, which means that we're not getting good information or even correct information in the places that they need to go. We know that feeds are full, though. There's so much content. There's only more coming in as AI continues to just fill our feeds. And that's one thing that people are pulling back from even social media for. But we know that it doesn't always land because of just the tone that it might take. And of course, there's a lot of dancing on the internet also, which sometimes that resonates for people. So if that's the way you get your news, as long as you're taking in good information, then don't let me tell you how to look at your Instagram feed, essentially. But what we do know, and this is kind of what leads into the talk today, is that most people are really, the Yale program on climate change communication, they do research every single year. We know that over 70% of Americans know that climate change is real. And a majority of those Americans understand that climate change is caused by the burning of coal, oil, methane gas, by putting this heat trapping pollution into our atmosphere that essentially has put this big blanket over our planet. But I think the biggest thing about it too is that a lot of people are concerned about climate change, but they don't think that maybe their neighbor or their friend or their family want to talk about climate change when really they do. And we have this tool that can help us. It is attribution science. So we know that primarily the warming that has occurred has been because of CO2 in our atmosphere, along with methane gas. And here in the United States, here's kind of the breakdown of how that heat trapping pollution gets into our atmosphere. A majority of it is from the way that we get around, from airplanes, from cars, from the way that we ship our materials, and then all the way down to agriculture, which is about 10% of those greenhouse gases. So what does attribution science do? Essentially, we're comparing what the world would look and feel like today if we hadn't put heat trapping pollution into the atmosphere versus what we're experiencing today. So we're taking these two worlds. Here at Climate Central, I'll show you the tools that we use, but essentially we're running a lot of climate models. And at one time, as we run it through, we're putting all of those historical emissions from this heat trapping pollution that we've put into the atmosphere, and we're running those models. And then we're going to take that human piece out and we're going to run them again. And what you get is a ratio. And that doesn't tell you necessarily that a storm was caused by climate change, that a heat wave was caused by climate change. When we talk about storms, we can do this really well with tropical weather. I say that a hurricane was always going to hurricane, but we understand that we took this natural disaster and we made it a little more unnatural. So if that's what attribution science can't tell us, what can attribution science tell us? What can it inform us about? It can tell us a change in likelihood. How much more likely was that weird heat that you walked out to this morning? How much more frequent is that going to become as we continue into the future, as climate change, as this global average continues to go up? And what I really like about attribution science is it can answer the question of change, of intensity. So we understand that this storm produced this much more rain, this much more wind. But what I really like about the science is that, that was a terrible event. Take a Hurricane Helene, a Hurricane Milton, flooding, whatever it might be. We know that that event was bad, but it's done and it's over with. So how do we move forward? This can help us understand, okay, we're at a world of about 1.2, 1.3 degrees Celsius above the pre-industrial average. In a similar world, and we warm it to about 2 degrees above that pre-industrial average, now we understand that another storm like this will produce this much more rain, or this much more wind, or the heat would be this much more likely. So it helps us understand the impacts of what we just went through and how it could happen more soon, as well as maybe even more intense. So we can almost always do this with temperature, heat. Is it cold outside? How much more rare is that becoming? Marine heat waves, sea surface temperatures. We can often do it with fires, with hurricane intensity, with rainfall, with droughts. It's really hard when you get into things like severe weather, specific mesoscale events. We can't really say about hurricane frequency, but we can understand, some of those broader patterns and then tie it back into the attribution science that we know. And essentially what we're saying is that the climate that we're now experiencing today, that we're gifting to future generations, is not the same that we were gifted by our grandparents, that our parents. I think that's one of the biggest communication techniques that I like to use. Okay, so all that to be said, here's how we do it at Climate Central. We use what's called the Climate Shift Index. This is global, this is daily, and we can do it across a couple different ways. One of those is going to be air temperature, what you're experiencing today. One of those can be sea surface temperatures. We can look at that across the entire basins of any ocean that you want to look at. But again, what this is telling us is it really helps us understand the why. And even if we see a big heat wave coming, we can use our forecast tools. So ours is based off the GFS model. And we can look ahead to say, okay, we know the National Weather Service is issuing heat alerts, heat advisories, excessive heat warnings. Does this have a fingerprint of climate change to it? Again, likely would have seen that heat wave, but would it have been this intense or this long if it wasn't for a fingerprint of climate change? So let's put this into practice. Starting on that storytelling arc, we know if you think back to March, that big Western heat wave they were experiencing, 42.5 million people experienced unusual excessive heat that was made at least 3 times more likely to occur because of climate change. So there was a strong fingerprint of climate change. 29% of the United States experienced a CSI of 5, a climate shift index of 5. What that means when you get to the top of the scale is that these temperatures in March would have been almost virtually impossible if there wasn't an influence of climate change involved. And what I think was the most striking about this event, and the reason I pulled it out, is because we can go back, the data goes back to 1970. This is the largest footprint of a climate shift index of 5. That was almost impossible that we've seen in the United States since 1970. So that's the land temperature. And then as we look at the ocean temperatures, that scale is bigger. It's 0 to 1,000 in terms of the scale. And the reason being is that it's easy to change the temperature on land. It's not so easy. You need a really big scale event to change the temperature in the ocean. But ocean attribution helps us understand hurricane intensification. That's probably the biggest headline you'll get from it. But also coral bleaching, ecosystems that are struggling because of the marine heat wave. We got a pretty big marine heat wave happening in the Pacific. A lot of birds are left without food. Some of that ecosystem's not matching up because some of those fish have tried to move on to cooler waters. So where we can use this, and I actually changed this morning because I thought it was pretty interesting, but we can use this information. So right now, the Gulf of Mexico is running at near record levels for this time of the year. The Caribbean is up there too. The Caribbean's running about 1 degree to 2 degrees or so Fahrenheit above average. So I wanted to pull in the loop from this morning over the Gulf of Mexico. You see all the clouds, the thunderstorms swirling there. There's a lot of wind shear. We don't have concerns that a tropical system will develop, but there is just a buku of tropical moisture that is spinning around the Gulf of Mexico. And as high pressure later in the week digs down the East Coast, brings down some cooler air, also brings down drier air, and a rainmaker moves in from the west, essentially what it's going to do, those red colors you see, this is precipitable water, rain-making water, that's going to get scooped up and just ooze into parts of Texas and Louisiana. And so we understand where the moisture is coming from. And we know that rain at this time of the year in the Gulf Coast, especially tropical downpours, isn't unusual. But what we do understand is that we have created this bigger bucket. And when the right weather system comes along, we understand that the bucket can get tipped and you can create more rainfall from it because a warmer atmosphere holds more moisture. So this isn't saying that, climate change is creating the big potential for rain as we go into the end of the week that could lead to some flash flooding. But what we are understanding is that these rainfall events are getting heavier. The rain is falling faster. That creates the potential for more flooding. We understand that because of this bigger atmosphere and where the moisture is coming from. Warmer oceans means more evaporation. So that's one of those ways to put that last, but why? Why was this one different? Well, here's one piece to it. We've got these weather pieces, but here's how climate change plays into it as well. And so then we can really drill this down. So weather is one way that we get in, but then let's talk about the things that we care about the most. We know that climate change is impacting our expecting mothers and pregnant people. We used attribution to understand last summer that in the US, climate change has added about half of the average annual days that there's heat risk for our expecting mothers over the last 5 years, particularly across the desert Southwest. And then you can open that up. Okay, why does it matter? Well, here's the risks that are, already facing somebody who has a really big job on them already. We know that this added heat can cause X, Y, and Z. The other thing that you can do is put it to the things that people love and they cherish, right? After a long day, maybe you just need a piece of chocolate to unwind. Start of your day, you really love a good cup of coffee. We can use attribution science to understand how much more harmful heat is being added to the regions that these products are being grown. To not only understand how those are being impacted, but also then we can bring it to your wallet. How much more are you paying? We know that it's not the whole story, but we know that it's a big story, is that when we can't produce as much, that supply and demand factor comes into play. And we know that climate change is adding more harmful heat to both coffee growing regions, as well as chocolate growing regions, cacao growing regions. And then we can have a little bit of fun with it. I think that's the biggest piece of this, is that we don't have to, climate change is a big stressful topic for a lot of people. So when it came to chocolate, I threw on my best pink tuxedo and we did some social media reel around it to talk about how it's impacting you, right? Make the science really easy and accessible, and then really put it into the pocket of people who understand and who really love chocolate, get into their algorithms. We can do the same with these heat waves. We can really just break this down and help them understand, yes, it's summer. Yes, it's supposed to be hot, but it's not supposed to be this hot. And we know that these heat waves are happening more frequently. Wouldn't it have been possible without climate change, so on and so forth. And I think the last part that I'll bring to you here is what I think is potentially one of the biggest impacts that we can have as a community this summer. It's around the World Cup. We know there's 16 host cities across North America. This has an opportunity to reach people who don't normally get climate change in their algorithm. And I'll bring this up. This was a post that was shared recently on the ESPN FC Instagram. It was of the French team who has just gone through a pretty historic heat wave themselves over the past week, struggling before they even made it to the United States for the tournament. They were struggling just in practice. And some of the comments there, one, the first one that pops up, they make millions, they'll be all right. Just because you make millions doesn't necessarily mean that you can play better in the heat. Or this one, these princesses won't last in construction. So it's a way to connect why the heat is impacting the players that you love, as well as the sport that you love and the games that you love. Because while some people may use chocolate or coffee to maybe wind down or just not think about the world for a little bit, a lot of people look at soccer as that entry point. So we can use attribution looking at the host cities. This is available at climatecentral.org. We looked at all 16 host cities. The hatched areas that you see, those are the amount of extremely hot days above the 90th percentile in June and July that have been added because of climate change. I picked Guadalajara because it's where the first matches will be played. And I picked New Jersey because it's where the last match will be played. We don't know who's going to be in that final game in New Jersey, but we understand that the odds of a match that has heat impairing player performance is likely going to be one of the higher ones there. And you can see in the 2020s that anywhere from 2 to 8 of these extremely above average days and above the hottest that you would expect in New Jersey have been added because of climate change. And then just kind of a preview for what is coming tomorrow. We have a second analysis that's coming out that's looking at performance impairing heat at nearly every single match in the World Cup. So this is where we can use the science to say, okay, we know through a tool that'll also be live tomorrow at 6:01 a.m. Eastern, you'll be able to go in and look at your favorite team, a match that you're interested, a host city, the tournament overview, and we could use Era 5 data along with attribution science to understand what the probability is of performance impairing heat, and then how much of that was added because of climate change. This is not released yet. This is kind of a sneak peek of it, but I wanted to show you this is kind of what that looks like. So the second match of the World Cup happening in Guadalajara on June 11th, the match between South Korea and Chechnya, 88% chance, just knowing what we know about historical odds, of performance impairing heat. But without climate change, that odd would have only been a 68% chance. Where I think this is really important is if you have a team who maybe has lost, then there's a chance that you could say, you know, if you're trying to figure out why was my team playing so bad, who can I be mad at? Why should I be mad, right? As you get passionate about your football team, you can help to understand maybe it wasn't the team play. It wasn't what you had set forward. It wasn't what we were planning to do out on the pitch. There's a chance that along with the opponents on the opposite side of that pitch, heat was also an opponent that's being an impact for players as they're trying to get out there and make their way through this beautiful tournament. So that being said, I'll pitch this as well if you're interested. I know the live stream will still be going, so I'm not saying join us live, but if you use that QR code to get signed up, we are going to have a webinar tomorrow that goes through all the science. We're going to talk to 2 professional soccer players who have dealt with heat and really it's a lived experience for them. And so if you get signed up, we'll send out the recording tomorrow afternoon so you can also get their understanding of it, understand the science a little bit more, and take that with you as well. Plus how you can get to that hub that has all the information for you. So that is it. That QR code will get you to our resource section. We have resources for essentially anything you're looking for. Is it solutions? Is it trends? Is it summer weather? Is it urban heat island effect? However you want to tell your climate change story and localize it to your community, we have those resources for you right now. Everything you saw today and everything that you see on our website is 100% free to use. We want you to get the science out there. We want you to get the data out there. If you think that you're not a storyteller, if you think you're not a trusted messenger, I guarantee you that somewhere in your life, there's an intersection of people who really want to hear about you talk about these things and really help them understand why it matters to them. And so we can help you do that at climatecentral.org.
Thanks, Shell. We're running a little tiny bit late. I was going to show off my cats, but I think we'll skip that. 2 people asked related questions. We'll just maybe show future ghosts if you could be a little quick in answering this. You know, you tried to tie this to particular luxury agricultural products, and so Future Ghost was asking if there's efforts to develop more heat tolerant, in this case, coffee plants.
Yeah, that's actually happening right now. And what I really think is interesting is as we see growing regions shift, I'm here in Texas. I know that there's been a push to even try to see if we could grow coffee plants in Texas. So there's the tolerance aspect or different varieties that you can consider, but also some people are starting to experiment and say, okay, if our climate is warming, are there other regions where we can actually grow these crops?
Yeah, interesting. I'm married into wine, and there's similar stuff happening there. Also very temperature sensitive, you know, climate sensitive crop.
Right.
All right. Well, thank you so much, Shell. That looks amazing. Looking forward to seeing that.
Yeah, thanks for having me.
All right. I'm back to badger you, to please, to request, to plead, to do everything I can to ask you to be in touch with your Congress critters. And tell them what a terrible idea it is to destroy the American scientific enterprise, and in particular that the enterprise that's related to weather and climate. The one that was the one that's new that dropped last Friday, and maybe you've missed it because it hasn't been reported, was a proposition or a proposal by the Office of Management and Budget to basically have politics take over, be the final word in the entire scientific process. So that is, every grant would be approved in person by the political appointee, the person who shows up at the beginning of some president's term to run an agency that they've never seen before, to make grants able to be rescinded at any time for any reason, to prohibit grants to people who have belonged to threatening organizations, which might wind up including, I don't know, the American Geophysical Union or the very un-American American Meteorological Society. This extends not just to weather and climate science, it's science-wide. It's a terrible idea. I was saying to somebody maybe last night that, it would be probably possible to extend political control over the entire scientific apparatus, but the apparatus would be a smoking ruin. And that's not what we need under any circumstance, basically here in the US or really anywhere in the world. So please apply pressure where you can. Talk to your friends and neighbors about this, but really especially call your Congress critters. With that, I'm going to bring to the stage Margaret Duffy, who's an early career scientist, and I just found out recently a second generation climate scientist. I knew your dad's name and I knew your name, and I'd never made that connection. But anyway, one of dozens. Andy Dessler was on last night. Chris Brotherton got some shout outs. Anyway, it's sort of lovely. So I didn't realize you were a new professor of climate science. Where are you going to work? Where are you going to be?
The University of Utah.
Oh, excellent.
Yeah.
Congratulations. We'll take it away, Margaret.
Thank you. Thank you so much. Yeah, so you just made the comment about the proposal to have political appointees approve our science. And I kind of want to just highlight why that would be so damaging. One reason why it'd be so damaging, now that I'm starting as a new professor and thinking about mentoring PhD students, a PhD is longer than the appointment of a president. And so, having kind of the political situation change for us every 4 years is so disruptive to our work. Our careers are longer than 4 years. A PhD is longer than 4 years. And so having these big swings in funding on timescales that are shorter than the length of our projects is really just adds a layer of difficulty to making our science happen. So with that, I want to talk about some stuff that I'm really excited to share with you. It's new for me. It's heat and humidity, humid heat events. Last year I came on and talked about cloud feedback. So you'll see this is kind of a new topic for me. I'm trying to expand my horizons a little bit. And I just love learning about things that are interesting in the climate science world. And this is what's gotten my interest lately. So this idea, okay, it's not the heat, it's the humidity. You've probably heard people say that. We've probably all experienced this, right? If you go, it's 80 degrees Fahrenheit in a dry climate, feels very different from 80 degrees Fahrenheit in a humid climate. And so that difference can be measured with what we call the apparent temperature, which is not a definition of temperature itself, but more of a concept. And so something like the real feel or the feels like on your phone would be the apparent temperature. So the motivation for trying to incorporate the humidity into the temperature is that the heat stress mortality and heat stress morbidity scale not just with the dry temperature, but with the temperature and the humidity together. And actually other things like wind speed also play a role, but I'll focus on heat and humidity for today. And of course, as the planet warms, we're seeing more and more of these extreme heat and humidity events. And this is a little figure here from the most recent IPCC report, I think, showing in red regions where what we call the wet bulb temperature, so one of the measures of apparent temperature, where that's getting more frequent, the extreme events. And then in blue is where they're getting less frequent. And we can see that pretty much the whole thing is red because the extreme heat and humidity events are becoming more and more common. Okay, but actually, despite how important of a subject this is, there's a lot of debate, a heated debate, if you will, about how to best measure the apparent temperature, the feels like, or the heat and humidity together. And this is kind of where the climate science and human physiology meet up, because what the best metric is really depends on our body's ability to process heat and deal with heat, and when we start to see the impacts of extreme heat and humidity. So I'm going to emphasize two metrics here. There's actually a lot of different measures that combine heat and humidity together, but I've kind of noticed two front runners in the climate science world, the wet bulb temperature and the heat index, and so I'll talk about those. These are similar to something like the feels like or the real feel that you might see in a forecast on your phone. I think those algorithms are proprietary, but they combine temperature, humidity, and sometimes things like wind speed too, to give you a sense of what the feels like is. And it can be really different from the dry temperature, which is why I'm so glad that the climate science community is picking up this subject. So for wet bulb temperature, there was a paper that came out 2010 that noted that spending kind of any significant amount of time in wet bulb temperatures greater than 35 degrees C would be fatal. Even if you're like very fit and very well adapted, there's kind of a fundamental limit of survivability at 35 degrees C wet bulb temperature. That's different from 35 degrees C dry temperature. And they noted that you start to see these temperatures emerging around 7 C of global warming, which thankfully we're not close to that, right? We're still around the kind of degree and a half mark. But obviously, like, you know, getting to that point would be really detrimental. And so we want to study that and avoid that. And then a couple of years later, Liu and Romps argued that actually maybe the heat index is a better measure of the apparent temperature, more relevant to the human physiology. And they found this to be fatal at 93 degrees C, which again, this is heat index. So it's not the dry temperature and it doesn't compare with the wet bulb temperature. They're different metrics. And we start to see this kind of fatal heat index, they think, around 10 or so degrees C of global mean warming, which again, we're thankfully not close to, but we would want to avoid that. But I think, you know, this is all very idealized. These are sort of like fatal temperatures, no survivors. This would be obviously really horrible. And so this assumes, you know, lots of wind, lots of shade. Nobody's working or exerting themselves. Everybody's fully acclimatized. It's healthy. It's young people. There's no underlying conditions. Nobody is pregnant, which I was pregnant last year and the heat was really tough. The summer was really tough. So, you know, that's a whole other thing. Anyway, there's a big kind of debate about the best metric to use. And we're realizing that there are temperatures at which basically like even the healthiest people wouldn't be able to survive. And we, of course, want to really avoid reaching those temperatures because that would be really scary. Thankfully, we're not close. I'm not trying to scare anybody here. You know, that's what we've been studying. So I'm going to talk about the wet bulb temperature for the rest of this talk, but I want to kind of acknowledge that there's a lot of thought that maybe the heat index could be more a good metric too. So when we talk about the wet bulb temperature, what I've done is I've gone through the observational record and looked at the events where the wet bulb temperatures are the highest and just looked at the meteorological conditions that lead to these really high wet bulb temperature events. And so here's one example that happened in Iran in the year 2000. Sorry, my date got cut off here. But this is a wet bulb temperature in Iran in August, wet bulb temperature event. So here's the Persian Gulf here. Here's Iran, Iraq, Saudi Arabia. I made this graph before there was a war. I looked at, so this is the wet bulb temperature map. And then I actually decomposed the wet bulb temperature into the contributions from temperature and humidity. And we can see when we look at this, like this is really a humidity event. And so, you know, in the olden days, when we would have studied this using just the dry bulb temperature, we would have missed this event because there's really nothing interesting happening temperature wise, but there's a really high wet bulb temperature because of the humidity. And we can see this in the graph as well, where the green is the humidity and the blue is the wet bulb temperature and the orange is the temperature. And there's really nothing that interesting happening in the temperature. This is just the diurnal cycle, day and night, day and night, day and night, day and night. And then we have these huge spikes in humidity that are driving really high wet bulb temperature events. So this is really motivating why we should care about the role of humidity in extreme events. So this event and many others are driven by the humidity. And so then, okay, so what's driving the spike in humidity? So this is, I wanted to know what was happening there from kind of the meteorology of that day. And so again, here's the Persian Gulf down here, which is a very warm body of water, which contributes a lot of moisture to the atmosphere. And the wind barbs here are showing that the wind is pushing the humidity over into Iran. And yielding this big buildup of humidity right here in Iran. And this middle panel is showing us the topography. So red means that there's a mountain. So it's getting trapped by the mountain, and then it's getting trapped. This graph is showing us that it's not moving up vertically. And so we're getting a really big buildup of humidity at the surface that's coming from over the Persian Gulf in this particular event. And so what I've been interested in lately, this is, research to come, is whether climate models are able to capture these really hot and humid events. And so what I'm showing here on the top panel is the observations of the highest wet bulb, like the single highest wet bulb temperature from the years 1979 through 2024. So the yellower colors mean a higher wet bulb temperature. And then here's an estimate from the EC Earth climate model. I'm sorry, the formatting got a little wonky when I uploaded my slides, but here's the estimate from the climate model in panel B, and the difference is in panel C. So where it's blue is indicating that the climate model is underestimating the wet bulb temperature, and where it were red, if there were any red on this graph, that's where the climate model would be overestimating the extreme wet bulb temperature. And we can see that we are systematically underestimating the extreme wet bulb temperature events in this climate model. And so that's what I want to understand. I want to know why. Why can't climate models capture this very well, or at least not this model? And so I've been trying to write some proposals to get funding to understand the ability of climate models to represent these extreme humid heat events. But obviously, I think as you've heard, the prospects are kind of dire right now. And there's not a lot of funding at the federal level. And so I'm not super optimistic that I'm going to be able to get funding to work on this, which is too bad, because I think this is super interesting and exciting. So I will stop talking and take your questions. Thank you all for listening, and I really hope that you are enjoying the live stream.
Thanks, Margaret. Yeah, congratulations on your professor position, and I'm really sorry it's the funding is such a mess right now. It's pretty discouraging. Could you talk a little, like, just for my edification, could you talk a little bit about how the other heat index works, and why at some level of detail why there's any controversy at all? I mean, you sort of said it has to do with human physiology, and okay, I don't understand that, but yeah.
Yeah, I don't either. But yeah, so the idea behind the wet bulb temperature is like basically to incorporate the impact of our ability to sweat. So, obviously when we sweat, then there's liquid on the surface of our skin, and that sweat evaporates, and that has a cooling effect on our bodies. And then, of course, if there's more humidity in the atmosphere, we can't sweat very well. The sweat doesn't evaporate very well into the atmosphere, and so that doesn't give us that cooling effect that we want. And so the wet bulb temperature is meant to kind of be like the temperature that you would get if you wrapped a thermometer in a damp cloth. So that's kind of the thinking behind the wet bulb temperature. I'm actually not sure exactly if there's like an equivalent way to think about the heat index, if there's like a kind of catchy thing like that for the heat index. But it's a similar metric in the sense that they both like incorporate the temperature and the humidity together into one number. And so that's kind of the idea behind having multiple metrics, or behind having a metric that combines temperature and humidity. But it's really interesting because, like, I think a lot of it seems like there's not like a single, my reading of the literature, which is not a perfect reading. It's like, it seems like there's not kind of a single metric. Like, it seems like it depends on like the region and the level, how acclimatized people are. And so that it's really like actually a complicated problem. I've mostly been working just on the like meteorology side and like what the atmosphere is doing. But it's a really, it's interesting that we kind of haven't pinned down like one measure that's the best for measuring heat stress.
Okay, I have a hard-hitting question from an NCAR scientist. Are you ready? Brian PM asks, do moist heat waves get more worse like hot days? Brian's drinking saying this apparently.
He's what?
His little icon has him opening a bottle of wine. So
yeah, well, we're gonna need it with the current funding situation. Do moist heat waves get worse like hot days? Yeah. Yeah, so I think I showed a map a couple of like on an early slide showing the frequency of the moist heat events over time, and they're becoming more and more frequent with warming. And I don't think that scales exactly with like quantitatively with the dry temperature, because again, they're kind of dominated by the humidity. So they're not necessarily changing kind of at the same rate as the dry bulb temperature events, but they are becoming more frequent as we warm the planet. And then obviously, hopefully I made a compelling case for why we don't want to get anywhere near something like 7 degrees of warming, because there would be regions of the globe that were just completely uninhabitable.
Time is a Pair asks, thanks, Margaret. Do studies take into account WGBT differences when the people feeling heat are inside and not in the sun, basically? I think this is what.
Yes. So some of the metrics so all of the metrics assume that you're in the shade. That's kind of baked in because you would have more propensity to feel heat stress if you were experiencing that radiation from the sun directly. And then so that's right. So that's kind of an idealization, right? Like this is like perfect conditions. When is it just not survivable under any conditions? And so it's already accounting for the kind of for being protected from the sun's rays. Of course, you might say, well, we have air conditioning, so it's okay. And I think that's true, but you wouldn't be able to go outside at all under some of these temperatures that we're talking about. And not to mention, like, if it makes you uncomfortable, that it makes me kind of uncomfortable to be thinking like there's a big productivity, right? A lot of people work outside, right? That's how we get our food. So there's a big productivity. Like some people, we have to have some people outside. Otherwise, we know that the economy is less productive when there's a lot of heat. And so, there's a lot of other factors too that we need to consider that aren't considered in these kind of really like upper limits that I introduced, these kind of like fundamental, no longer survivable limits that I introduced. So yeah, but that's a great question. This is clearly a very informed question asker, because the impact of the sun's rays kind of compounds the effect of heat.
Okay, there's another question from Future Ghost, but we do not have time. So if you have the ability to answer it in the live stream. We have come to that time of the live stream where we have to reboot. We have technical limits on how long we can make each individual chunk of this live stream. And so what's going to happen now is I'm going to wave goodbye and this live stream will stop. Go back to wclivestream.com/watch. And we're going to reboot it. Just go back there and I will see you on the other side in about 90 seconds.